They can share, sir.
They can share, sir, now?
Yes, sir.
Yeah. Sir,
Yeah, it is.
Yeah, okay. 1 minute. Yeah. Answer Matthew, you are there?
Yes, sir. Yes, sir. Am I audible?
Yeah, you are audible. You can. Sir, are you ready, sir? Mahesh, sir?
Just give me a minute, sir. Just give me a minute.
Okay. Mahesh, sir? Mahesh, sir? Sir? Hello? Can you hear me? Answer, can you hear me?
Yes, sir.
Sir, you are muted again, all the people. Can you hear me, sir? And that Mahesh, the speaker, no, you are muted him. He cannot talk.
Okay, sir. Okay.
You just see, sir, all the people, please unmute them. At least these people. All these names which are given to you, please unmute them. Otherwise, they cannot conduct the program.
Okay, sir. Okay, sir.
Yeah.
Hello, sir.
Hello, Mahesh, sir.
Yeah. I'm able to unmute myself.
Yeah. Okay. Good morning, everybody. I welcome all of you for the second day of our international conference on new trends in differential equations and applied mathematics. So I welcome all of you, and over to Ansar to introduce the speaker of the day. Ansar Matthew, can you hear me? Ansar Matthew? Sir, please unmute all the people, the names which I gave you, sir.
Good morning, sir. Am I audible?
Yes, Ansar.
The capacity to learn is a gift. The ability to learn is a skill. The willingness to learn is a choice. This was quoted by Brian Herbert. Good morning to one and all present here. I, Ansa Matthew, research scholar, Department of Mathematics, Christ, deemed to be University, warmly welcome you all to the second day of the International Conference on New Trends in Differential Equations and Applied Mathematics, ICNTDEAM 2021. Organized by the Department of Mathematics, Sri Vidya Mandir Arts and Science College, Krishnagiri, Tamil Nadu, in collaboration with Department of Mathematics, Jyoti Engineering College, Thrissur, Kerala, and Department of Mathematics, Christ, deemed to be University, Bengaluru. Without much delay, we move on to the session for the day. I request Meghna ji to introduce the first speaker for the day.
Good morning, everyone. It's a great pleasure for me to introduce our first speaker, Dr. Mahesha Narayana. He holds PhD from Gulbarga University. He completed his postdoctoral research at the university in South Africa. He was a part of the DST research project from the year 2005 to 2008. He has almost 17 years of teaching experience. Currently, he is working as a senior lecturer in the Department of Mathematics in the University of West Indies, Jamaica. He has almost 36 national as well as international publications to his credit. He has delivered around 15 invited talks in various national and international conferences. Now, I kindly request Dr. Mahesha Narayana to deliver the talk.
Thank you, Meghna, for that kind introduction. And at the outset, let me first ask you if the screen that I'm sharing is visible to you, and am I audible to you?
Yes, sir. Yes, sir. We can
Right.
see your screen and audible also.
Yeah, thank you so much.
Voice is clear, sir.
Yeah, thank you so much for the confirmation, sir. So I would like to thank the conveners of this international conference on new trends in differential equations and applied mathematics to give me an opportunity to take part in the conference and present my work. And I congratulate Sri Vidya Mandir Arts and Science College and Christ deemed to be University, Bengaluru, for putting this wonderful conference during this pandemic time. And it's good that everybody is being at home and able to attend conference. So this is one of the advantage of such a pandemic. Though there are other bad phases of it, so we should look at the good things. So with this note, I would like to present my lecture on exact solution of the boundary value problem arising from heat transfer in a nanoliquid flow due to a quadratically stretching sheet. So the focus will be on the differential equations, that is mainly the boundary value problem, and how we are able to get the exact solution of that boundary value problem. And also there is an application point of view that it is coming from quadratic stretching sheet problem, which has industrial applications. And this problem is studied with the help of nanoliquid as a coolant. All right. So this is the outline of the talk. So I'll be introducing you to the problem and necessary preliminaries to get started. And I will talk about conservation laws and the models for nanoliquid. And I'll take you to flow analysis thereafter, and then the heat transfer analysis, and the engineering point of view, the two parameters which are important, that is the skin friction parameter and the Nusselt number. So I will take you to the definition of those two parameters, and finally I'll discuss the results coming from the exact solution and some conclusions based on the results. All right. So now let us understand what is meant by a stretching sheet problem. So many of you working in the area of boundary layer theory would have come across such a problem, which is usually encountered in extrusion process, something like polymer extrusion processes. So you will have an extruder, and you can see this particular place where the plastic pellets can go in, and the extruder start melting those plastic whatever material, and there is a die which is at the end of the extruder. So this molten material comes out of the die, and it is drawn into the cooling liquid with the help of a puller. And while the sheet is drawn into the cooling liquid, so it is also being stretched. So that's why the problem is known as the stretching sheet problem. So the puller tries to stretch, and there is a last device which tries to roll this polymer sheet and for further application or further processing. All right. So the main part where we are interested in is in the cooling stage. So the middle one, the cooling stage. So here you have a cooling bath. So this liquid is at rest. So the object is being stretched. So what happens is that it is slightly different from the usual boundary layer flow past object. So let's talk about Blasius flow, where a flat object is at rest, and there is a flow past the plate. So the boundary layer is observed at the surface, close by the plate. So it will have a zero velocity at the plate, and as you move away from the plate, it will reach the stream velocity. So it is quite opposite to that kind of boundary layer flow. Here, the object is moving, the liquid is at rest. So it is a coerced flow that the sheet, which is coercing through the liquid, will take the liquid in the vicinity along with it. So the maximum velocity is observed at the sheet, and as you go away from the sheet, the velocity decreases to zero. So it's a very interesting problem from a boundary layer point of view, and it has a lot of industrial application in the form of polymer extrusion process. And it is not limited to only this. So there are other processes, something like drawing of metallic plate to a cooling bath, condensation process, production of papers, blowing of glass, tinning, coating process. All these are giving rise to something like a stretching sheet problem. So these are some of the industrially important processes wherein one come across the stretching sheet problem. And there are two important key factors that determine the properties of the extruded. So the desired mechanical properties for the best outcome in such extrusion process would greatly depend on how the sheet is being cooled. So how the sheet is being cooled depends on the two things, that is the choice of proper coolant and how we could regulate the flow of the coolant. So the second one, that is regulating the flow of the coolant, is done by some external agencies like application of magnetic field. If the carrier liquid is weakly magnetic fluid, then we can regulate its motion by application of magnetic field, or you can try to introduce periodic oscillations where you can regulate the flow. So that is one kind of thing which we are not looking at this work. So what we are looking at is the choice of coolant. So the choice of coolant plays an important role as well. So one particular class of liquid that we are looking at, which is very popular in recent days, known by the name of nanoliquids. Okay, so nanoliquids, it's a mixture of base liquid with nanoparticles. So as you can see it in this figure, so the nanoparticles are of the size of nanometers, and they are mixed with this base fluid. So base fluids, something like water, and you use some agencies like dispersing device, or with the help of dispersant, you will try to disperse the nanoparticles homogeneously in this base liquid. So that gives rise to a nanoliquid. So it's basically one of those suspensions with suspended particles of the size of nanometers. All right. So this nanoliquid has gained a lot of interest and popularity because of its high industrial importance. And what makes such a liquid very important is the question. So usually the base liquids like water or oil or something else, they have very poor thermal conductivity. So their cooling capacity is limited. So once we have this nanoparticles added to the base fluid, and which gives rise to a nanoliquid, will greatly improve on the conductivity aspects of the liquid. So the heat carrying capacity and heat transfer properties are very much enhanced in such a liquid. So because of this, it has been widely used in industries, and it has been widely studied in recent days. So the term nanoliquid was first introduced by Coy and Eastman during 1995, while they were working at Argonne National Laboratory, USA. And they were trying to synthesize such a liquid, and they came up with this name, nanoliquid. And compared to the micro-sized particles, so which we can see in micropolar fluids, so nanoparticles possess a high surface area to volume ratio. So due to the occupancy of large number of atoms at a small region, so which makes them highly stable as suspensions. So other suspensions with the micrometer-sized particles will have this problem of coagulation or settling at the bottom. So you can't keep them dispersed uniformly over a long period of time. So the big advantage of nanoliquids is that so the nanoparticles that are introduced can be kept dispersed uniformly. All right. So this is about nanoliquid, and the basic constituents of the nanoliquid, as I told, are the base liquid and the nanoparticles. So the commonly used base liquids, as I mentioned, water is one of those, and ethylene and triethylene glycols, oils and other lubricants, biofluids, polymer solutions and others, and also glycerin and some other fluid, engine oil perhaps, which comes under the other lubrication category. So these are some of the commonly used nanoliquids. And some of the commonly used nanoparticles are metal oxides like alumina, that is Al2O3, copper oxide, then titanium dioxide, then carbides like silicon carbide, nitrides like aluminum nitride, silicon nitride, and metals like copper, silver, gold. So non-metals like the carbon compounds like carbon nanotubes, graphites, graphene, and there are some specialized functionalized nanoparticles. So based on the surface modification, they are used in the area of medicine for prolonged imaging. So these are some of the commonly used base liquids and nano particles, and mixture of that will gives rise to nano liquid. So there are plenty of other applications of nano liquid. So what we are looking at in this study is its heat transfer properties. Okay, so here I mentioned some of the advantages of using nano liquids. So the absorption of thermal energy will be maximized with the change of size and shape and the material volume fraction of the nanoparticle. So volume fraction of the nanoparticle is basically the concentration of nanoparticles. So it is it's basically how many particles are being dispersed over a given volume. Okay, and the suspended nanoparticles increase the surface area because of their smaller size, and thereby increasing the heat capacity of the liquid. And suspended particles enhance the thermal conductivity, as I mentioned earlier. So this helps them to be very efficient in the heat transfer systems. And suspensions of nanoparticles can provide enhanced stability against sedimentation and coagulation with better thermal, mechanical, electrical, and magnetic properties. And to make a suitable liquid for catering a particular application, so properties of liquid can be changed by varying the concentration of the nanoparticle. That's another advantage. So you could come up with different concentration nanoliquids based on your needs. And nanoliquids can also be used as coolants in heat transfer equipment, such as heat exchangers, electronic cooling systems, radiators, and so on. So we can talk about nanoliquids whole day, but let us move on to the next thing, which is the main aspect, which is the models of nanoliquids, because it'll be using this nanoliquid as a coolant because of its importance in heat transfer enhancement. And therefore, we need to know what are the available models for nanoliquids. So there are two models. One is the single phase model. The other one is the two-phase model. In single phase model, we assume the local thermal equilibrium between the solid and liquid phases, and the liquid particles and the solid particles will have different thermal properties, whereas similar properties when the flow is concerned. And here the solid fluid mixture is assumed to behave as a single continuum. And the thermophysical properties are modeled based on the phenomenological laws and the mixture theory, which we will take up shortly. And in the two-phase model, so there is a non-equilibrium, thermal non-equilibrium between the solid and the liquid phases. And the enhancement of thermal properties are explained based on the thermophoresis and Brownian motion effects. And the model is based on the conservation laws in which the solid and fluid phases contribute separately to the heat transfer. So there will be a conservation of energy equation and also conservation of species while modeling using a two-phase model. And there are also other hybrid models which mix both single phase and fluid phase, two-phase models. So for the present study, we'll be studying the single phase model, which is good enough to capture some of the important things. All right. So yeah, so the problem that we are looking at is this boundary layer flow due to a quadratically stretching sheet. So here I should explain what is meant by quadratic stretching sheet. So the velocity with which the sheet is being stretched, usually if it is proportional to the distance from the slit. So the slit is assumed to be at origin, and x-axis along the sheet, and y-axis normal to the sheet. And the x that you measure from the slit, the velocity is proportional to the distance. If it is just equal to alpha x, then we call such a stretching sheet as a linear stretching sheet. And if we introduce a mild perturbation in the form of a quadratic term, that is plus beta x square, then we have what is called as a quadratic stretching sheet. And many researchers have argued that the stretching sheet velocity need not remain linear all the time. So we need to add a mild perturbation in the form of quadratic velocity to model it in a proper way. So in that viewpoint, with that viewpoint, I'm considering a quadratic stretching sheet problem. And as I mentioned, so there will be a boundary layer in the region close to the sheet. And as you can see in this figure, the maximum velocity will be observed at the sheet. And as you go away from the sheet, the velocity keeps decreasing and finally reaches the ambient velocity, which is 0. Same thing happens at the for the thermal boundary layer. So the temperature will be very high at the sheet because it's a hot molten sheet which is being stretched to the cooling bath, and therefore has a maximum temperature at the sheet. And as you go away from the sheet, the temperature decreases. So what we are looking at is how best we can exercise the cooling of this sheet with the help of nanoliquid, so that we can arrive at good properties of the extrudate, which is the sheet being stretched. All right. So the governing equations, which is the continuity equation and conservation of linear momentum, conservation of energy, written for the nanoliquid. So as shown in equations 1, 2, 3. And for incompressible nanoliquids, the equation will just reduce to divergence of Q equal to 0. And the second equation, which is the balance of forces, which can be regarded as Newton's second law for liquids. Okay, so the rate of the left-hand side represents the rate of change of momentum. The right-hand side is the net force, that is various forces acting on the fluid element. Okay, and here Q is the velocity vector, P is the hydrostatic pressure, and mu NL is the viscosity of the nanoliquid, and KNL is the thermal conductivity of the nanoliquid, and rho CPNL is the heat capacity of the nanoliquid, and T is the temperature, and the small t is the time. So we will be looking at a fully developed steady state flow. So we'll assume the time derivatives to vanish. Okay. Okay. So in a single phase model, the thermophysical properties are modeled based on the phenomenological laws and the mixture theory. So for the viscosity and thermal conductivity, so one can use Brinkman model for the viscosity, which is given in equation number 3. I'm sorry, equation number 4 perhaps. Yeah, equation number 4. And the Hamilton-Crosser model, which models the thermal conductivity of the fluid, which is given in equation 5. And the subscripts S denote here the solid phase, and L denote the liquid phase, and phi is the nanoparticle volume fraction, and it is a small amount that is added, small amount of nanoparticle which is added to the liquid. Therefore, phi is a very small quantity, usually of the order of 6% or less. Okay. And this is required. This is one of the conditions for your Brinkman law to hold. So if you take higher particle concentrations, then these laws may not be valid. So to keep them working, so we should have this particle fraction to be under 6%. Okay, so the density and the heat capacitance are modeled based on the mixture theory. So the density of the nanoliquid, for the density of the nanoliquid, there is contribution from the solid phase. So rho s is the density and phi is the volume fraction. So that is the contribution from the solid phase. And remaining 1 minus phi will be the liquid occupancy, and rho L is the density. So 1 minus phi into rho L gives the contribution to the density from the liquid phase. So this is mixture theory. Okay, so and heat capacitance is again coming from the solid phase as well as the liquid phase, as given in equation 6 and 7. And these are the symbols which I explained you earlier that appear in the conservation equation. So the thermophysical, so in this study, we are looking at two nano liquids, one with copper nanoparticles and the other one with aluminum oxide, which is commonly known as alumina. So alumina nanoparticles, and with the base liquid as water. Okay. And here in table 1, we have listed some thermophysical properties of both the base liquid as well as the nanoparticles. So these are the images of copper nanoparticles and alumina nanoparticles at the nanometer level. Okay, and table 1 gives you the list of properties for the used base liquid and the nanoparticles. Okay, and these are the things that are used in the conservation equations as well as for the computation purpose later on. All right, so when we apply boundary layer approximation to equations 1 and 2, we get equations 8 and 9. So the usual boundary layer approximations, where we assume that the axial velocity is predominant as compared to the transverse velocity, and the variation of axial velocity in the transfer direction are predominant as compared to variation of axial velocity in the axial direction. So this is a standard boundary layer approximation, and with the help of that, equation 1 reduced to equation 8. So this is due to the incompressibility condition that I mentioned earlier, and equation 9 is due to the boundary layer approximation. And the v component or the y component of the velocity just vanishes because of the boundary layer approximation. So you have a single equation for u. So there are unknowns at this time. U and v are the unknowns. So we have two equations in the form of 8 and 9. And here nu NL is the kinematic viscosity of the nanoliquid, which is the ratio of viscosity to the dynamic viscosity to the density. And as mentioned earlier, mu NL is modeled using Brinkman law, and rho NL is modeled using mixture theory. So those information will go into equation number 9. And the boundary conditions that are used, as I mentioned earlier, so it's a quadratic stretching velocity, which is more realistic than a linear stretching velocity. And we also assume vertical through flow, which is given by VW plus delta X. So this is for only the mathematical analysis part of it. Because if you just take, what we want is an impermeable sheet. So for the impermeable sheet, VW will be 0, delta will be 0. So that forms a special case, and that is a more practically oriented case. And the reason why we have introduced VW and delta here is for the mathematical analysis point of view. And without that, if you just assume 0, V to be 0, as pointed out by I'm not getting the researcher's name. I'll show you Kelman, maybe, yeah, Kelman's paper, where he has pointed out that with V equal to 0 and U equal to alpha x and beta x squared, it's not possible to arrive at the exact solution. So this you can say that it's for the mathematical analysis point of view, but the correct boundary condition, which is V equal to 0, is also a part of this general velocity. With VW 0 and delta equal to 0, we get the impermeable case. So with that in mind, we proceed to the mathematical analysis. So what we need to do is solve equations 8 and 9 subject to conditions 10A and 10B. And 10B, as mentioned earlier, is the ambient condition where as you go away from the sheet, y tends to infinity, the velocity goes to 0 because the ambient fluid is at rest. So the boundary conditions in 10A for U and V are respectively due to no slip and vertical through flow, and the condition at 10B is due to ambient quiescent state, which is the rest state. And the constants alpha and delta appearing in the equation 10A have dimensions of per time, and beta has the dimension of per time per length. Okay, so we need to keep beta and delta to be very small, just to make to make them see that they are very mild perturbations. Okay, so alpha, delta and beta are very small numbers, and VW positive represents the blowing case, and VW negative represents the suction case. And we use on this non-dimensional variables to put the governing equation in this form. So equations 12 and 13 are the non-dimensional form of boundary layer equations. So here you have 1 by phi 1, where phi 1 is defined to be 1 minus phi to the power 5 by 2 times 1 minus phi into 1 minus phi plus phi into rho s by rho l. And this is a parameter which depends on the volume fraction as well as the densities of the constituents. And the boundary conditions are put in this form, 14A and 14B. And these are the non-dimensional numbers that appear in the equation. So beta star is the quadratic stretching parameter, and delta star is both of them are quadratic stretching parameters, and VW can be regarded as transpiration parameter. And we use on this stream function formulation just to eliminate the number of variables. So there are two unknowns, U and V. Now, with the help of this, we will have a single unknown psi, which is a stream function. And equation 16 is the corresponding equation of motion, and 17a and 17b are the respective boundary conditions in terms of the stream function. And the problem allows a solution of the form x into f of y plus beta star x square into g of y, where this quadratic stretching parameter beta star will appear in the solution later on. So this is unlike in the linear stretching sheet case. The stretching parameters appear implicitly in the dimensionless variables, whereas here they appear explicitly in the solution, which enables us to have them as one of the controlling parameters. So as mentioned earlier, the way we cool the sheet is very important, and if the stretching rate is controlled with the help of the stretching rate, sorry, what I was saying. So if the stretching rate can be controlled as a controlling parameter, then that will enable us to cool the liquid in an optimum way. Okay. So here the unknown functions f of y and g of y are to be determined, and we'll substitute equation 18 into 16, which will give us equations 19, 20, 21, which are three equations for the three unknowns. I'm sorry, there are three equations for the two unknowns. So this defines a over-defined system. So there are only two unknowns, f and g, but there are three equations. So we'll have to sort out this consistency issue, and how we'll handle is presented shortly. So the boundary conditions in terms of f and g are given by 22 and 23. And here we introduce another variable s, which is ratio of delta square to beta delta star to beta star. So we further use on scaling just to enable us in finding the exact solution, and the scaling is given in equation number 24, and with the help of the scaling, the equations are put in the form of 25 to 29. So this is a scaled boundary value problem, and as mentioned, so there are two unknowns, f and g, and there are three equations. So what we do is first solve the equation 27 subject to conditions 29. So equation 27 subject to 29 gives a solution of the form gy equal to minus phi 1 s into exponential y by s as given in equation 30. And once we substitute for g in the intermediate equation, that is 26, we get a second order differential equation for f, which is non-homogeneous. So when we solve for this second order differential equation subject to boundary conditions 28, we will end up getting the solution for f of y as given in equation 32. And now that two equations are covered, 26 and 27, we need to see that this function f of y, what we have, has to satisfy equation 25 in order that all the equations are being covered. So once we substitute f of y into equation 25, it will result in a consistency condition. So the consistency condition is this particular equation, s square minus vws minus 1 by phi 1 equals to 0. So the solution therefore exists for these values of s as given in equation 33. So we consider a positive root from equation 33 just to have the solution in line with the physics of the problem. Okay. And with the help of this equation 33, the solution f of y can be written as given in 34. And we redefine S star as 1 over S just to compare our solution with whatever has already appeared in the literature. And with that, we have f of y and g of y rewritten in form of S star, and corresponding stream function is given by equation 37. So we should note here that such a solution is also assumed with the help of boundary conditions. So the boundary conditions will dictate a solution of this kind. That is what people have done while studying stretching sheet problem. So by considering a quadratic mild perturbation, one can actually derive such a solution. So here the solution is being derived in a mathematical rigor. It is not assumed. But most of the case, when we study stretching sheet problem, it is the assumed solution of this kind. Okay, so that's what I want to mention at this point. So with the help of the exact solution, the velocity components can be written as given in 38 and 39. And I think, sir, how many minutes are left? I think I'm going over schedule.
Another 3-4 minutes. Can you?
Yeah, sir. I'll try to wind up.
Yeah.
Thank you so much. And the heat transfer, for the heat transfer analysis, there are two boundary heating processes are being used. Surface temperature, prescribed surface temperature, where surface temperature is mentioned, and prescribed heat flux, where the sheet heat flux is mentioned. So these are the PST boundary conditions. And the solution in this particular case is assumed as given in 42. So it's again by the nature of the boundary layer that we have. So once we substitute such a solution, it looks in the form of separation of variables, if you see. So t is a function of x and y. So this uw of x is a function of x. Theta of y is a function of y. And when we substitute that in the governing equation, we get equations 44 and 45, with PRNL being the nanoliquid Prandtl number, and phi2 is the another nanofluid parameter. And once we substitute for this uw and compare coefficients of x and x square, we end up getting two equations. And again, here there is a consistency issue. There's only one variable theta, which we need to find, but there are two equations. And again, what we do is solve equation 48 subject to given boundary conditions, and then use that in equation 47 to arrive at a consistency condition. So equation 48 admits an exponential solution as given in equation 49, and that when we substitute in equation 47 give us a consistency condition. So that means it is the exact solution does not appear for all choices of m. So only such a choice of m, that is m equal to PRNL by phi1, only for such values of m. So the problem has an exact solution. And the exact solution for theta is given in equation 51. And yeah, so the wall heat flux is defined in this case as given in 53, and the temperature distribution is given by 52. And similarly, one can do for the other boundary combination, boundary condition combination, that is. So which is a prescribed heat flux. So I will just skip this and you can I can share the presentation with you. Then you can go through it if you're interested. And yeah, so with the help of this wall shear stress and wall heat flux, one can define the screen friction coefficient as given in equation 61 and Nusselt number as given by 63. So the two nanoparticles considered were copper and alumina, and water was considered as base liquid. And here we have derived exact solutions wherein the stretching rate is part of the solution, and hence it gives us an opportunity to consider that as a controlling parameter. And the solution exists for this choice of S star, which is given by this equation in this slide. And the S star versus VW is shown here. And you'll see that the stretching parameter S star, which is the ratio of stretching parameters, it decreases as a function of the nanoparticle fractions. And same thing is observed for the alumina, but the variation is not that predominant. So the streamlines are plotted using this particular expression, and you'll see that we can observe a lifting effect at the sheet because of the quadratic component of the stretching velocity. And yeah, same thing holds for alumina water nanoliquid. And here we cannot make out anything about what happens, I mean, which nanoliquid is better in terms of flow. So for that, one can plot the velocity distribution U. So you'll see that the copper, I mean, it clearly indicates that in the absence of nanoparticle, the velocity is more, and in the presence of nanoparticle, the velocity is less. And that is quite understandable because the suspended particles will enhance the viscosity, and therefore they'll reduce the flow a little bit. And these are very much in line with the physics of the problem. And here we have plotted the temperature profiles as a function of time. And you'll see that in the absence of nanoparticles, the temperature profiles are less. And as you increase the nanoparticle fraction, the temperature profiles increase, meaning that there's more heat transferred to the boundary layer region from the sheet. So that is the advantage of using nanoliquid. So it carries the heat at a larger scale than the usual coolant. Okay, and the temperature distributions are shown here. Again, you'll see that based on the computations, the Al2O3 water nanoliquid, which is alumina water nanoliquid, has more temperature distribution as compared to copper water nanoliquid, meaning that it takes the heat away, more heat away from the sheet. So from the solution and the results, we can conclude that alumina water can be used for better cooling. All right, so these are some of the conclusions. And yeah, so we can obtain the clear liquid results and the linear stretching sheet results by taking phi equal to 0 and beta star equal to 0. And results of the shrinking sheet problem can also be obtained using appropriate sign change in this problem. And yeah, so Yeah, as mentioned earlier, velocity is a decreasing function of nanoparticle volume fraction, and alumina water nanoliquid possess increased temperature distribution. And the solution of quadratic stretching sheet problem exists for all possible transpiration parameter VW, but the one which is of importance is VW equal to 0, which is a part of this solution. Okay. So with this, I conclude my talk, and these are some of the references that are used, and I will leave the presentation with the organizers, so you can share, and if you're interested, you can look into it and try to make out if I missed something in the talk. Okay, so with this, I thank once again the organizers for giving me an opportunity to present this work, and I will open myself to questions if there are any.
Thank you, Mahesh sir, for the wonderful talk. Now, if anyone has any questions, I'm sure Dr. Mahesh Narayana would be pleased to answer them. I request participants to unmute the audio if you have any questions. If you are streaming the video in YouTube, kindly post your queries in the comment section.
I think there is one hand raised by Subir there. I think I did not notice that earlier. Subir, if you have any questions. Maybe it's by mistake. I'm not sure.
So I can conclude that. I think.
Hello.
Questions.
Yeah.
Hello.
Yeah. Please go ahead.
Sir, I am Subir Kumar Dev from West Bengal. Yes, there is no question about your paper. Actually, I want to present my paper on the existing on differential geometry mainly.
Okay.
So, how can I represent my paper?
I think you can ask with the organizers. They'll try to help you out with your presentation.
Okay, thank you.
Yeah.
Those things you just send a message to organizers, they will help you out in doing that. Yeah, and so you can conclude them.
Once again, thank you, Mahesh sir, for the wonderful talk.
Yeah, thanks, Ansa, and
Thank
thanks,
you, Mahesh sir. Thank you, sir.
Thank you so much for this opportunity.
Thank you.
Yeah, thank you, sir.
Thank you, sir.
And participants, have a good day. And so, bye bye from me. Take care. So, can I leave the?
Yes, sir. You can stop sharing this.
Okay, thank you, sir.
If you feel like if you are free, you can just stay in the meeting. Otherwise, thank you very much once again.
Yeah. Thank you, sir. Thank you. Bye bye.
So good morning, sir.
Yes, good morning.
Good morning, sir. I will introduce you.
Good morning.
Sir. Okay.
Yeah.
Our next, yes, sir. Am I audible?
Yes.
Our next speaker for the day is Dr. S. Karthikeyan, Assistant Professor, Department of Mathematics, Peria University. He has received his MSc, MPhil, PhD degree from Bharatiya University. He was a recipient of the ICM Open Arms Grant to participate the ICM Rio de Janeiro, Brazil, and also full travel support to participate in ICIAM Valsina, Spain. He was also a part of the research project Studies on Existence of Blow-up of Solutions of Partial Differential Equation, which was funded by SIR, New Delhi, from 2016 to 2019. He is a member of several professional bodies, namely Ramanujan Mathematical Society, Indian Society of Industrial and Applied Mathematics, and American Mathematical Society. Dr. S. Karthikeyan has published over 18 research papers in several reputed journals. On behalf of the entire team, I cordially welcome you, sir.
Sir Karthikeyan, sir.
Yes, thank you. So first, let me share my screen.
You have to share your PPT, sir.
Yeah. Yes.
Yes, sir. We can see your PPT, sir.
Yes. Very good morning to one and all present in this online platform. At the outside, I would like to thank the organizers of Sri Vidya Mandir Arts and Science College, Uttangarai, Christ University, Bangalore, for giving me an excellent opportunity to deliver a lecture in this international conference on new trends in differential equations and applied mathematics. I also appreciate the efforts of these two reputed institutions for organizing such a wonderful conference during this pandemic time. So, of course, there are pros and cons in organizing this virtual conferences because I have a lot of experience, but we should always take the positive part. And with this brief note, let me start my lecture. I will talk on the controllability of dynamical systems and its applications to stochastic dynamical systems.
Thank you, Karthikeyan, sir.
Yes, sir. Am I audible?
Yes, audible, sir. Thank you for your valuable presentation, sir.
Okay, thank you. Thank you so much. Okay, so let me continue. So this is going to be the plan of my talk. I would like to motivate the concept of controllability with some interesting examples, and then I will try to classify the idea of controllability. Further, we will characterize the concept of controllability of deterministic systems, and I will try to extend what are the possible extensions to stochastic control systems. So first, let us consider a very simple differential equations to understand the properties of control system. We just consider a first order differential equation, a simple first order differential equation dx by dt equal to minus 2x with some initial data, and this has a solution which is so this equation admits an exponential solution which is given by 3 times e power minus 2t, and whose trajectory is given in the graph in the first picture. So the same differential equation can be considered with a perturbed term or a forcing term sine t, whose solution is given by something like 1 by 5 and etc. And you can see in the picture that the solution or the trajectory gets changed when this forcing term is included. So this type of system or this type of system with the forcing term is basically called as a control system. So I will give you some of the interesting models where we come across this type of control systems. The first example comes from the vehicle dynamics. So basically, this first order differential equation governs the dynamics of a vehicle where m is the mass, v is the velocity due to the force from the engine, and f of t is the external force or the retraction force, and this nonlinear function is the restrictive force. So here, this is the nonlinear part, and the f of t is the non-homogeneous or the forcing term. Next, let us consider a second order differential equation which governs the dynamics of a simple pendulum, where m is the mass, L is the length of the rigid massless rod, and theta is the angle made by the rod with the vertical axis, and k is the coefficient of friction. And this is basically a second order nonlinear differential equation which governs the dynamics of the pendulum. So we are going to put this in terms of a first order differential equation by defining a state vector of the form x of t is equal to theta of t, theta dash transpose. So we can make the second order differential system into a first order differential system of the form x dash of t equal to a of t, a x of t plus b u of t, where a and b are matrices of appropriate dimension, and u is the function which is given by minus g by l sine x1 of t. Next is another interesting example, which is basically a second order differential equation which governs the motion of a spacecraft which runs, which goes to a height h of t above the surface at time t. So once again, this second order differential equation can also be put in the form of a first order differential form with by making a suitable transformation. X1 is equal to h, x2 is equal to v, and taking u is equal to f by m minus g, where f is the thrust force, m is the mass, and v is the velocity, and g is the gravitational constant. So the basic idea is taking a second order differential equation, or in general any linear or nonlinear first differential equations can be converted into a first order differential system by making use of a suitable transformation. Now let us formalize the basic idea of the control problem. So let us consider the state equation of the form Lx equal to f of u, where x is the state that we are trying to control, u is the control function that comes from a set of admissible controls, and the operator L is, it may be a differential operator or a partial differential operator, which depends on the physics of the problem, and the function f denotes the way in which the control acts on the system. So the main objective or the main goal is to find a function u which takes the system to the prescribed or a desired state. And if we are trying to design a control function with a minimum cost, then that control will be called as an optimal control. So the subject of these questions will be answered by the subject called a control, which was developed by three mathematicians and by Kalman, with a theory of filtering and algebraic approach to control systems, and Potriagan with the maximum principle, which is a generalization of Lagrange multipliers, and by Bellman with the principle of dynamics programming. So now let us put the problem of control system in a more mathematical way. Let us consider the finite dimensional control system of the form 1, where x of t is a map from 0, t to r power n, so which is a n vector, and the control vector u of t is a map from 0, t to r power n, which is an m vector. A and b are matrices of appropriate dimensions, namely A is an n by n matrix and B is an n by m matrix, and n is the number of components of the system that has to be controlled. M is the number of controls acting on the system. In practice, the number of components has to be more than the number of controls. The most interesting case is that the control system which have the minimum number of controls than the number of components. If m equal to 1, it means that the n components will be controlled by a single control or a single input. So now the basic question is, can we find a control function defined on 0, t to take the system from any initial state x0 to the final state x1? The definition of controllability was formally given by Kalman in 1960 as follows. So the system 3, that is the previous system 3, is controllable or exactly controllable in time t, in any finite time t, if for any given initial data x0 and final data x1, there exists a square interval function u such that the state is taken to the final state x1. In other words, the system is said to be controllable in a finite time t if when the set of all reachable state is the whole set Rn. The problem of approximate controllability is slightly different if we are transferring the initial state of the system to an epsilon neighborhood of the final state, then this problem is called as the approximately controllable problem. So pictorially, the problem of controllability can be explained as follows. So the black line represents the transfer of the initial state to the final destination, which is the problem of exact controllability. And the green line and the blue line takes the initial state to an epsilon neighborhood of the final destination. So this is the problem of approximately controllable. So Kalman gave the rank condition for the finite dimensional linear deterministic system to be exactly controllable. So he stated that the system 3 is said to be controllable in a time t if and only if the rank of this augmented matrix is n. If this holds, then this system is controllable for all time t positive. So it is to be noted that the rank n denotes the number of components that are sensitive to the action of the control. So we can just see how we can construct a control function from a very simple case. So let us consider a very simple scalar differential equation, x dot is equal to ax plus bu, where a and b are real numbers with some initial data x naught. So we are going to find a control function u which takes the state from x naught to x1. So for this, we are going to consider a differentiable function z of t, which is given as follows, which is obtained by the method of linear interpolation. It can be easily seen that z of t satisfies the properties, namely z at t naught is x naught and z at t1 is equal to x1. So we are going to show that this is the control function which is going to take the initial state of the system to the final state x1. So to do this, let us consider the basic control system, namely the x dot is equal to ax plus bu. So this can be rearranged to get u something like 1 by b into x dot minus ax. So let us define a suitable control function z using the function z by u is equal to 1 by b z dot minus az. So if we substitute the function u in the original differential equation, we will get a equation from d by dt x minus z equal to a times x minus z with x of t naught minus x of z naught equal to 0. So let us take y is equal to x minus y. So this system can be rewritten as dy by dt minus ay with the initial data at t naught equal to 0, whose solution is given by the trivial solution y of t is equal to 0, which means that x of t agrees with the function z of t, and thus the function u given here is the suitable control function which transfers the system from the state x0 to the state x1. So now let us consider the n-dimensional control system. So here A and B are matrices of n by n dimensions, and we assume that B is an invertible matrix. So the previous case motivates us to design a control function of this form: U is equal to B inverse Z dot minus A Z, satisfying Z of T naught equal to X naught and Z of T1 equal to. If we use this control function in the first order differential system, we will end up with X of T is equal to Z of T. So this control function is a more appropriate control function which transfers the state from x0 to x1. So the most interesting is as follows, where the number of control is less than the number of components. So let us consider the differential system of the form 3, where A has a dimension n by n, B is of dimension n by m, and let us assume that B is an invertible matrix. Let us multiply both sides by the exponential matrix, namely e power minus ta, and integrating from 0 to t is an integral representation of the solution of the system 3, where the exponential matrix is given by this infinite series. If the initial condition x of t naught equal to x naught, if the initial condition is taken to be x naught at time t naught, then if we integrate the equation 4, we will end up with the integral representation which is given here, where P of t is called as a transition matrix of the linear system x dot is equal to Ax. So to construct a more appropriate, more suitable control function, we are going to define a new matrix which is called as a controlability Gramian, and this controlability Gramian was given by Kalman, which is an n by n matrix. Then if u of t takes this form, namely u of t is equal to b star p star wt inverse x1 minus p of t x naught, where this star denotes the matrix transpose, then this function u will transfer the system from x0 to x1. It can also prove that this function u is the optimal control, which means that it has a minimum L2. In general, the concept of controllability and the concept of approximate controllability are equivalent in the case of finite dimension, but they are not equal in the case of systems. So now let us try to idea of controllability to stochastic dynamical systems. Let us consider a differential equation which is perturbed by a new term c times xi of t, where x is the state, u is the control input, xi is the external disturbance, and y is the output, and a, b, c, and d are matrices of appropriate dimension. If this external disturbance xi of t is taken to be a white noise, which is the derivative of the Brownian motion, then we will end up with an Ito equation or a stochastic differential equation of the form 5, where W of t is the Wiener process or an n-dimensional Wiener process. So we come across many difficulties when we move from deterministic to stochastic control. So the problem here is understanding the state space. In case of deterministic control systems, the solution are just real valued functions, but in the case of stochastic systems, the solution are something like a random process. So the state of stochastic systems or random variables taking some values in the state space X. Thus, the extension of complete and approximate controllability concepts to stochastic control systems is a little bit difficult. Therefore, there should be some steps to weaken these concepts to extend them to stochastic control systems. There are two different approaches. The first approach considers the space X along with a suitable space of X valued random variables, which serves as a respective state space. And then we can try to prove the closeness of the attainable set dt to the larger space X, either dt equal to X or dt is dense in X. And the second way is approximating every point of the smaller space by random variables from dt in some probabilistic sense. So now let us consider a stochastic control system of the form 6, where X is an n vector, A and B are matrices of appropriate dimension, and sigma is a function from 0, t to r power n cross n. Then the stochastic differential equation is equivalent to an integral representation, which is given as x of t is equal to phi of t x naught plus integral 0 to t p of t minus s b times u of s ds plus 0 to integral 0 to t p of t minus s sigma of s dw of s, where this p of t is the transition matrix, which is an exponential matrix. So in order to study the concept of controllability of stochastic dynamical systems, we need the following sets and operators. So omega ft is the probability, denotes the probability space with the probability measure p on omega, and the set ft is the process. L2 of omega ft rn is the space of all ft measurable and square integral random variables with values in Rn, and L2 0, t Rn is the space of all square integral functions and ft measurable process in Rn. So in order to construct the controllability matrix, we need to define operators on an infinite dimensional space. So we define an operator, namely this is a bounded linear operator from L2 to L2, which is defined as here. We also require the adjoint of the above operator, which is given by LT star and is defined as follows. And we consider the set of all states attainable from x naught, which is given by RT, where this x of t is the solution of the stochastic dynamical equations corresponding to x naught, and u is the u comes from the set of all admissible controls. Now we define the controllability operator gamma t, which is associated with stochastic dynamical system 6, which is defined as follows. So this controllability operator is very, very important to construct the appropriate control function. So here gamma of t is a bounded linear operator from an infinite dimensional space to another infinite dimensional space, namely the set of all square integrable functions L2. And the small gamma is the controllability matrix associated with the deterministic dynamical system. So now we formally define the problem of controllability of stochastic dynamical system. The stochastic control system is said to be completely controllable if the set of all reachable states is equal to the whole space, namely the L2 space, which means that all the points in L2 can be reached from the point x naught at time t. And the problem is said to be approximately controllable if the set of all reachable set is dense in this L2 space. This means that all the points in L2 can approximately reach at time t from any arbitrary initial point x naught in L2. So the following gives an equivalent condition for the controllability of stochastic dynamical system. So basically, if the deterministic system is controllable, then the stochastic system is completely controllable on 0, t, and stochastic system 6 is also approximately controllable on 0, t. So now we can design an appropriate control function which can transfer the state from x0 to xt at time t. So let us assume that the operator, the controllability operator, gamma t to be an invertible matrix. Then for any arbitrary final state and the linear function sigma, the control function given here will transfer the system from x0 to xt. So the proof of this result is very, very simple. If we substitute x of t in the original equation and taking x0 equal to, taking t is equal to 0, we can see that x of t naught equal to x0, and taking small t equal to capital T, we can see that x of capital T is equal to the final state, namely xt. So now we can extend the concept of controllability to nonlinear stochastic systems. So here we are going to consider an interesting model which is called as a cascade connection model. So there are two mixtures, namely M1 and M2 with different concentration, namely C1 and C2, which flows from one end to the other end. So here C1 and C2 are the input concentrations of the product. Q1 star and Q2 star are the constant flow intensities for concentrations C1 and C2. V1 and V2 denotes the volume of mixtures 1 and 2. C1 and C2 are the strength of solutions in mixtures 1 and 2. H is the arising in the reactor. So the dynamics of this model can be put in the form of a first order differential system with state delays. So here x dot is equal to a naught x of t plus a1 x t minus h plus b into u of t. So the same problem can be imagined where more number of delays can occur. So just like the equation 7. So in the equations in the equation 7, we have included more number of state delays in the stochastic control system with the initial data 8. So here AIs or matrices, AIs and B or matrices of appropriate dimensions. Sigma is a linear function. HI or the constant delays which satisfies these properties, and the xt denotes the trajectory of the system with initial data defined on the interval minus hm comma 0. So the integral representation of the equation 7 is given by the equation 9, and it can be proved that this integral representation is a unique solution of the system 7 on the interval 0 comma t, where F is the transition matrix given by 10, which satisfies the property that F at 0 is an identity matrix and F vanishes when t is less than 0. So the equation 9 can be rewritten in the form when u of t is assumed to be 0 when t is positive. So we get an equivalent representation as given here. Now we shall define the sets and control operators to establish the controllability problem. So the bounded linear operator LT, which is a map from an infinite dimension space to another infinite dimension, basically L2 space, which is defined as L2 as LT, and its associated adjoint operator is given by LT star. Now we can frame the linear controllability operator, the big, which is a bounded linear operator, and the associated deterministic matrix GT as here. So now we can extend the idea of linear control systems to nonlinear control systems. So let us consider a delayed nonlinear control system of the form 11, where the nonlinearity is introduced in the function sigma. So the idea here is to represent the solution of 11 as an integral representation, and we are going to use the fixed point technique to establish the uniqueness of the solution. So we are going to assume that basically the ellipsis condition and the linear growth condition on the function sigma, which is given by h1 and h2, and we are going to assume that the linear system is completely controllable. With these assumptions, we are going to all square integrable functions and ft measurable process with this norm. And now we are going to define a nonlinear operator p from b2 to b2, which is defined as follows, that is given by 12. So where this u of t is the control function which transfers the system from x0 to xt. So we are going to prove that this nonlinear operator possesses a unique fixed point with the help of Banach contraction principle. So the following theorem states that if the linear stochastic system 7 is relatively exact controllable with the assumptions h1 and h2, then the semilinear stochastic system is also relatively exact controllable if this inequality 14 is satisfied. So to prove that P is a contraction, to prove P has a point, we are going to employ the Banach contraction principle. So to employ the Banach contraction principle, we will prove that P maps B2 into itself, and then P is a contraction on B2. So since we assumed the inequality 14, we can see that P is a contraction on B2, which proves that this P has a fixed point, and this proves that the nonlinear operator has a unique solution, and that guarantees the existence of the control function u of t. And there are many open problems as far as the control problem for stochastic dynamical systems, in particular control problems for stochastic PDEs or at an infant stage, as well as the inverse problem for stochastic PDEs or also at an young and budding researchers or welcome to work in this particular areas. So these are all some of the references. An introduction to stochastic differential equation by Evans is a very good textbook to start with stochastic differential equations. And the paper by Mahmoudou and Zurlo or the basic papers which started the idea of controllability for nonlinear stochastic systems. And the reference 12 is also one of the best textbook for starting with stochastic differential equations. If you have any questions, I'm happy to answer.
Now we are open for questions. If participants have any questions, I'm sure Dr. S. Karthikeyan would be pleased to answer them. You can kindly unmute your audio, or if you're streaming the video in YouTube, kindly post your queries in the comment section. Thank you very much, sir, for enhancing us with such an informative session.
Yes, thank you once again. In particular, I would like to thank Dr. Jayakumar and Dr. Raghavan for their invitation. So thank you once again. I will share my presentation with the organizers, and interested participants can receive them. Thank you once again.
Dear participants, we shall break for a tea break for 15 minutes. I request all of you to join back by 11:20. We shall start the next session sharp at 11:20. An humble reminder to all the participants who are presenting their papers, kindly join the WebEx link which is being shared through WhatsApp and Telegram.
Answer Matthew. We can start now the next session.
Yes, sir. We said
If the
11:20.
guest is there, speaker is there,
Yes, sir. We can start, sir.
speaker is there, we have to check that.
Yes, sir. I'll just check.
Pranesh, sir.
Yes, sir.
Please wait for 5 minutes, sir. Madam is joining now.
Yeah, madam is joining now.
Yes, sir.
Yeah. Once she join, we'll start, sir.
Okay, sir. I will tell, sir.
You just inform once she joined there.
Okay, sir. Okay, sir.
Okay.
Okay, sir.
Ansa, you can start, I think so. Madam is ready.
So, madam is ready, sir.
Yeah.
Yes, sir.
Yeah.
It gives me immense pleasure to welcome Dr. Ishwari Prem, Assistant Professor, Government Arts College for Men, Krishnagiri. Ma'am has around 14 years of teaching experience. She has guided around 25 MPhil and 2 PhD scholars. She is also a member of board for studies in Jain Women's College, DKM College, PG Maths, Peria University, and Sri Vidya Mandir Arts and Science College. We warmly welcome you, ma'am.
Thank you, madam. Shall I start, madam?
Yes, ma'am.
Okay. This session, good morning to everyone present. This session, I start with the history of differential equations. It was the 17th century. Some European mathematicians were working on two basic problems. The very first one is it possible to find the tangent to a given curve at a given point of the curve? The second question, is it possible to find the area under the given curve? That two questions are solved by the great mathematicians Newton and Leibniz. Independently solved these problems. The theory that they invented in this process was calculus. Derivative, which is the basic tool in calculus, Leibniz was motivated directly by the first problem. The problem which was of great significance to scientific applications. He recognized the derivative as the slope of the tangent to the curve at a given point. Newton, on the other hand, arrived at it by considering some physical problems such as determination of the velocity, acceleration of a particle at a practical instant. He recognized the derivative as a rate of change of physical quantity. A manuscript dated May 20, 1665 shows that Newton at the age of 23 had sufficiently developed the principle of the calculus to be able to find the tangent and curvature at any point of any continuous curve. He called his method fluxions from the idea of following are variable quantities and the rates of flow or growth. His discovery of the binomial theorem, an essential step toward a fully developed calculus preceded these. We know that a plus b the whole square as well as a plus b the whole cube, etc. up to n terms also. Now, the word function seems to have been introduced into mathematics by Leibniz in 1694. The concept now dominates much of mathematics and indispensable in science. Since Leibniz's time, the concept has been made precise. If y and x are two variables, so related that whenever a numerical value is assigned to x, there is a determined a numerical value of y. Then y is called a function of x. And this is symbolized by writing y is equal to f of x. Our part is discussing about the differential equation now. So coming to that, the rate of change of y with respect to x, or as it is called the derivative of y with respect to x, is defined as follows. To x is given any increment, say delta x, so that x become x plus delta x and f of x or y became f of x plus delta x. The corresponding increment delta y of y is its new value minus its initial value, namely delta y equal to f of x plus delta x minus f of x. As a crude approximation to the rate of change y with respect to x, we may take by our intuitive notation of rate as an average. The result of dividing the increment of y by the increment of x, that is delta x by delta y. If y is equal to f of x, the limiting value of delta y divided by delta x, provided such a value exists, is called the derivative of y with respect to x and is denoted by dy by dx. Apart from Leibniz and Newton, our great mathematician Bhaskaracharya in the year 1114 to 1185 CE has been called the greatest mathematician of medieval India. He was born in Karnataka and is considered the progenitor of differential calculus 500 years before Newton and Leibniz. He is particularly known in the discovery of differential calculus and its applications to astronomical problems and computations. Here, an equation. What do you mean by the differential equation? What is the basic formula for that? We start with the dy by dx. An equation involving one or more unknown functions and its derivatives with respect to one or more known functions is called a differential equation. The first one, x into dy by dx equal to t, is an example for ordinary differential equation, whereas x into dou z by dou x plus dou y into dou z by dou y minus z equal to 0 represents the partial differential equation. You know that partial means number of independent variables are more than the ordinary differential equation. Yes. Before this one, going to the biological system, what are the importance of differential equations here? Analysis has been the dominant branch of mathematics for 300 years, and the differential equation is the heart of analysis. This subject is the natural goal of elementary calculus and the most important part of mathematics for understanding the physical sciences. It is a truism that nothing is permanent except change, and the primary purpose of differential equations is to serve as a tool for the study of change in the physical world. A general book on the subject without reasonable account of its scientific applications would therefore be as futile and pointless as a treatise on eggs that did not mention the reproductive purpose. So, before discussing the mathematical model, we shall know about the biological systems. In biological systems, a vast area of it, in that I have to take only few things. When we think of biological systems, our minds may immediately wander to the Amazon rainforest, brimming with thousands of plants and animals that live with each other, compete with each other, and depend on each other. We might think of the incredible expanse of the Earth's oceans, of colorful fish swimming through coral reefs, nibbling on algae. 2-meter high African termite mound may come to mind, with the huge colonies of individuals that have their specific role and whose lives are controlled by an intricate social structure. Here, biological systems abound at all sizes of scales. Here, a termite in Namibia is visible evidence of a complex social system. The system is a part of larger ecological system, and it is at once the host to many systems at smaller scales. These examples are indeed beautiful manifestations of some of the fascinating systems nature has evolved. However, we don't have to look at that far to find biological systems. Much smaller systems are in our own bodies and even within our cells. Kidneys are waste disposal systems. Mitochondria are energy production systems. Ribosomes are intracellular mechanics or machines that make proteins from amino acids. Bacteria are amazingly complicated biological systems. Viruses interact with cells in a well-controlled, systematic way. In this, biological phenomena are often difficult to understand because our minds are trained to think linearly. Biological system often consists of large number of components, but they pose an additional formidable challenge to any analysis because the process that govern them are not linear. Consider a problem. Here is the problem. If an investment of $100 leads to a return of $120, to a return of, suppose we have to take in $1,000, which is to the return of $12,000. Biology is different. If we fertilize our roses with 1 tablespoon of fertilizer and the rose bushes produce 50 blossoms, a little bit more fertilizer what we are using may increase the number of blossoms, of course, but 100 tablespoons of fertilizer will not produce 5,000 blossoms, but almost certainly kills the plant. Which one gives the contradiction? So in biological, we must concentrate on that. Modeling in system biology is really a special way of looking at the world. Whether we just conceptualize situation in the form of components and interactions, or whether we actually set up equations and analyze them, we begin to see how complicated phenomena can be conceptually simplified and dissected into manageable submodels. We develop a feel for how such models might respond to change. Modeling may become life-changing adventure. That one becomes life-changing advances. Here, we are taking algorithm for modeling. Modeling is a mathematical and a computational endeavor that in some sense resembles in fine arts. Here, the left-hand side, we have taken that goals, inputs, and initial exploration. In goals, inputs, and initial exploration, we find that the scope of the model, the data availability, and other available informations also. The second thing, model selection. In model selection, we are concentrating on the structure of the model. Under that, explanatory versus correlative, or static versus dynamic, continuous versus discrete, deterministic versus stochastic, and other things also. The third one, model design. How should you design a model? In this one, diagram and list of components here based on the variables or parameters. Here, what are all the different types of variables we know? One is dependent and independent variables. The process and interactions, signals, process modulations, and other things. The next one is model analysis and diagnosis. In that, internal consistency or external consistency, reasonableness, stability, sensitivity, and structural. The last one, model use and applications. What are all the uses? You know, confirmation, validation of hypothesis, explanation of causes and effects, etc. Conclude that discovery of design principles. Here, before going to taking that, the first point is goals, input, and initial exploration. We are concentrating, arguing about the question of scale. The first four most important aspects of the exploration phase are the most appropriate scales for the model with respect to both time and space, and also with respect to the organization level. Scales in biology span several orders of magnitude in size and time. It is given like that. Here it is given that, which of course, human organs and ecosystems contain small molecules and genes, so that they really span multiple size and time scales, which makes multi-scale modeling challenging, fascinating, which is given in this figure, the graph. Next one is data availability. The quantity of available data provides important clues for exploring options of model selection and decision. If a completed model with many variables and parameters is supported only by very scarce data, the model may capture this data very nicely, but as soon as we try to apply it to a slightly different scenario, such as wider spacing of the trees or a richer fertilization regimen, the model predictions may become unreliable or inaccurate. Why, Chris? Numerical data are the gold standard for mathematical modeling. We should not scoff at qualitative data or information that contains fair amount of uncertainty. For instance, if you are told that experiment shows some outputs increasing over time, this piece of information can provide a valuable constraint that model must satisfy. Especially in a clinical setting, this type of qualitative and semi-qualitative quantitative information is prevalent, and more of it is available, the more any model of the phenomena is constrained. We'll see the model now one by one. Only few models we are going to discuss. Here, model selection, design, analysis, and structure by taking a very small example. For an example, consider an infectious disease such as tuberculosis or influenza that easily spreads throughout a human population. The purposes of studying a very complex phenomenon with as a simple model as possible. Let's suppose the following. The infectious disease is spread by human-to-human contact. Second point, although bacteria or viruses are the true vectors of the disease, we ignore them. Third one, individuals may acquire and lose immunity. Fourth point, the primary questions are how fast the disease progresses, whether it disappears without intervention due to immunity, and whether vaccination or quarantine would be effective. The last one, we do not intend to account for the spatial distribution of cases of infection throughout some geographical area. Here the case in dynamical model, in the case of the bacteria, the growth in volume may vary, often depends on how big the bacterium already is. The change in the volume, the figure it is given, represents the shape of the E. coli bacteria, resembles in the form of cylinder with caps. So the change in the volume over time is given in mathematical terminology as its time derivative, given by dV by dt. dV by dt is nothing but some function of volume V at a time t. The next model, the interviewing model of a blue sky catastrophe model. Here the system of two differential equations. What are they? One is dy by dt equal to y with the parameter t, with respect to the time t, and the second differential equation, dy by dt equal to x minus x cube minus 0.25y plus a into sin t. In this case, see, four figures are coming together, four different concepts given. In this equation, which appears to oscillate quite regularly about the baseline value given in A, where the second one, without any changes, the oscillations later becomes the irregular for the given in the figure B. Taking the initial value x naught equal to 0.9, y naught equal to 0.4, and a equal to 0.2645, we are getting this one. Suppose we are changing the values. very slight changes we have taken. A is equal to 0.265, X not equal to 0.9, and Y not equal to 0.4. We are getting numerical features may changes. The changes occurs in the figure C and A4. Next model, SIR model. For the infectious disease problem, consider a simple differential equation model called a SIR model, which is by its nature moderately explanatory, dynamic, continuous, deterministic, and independent of spatial aspects. More complicated choices could include random processes associated with the infection of susceptible individuals or age distributions with the population with different degrees of susceptibility and recovery. In this case, the differential equation is given as ds by dt, which is nothing but s dot, which is expressed in terms of the parameter and other things. I didn't give the full thing here, just I have taken the differential equation and show the model here. The next one is model for continuous dynamical systems. The linear differential equation of the type dx by dt, which is equal to x dot, which is equal to a into x, which describes an exponential growth or decay. The equation says that the change as expressed by the derivative on the left-hand side is directly proportional to the current size or amount of the quantity x with a proportionality constant a. If x and a are positive, the change is positive and x is continues to grow. If a is negative, x keeps decreasing. Now, we are discussing about the stochastic diapatic model. Past few years back, we have started in doing the diapatic mellitus model. In this case, we have assumed that already we discussed about in the biology, system biology itself, so many cases. Here we are concentrating on only one case, diapatic mellitus model. Let us know about what is the diapatic and the basic thing, how it is, how the organs of our body are infected, due to what reason. Diabetes is not merely a metabolic disease, but very much a vascular disease. Diabetes is a worldwide medical problem and is a significant cause of morbidity and mortality. It has considerable impact on both the patient and the society because it typically affects the individuals in their most productive years. Insulin is secreted by beta cells of the islets of Langerhans in pancreas. Islets are scattered throughout the pancreas. Insulin is secreted by the beta cells in response to small changes in glucose concentrations. Insulin is an important anabolic hormone with a profound control over carbohydrate, protein, as well as fat metabolism. Idiopathic destruction of insulin-producing beta cells in islets of Langerhans in the pancreas, resulting in inability to produce endogenous insulin, which is vital for control of blood glucose and other metabolic functions. Most of the patients have varying degrees of dual defects, beta cell dysfunction, and insulin resistance. Diabetics have inherited beta cell defect to which occurred dysfunction of beta cells due to infantil or malnutrition, and a transient dysfunction due to toxic effect of severe hyperglycemia can be super added. Due to beta cell dysfunction leading to insufficient insulin secretion and gradually diminishing over all insulin secretion and leads the organ damages. Hyperglycemia is a major causal link between diabetes and complications. The impact of diabetes on both the health of individuals and the healthcare system resides almost entirely in the long-term complications of diabetes, affecting almost every system in the body, including eyes, heart, feet, and nerves. In this model, we have taken organ failure, prophylactic treatment, discussing about the diabetic mellitus model. The general assumptions of the model studied are given below. Assuming that a person becomes diabetic at the end of a random length of time u with a cumulative damage function f. He is exposed to several risks and the damage processed to his organs before becoming diabetic due to stress and strain or due to his habits. The damages occur to his organs in accordance with a general renewal process with the interoccurrence cumulative damage function G. When the damage caused to his organs exceeds a threshold Y, he is taken for hospitalization. The threshold Y has a discrete distribution with the probability of Y equal to K equal to P suffix K for all K greater than 0, which is the probability of organ failure on the kth damage, and summation P suffix K varies from 1 to infinity equal to 1. The random variable B is the time at which the threshold exceeded for the first time. Third point, third assumption, he is sent for prophylactic treatment to avoid diabetes after a time W, which has exponential distribution with the parameter A. Initially at time 0, he is normal, that is in good condition, don't want to take any medicine, anything at all, he is good, quite good. All his organs are working good. His organs are free from damages. He is sent for hospitalization when either he becomes diabetic or damage caused to his organ exceeds the threshold or prophylactic treatment is required. Fifth point, during hospitalization, he is treated for diabetes if he is so. He is given prophylactic treatment if admitted for the same. All damages to his organs are treated one by one. Treatment time for diabetes, the damages caused by prophylactic treatment are independent with the distinct distributions represented by R suffix D, treatment for diabetes, general distribution R, and a prophylactic distribution for R suffix P. In this model, the cumulative damage function F is Erlang 2. We are assuming that the distribution function is Erlang. The function G is general. Erlang, the parameter is taken to be as lambda. Hospitalization for the person starts at the time T, where only when means minimum of U, V, W. At time V has exceeded the threshold level Y of the organ. When T equal to W, the person is sent for prophylactic treatment. Let N be the number of damages occurred during the time before treatment, and R be the individual treatment time. R suffix D and R suffix P are the treatment times for diabetes as well as the prophylactic treatment respectively. Then the total treatment time is represented in terms of A cap. It is taken as the equation. First one with the treatment for diabetic, in addition with the cumulative damages occurs in the organ, or cumulative damages only taken place, or for cumulative damages along with the prophylactic treatment. These three cases are possible. So should you writing that equation means we have taken one equation in the probability when the person is admitted for diabetes or organ damages or prophylactic treatment respectively, the cumulative damage function F1 of T of V is calculated. We are taking that F1 of T is taken to be as probability of V is less than or equal to T, which is taken in terms of summation as well as in continuous case also. After this, we are taking to find the solutions by using partial differential equations to find the expected time to treatment and the time to hospitalization. After that, we calculated the variance, joint distribution, and find the solution to this diabetic mellitus model. Okay. Yes. I have referred these two books, Men of Mathematics and with the first course in system biology. Okay. Is it audible?
Yes, madam, we can hear you.
Okay, thank you, sir.
If anyone has any questions, I'm sure ma'am would be pleased to answer them. Participants can either unmute your audio, or if you're streaming the video in YouTube, kindly post your questions in the comment section.
I think there is no more question. Nobody is asking question.
Yes, sir. Thank you, ma'am, for enlightening us with such an innovative topic. Thank you very much.
Okay. Even though there are so many other models, due to time constraint, I restricted to the selected models. What has been discussed in this presentation only, madam.
Yes, ma'am.
Okay.
It has been a very innovative session. Thank you very much.
My special thanks to Dr. Raghavan, Head of the Department of Mathematics, Sri Vidya Mandir, Arts and Science College, Dr. Mayama Joseph, Head of the Department of Christ Deemed University, Bangalore, and Head of the Department of Mathematics, Jyoti Engineering College, Thrissur. Thank you, one and all, madam.
Zoom link type in it. Yes, ma'am. Thank you, ma'am.
Yes.
For your valuable presentation, ma'am.
Sir, Jackma, sir.
Ma'am.
Okay, sir.
Thank you so much, madam.
Thank you, sir. Thank you. Shall I leave?
Okay, ma'am.
Okay, thank you.
For the next session, Richa, it's
Again,
over to
so
you.
we'll start the next session, sir, because still 10 minutes is there.
So wait, sir. He's on the line, sir. We'll come within 5 minutes, sir.
That's what 12 o'clock only it starts.
Yes,
We'll
yes,
start at 12. Okay.
Yes, sir. Within 5 minutes, we'll join, sir.
Yeah. And so we'll wait for some time.
Yes, sir. It's over to Richa now, sir.
Yeah.
Yes.
Okay, sir. We'll wait.
Sir.
Yeah. Hello, sir. Sir, it is audible.
This is audible, sir.
Yeah, it's audible.
Okay. Okay. Thank you, sir. Thank you, sir. Okay, sir.
Is sir joined, sir?
Yeah, I joined, sir. Okay, sir.
So we'll start the session.
Yeah, we can start, sir. No problem. We will start.
Okay, Richa, can you start the session?
Sir, Dr.
Okay.
Hakim has joined.
Hmm?
Dr. Abdul Hakim has joined.
Yes, ma'am. Join, ma'am.
Yes, he is joined.
Okay, fine.
Because the name is showing different here, that is why we are got confused.
I think it's in my daughter's name. I think.
Yeah,
so.
no problem, no problem, sir. Okay.
I forgot to change that. Okay.
Okay. Good afternoon to one and all present here. I'm Richa Shaha. I'm a PhD scholar of the Department of Mathematics, Christ deemed to be University. And I'm truly honored to introduce our next guest speaker, Dr. A.K. Abdul Hakim. Dr. Hakim is a celebrated researcher in the field of fluid mechanics. He obtained his doctoral degree in the year 2008 from Bharatiya University, Coimbatore. Dr. Hakim's areas of expertise include differential equations, partial differential equations, computational fluid dynamics, heat and mass transfer, and flow through porous media, to name a few. He currently works as an assistant professor in the Department of Mathematics at Sri Ramakrishna Mission Vidyalaya College of Arts and Science, Coimbatore. He has more than 12 years of teaching experience at both the undergraduate and postgraduate levels. Under his supervision, 18 students have been awarded their MPhil degrees and 3 students have been awarded their PhD degrees. Dr. Hakim has been invited to deliver lectures in conferences and workshops in notable institutions all over the country. He has more than 50 national and international research publications to his credit. He is currently also a reviewer for several reputed international journals, some of which include the Journal of Applied Fluid Mechanics and the Journal of Molecular Liquids. Without further ado, please join me in welcoming Dr. Hakim for the next talk. Over to you, sir.
Okay, thank you, ma'am. My PowerPoint is visible, ma'am?
Yes, it is.
Yes, it is only. Okay, ma'am. Okay, shall I start my things?
Yeah, yes, please go ahead.
Yes,
okay,
sir, start.
Okay, thank you, sir. Thank you, sir. Very good. Very good morning to one and all present here. First, I would like to thank the organizers who gave me this opportunity to share my knowledge on introduction to computation fluid dynamics. So my topic is very much for those who are doing the research. Basically, I'm going to give those who want to do the research in computation fluid dynamics. The lecture will be very useful. Okay, before going to start my things, this is my plan of presentation. I want to tell the relevance of fluid dynamics in our life. Then I'm I will just give some brief idea about the basics of fluid dynamics. Then some of the problems involving the heat transfer in cavity. If time permits me, I will discuss more in boundary layer flow problem also. So before going to my talk, just I want to ask, what is the purpose of doing research, especially in mathematics? Means just if you ask these questions, means only one things we come in our mind. The first one is, suppose in a human, as a human, we need something. Physically we need something, and biologically also we need something. Physical needs means nothing but the basic shelters or basic clothes, like that wise. Biological means water and food are our biological need to live in this world. Psychologically we need some families and friends. Okay, so wants is entirely different from needs. So what is meant by wants means the same category in the physical needs also. We need shelter, but here we need the nice house, nice dress, like that wise. Biologically nowadays we are want only the organic foods, organic fruits, like that wise. So biological need, biological wants. So psychological wants also, nowadays we are talking due to this quarantine period also, we are conducting these seminars, like using some Zoom was like that webinars. So this is our wants. To fulfill the needs and the wants, the STEMs, these are the scientists and technologists and engineers and mathematics are played together to fulfill the gap between the needs and the wants. Okay, so in the scientist, in the technologists and engineers are using that mathematical models So that is very, very important, because the scientists and technologists or engineers are using our mathematical model to develop their new ideas or new things before implemented into our physical phenomena. So if any things occur, means what they will do means they will convert that physical concept or physical problem into our mathematical models. Mathematical model means it will come under differential equations or partial differential equations. That model can be interpreted, that can be solved using our mathematical idea. They will get some more, they will get some ideas. After getting that ideas only, they will interpret it in our daily life. So these are the things to fulfill our needs and the want, and that things the mathematical play a vital role. So that's why the mathematics is called as the language of science also, because using that mathematics only all the science are developing. So mathematics have many real world problems, so many problems in and around us. Mathematics is there. So here in our mathematics we are classified into pure and applied mathematics. So now I am going to talk about only by the applied mathematics, because our fluid dynamics is coming under the applied mathematics only. So in that fluid dynamics, merely we are using that partial differential equations only, the partial differential equations. So now I am going to my topic, that is our fluid dynamics. It is one of the applied mathematics. So before going to my topic, I want to tell what are the relevance of fluid dynamics in our life, because we are telling that where we are using the fluid dynamics in our life. The first one is, all of you are all of you know about that. If you want to live in this world, what we need air, the very, very must thing. The second one is water. So air and water are our natural fluids. So somebody, if you ask anybody, means all will think about that. So how you will tell that air is a fluid? So I will explain you later how the air. All of you think, if you ask a normal person, means what they will think means, so fluid means liquids only, we will tell it is a fluid. So it is not like that, right? Air is also a fluid. I will explain in the basics in the next things. I will explain while coming to the basic concepts of fluid dynamics. I will explain that things. Okay. So all our living beings on the earth are sustaining by breathing air and drinking the water. So these are the if you think about our human body, so it is working under the fluid dynamics ideas only. Without fluid dynamics idea, our body cannot be function. For example, if you take all of you know about the heart is pumping, and it allows our pure blood throughout our body system. After that, deorganized bodies after coming to a heart, and it will be due to the pumping only, the blood is circulating through our body. If you think about that, only in our human body means only the 7 to 8 liters of blood will be there. But how many nerves are there means it is around 1 lakh miles of nerves are in our body. So due to that pumping only, due to that pumping pressure change, so that the whole the 7 liters of blood is flowing throughout our body. So this is one of the ideas of our fluid dynamics in our body. Now if you take our lungs, so in lungs what we are doing is just we are breathing air in our inhaling of air containing the oxygen, and it will it will go to the bloodstream, and after getting deoxygenating, and the waste, that carbon dioxide is coming out. So this is also a ideas of our fluid dynamics in our body. So now our waste things are extracted through our kidneys. The kidneys is the best examples of porous media. So this is also a example, the relevance of fluid dynamics in our body itself. Now if you think about in and around us, we are surrounded by all the things are by based on the fluid dynamics principle only. So engineers, if you are sitting in the home, you are using the fans. If you go to the office, we are using, suppose you are traveling, you are using the buses. On each and everything, some fluid dynamics concept will be there. Okay. So like that way we can tell the relevance of fluid dynamics in our day-to-day life. So many examples we can give like this wise. Okay, so now I am going to tell the basics ideas about fluid dynamics. So already I told that air is also a fluid, liquids also a fluid. So how you can tell that air and liquids are fluid? So now I am going to give the definition before going to the some substance. So what is meant by matter? So you want to discuss. I am going gradually. So what is meant by matter means the matter is made up of atoms and molecules. All of you know about that atoms is a single element. The molecules are more than one element, more than one type of elements. So matter is a tiny particles. Okay, so the states, so matters are classified. Generally it is classified into three things. The first one is solids and liquids and gaseous. So what is meant by solid means the solid also a tightly packed molecules. Okay, it has a regular space. The coherent force between the two particles will be high, so it won't be move here and there. There is no more movement will be in that particle itself. But if you comparing with the solid to liquid, it is not a closely packed. It is not regularly. There is no regular arrangement in the liquid, so there will be some distance between the two particles will be there. Otherwise, if you tell me the coherent force is very less, so the particle can move here and there without any disturbance also, without any external force, it can be move here and there. So that we will tell it is a liquid. So if you come to the gases, the gases is entirely different, because in that there is no regular arrangement in the particles. So the coherent force is very less. So it can be moved here and there. So now you can see that the liquid in the particles in the liquids and gas are capable to move without any external force. So now if you come to what is meant by fluid means, okay, now if you come to the substance which is capable of flow is called fluid. So as per the definition of the liquid and the gas, so it is a substance which can move with which is a substance which is capable of flow. So that's why we are telling that the air also a fluid, that the liquids also a fluid. So if you think about the air, so we will tell that is a compressible, incompressible. I will come you later. Okay. So what is meant by dynamics? The dynamics is nothing but the study of motion of a fluid, of any particle is called dynamics. So in fluid dynamics is a science which deal with the study of motion of the fluids. So that is the thing. So that is the definition of the word fluid dynamics. So now I already told that the air is also a fluid, and water liquids also a fluid. So further it is classified into compressible fluid and incompressible fluid. So what is meant by compressible fluid means? For example, incompressible fluid. So just I'm going to give one example for both the case. Suppose you are taking the 1 liter water can, just you can fill only the 1 liter capacity only, because its capacity is 1 liter. Suppose if you pour a liquid or water or anything in the form of liquid, it will take only the 1 liter. If you allow more means what will happen means it will go outside only. Suppose if you give also pressure also, the water will come outside that bottle. So that is happening. So that is incompressible because the density is constant there. So if you come to the incompressible, see, compressible means, suppose if you are taking one balloon, so its capacity is 1 volume, 1 kg. So suppose if you are giving more than that capacity, so it will allow, because the air can be changed the density. So that is called compressible. Okay, so the air is a compressible fluid, so liquids are the incompressible fluid. So that is the thing due to that properties. So dynamics. So dynamics also is nothing but the flow, to study the motion. In that motion we are generally, I'm not talking about only generally we are talking about the steady flow and unsteady flow. In that unsteady flow means that velocity is not depend on the time. So it is there. If the velocity depend on the time, means we will tell it is a steady flow, like that way. So now I told what is meant by fluid. The substance which is capable of flow. On that things, I explained that here also the compressible. Another one is the incompressible fluids. So in that flow is nothing but the steady or unsteady. Because the fluids have some of the properties. If each and every man is there, means there will be some characters will be there. Suppose I am there, means for me some inbuilt characters will be there in your born or due to my surroundings. There will be some inbuilt characters will be there. Suppose some persons will be always helping to others. So this is the characteristics of that person. So like that wise, the fluid is also having some characteristic functions. That characteristic functions will also disturb the flow in quite nature. So I'm going to explain that. So in that very important thing is viscosity. For example, if you take a water and if you pour it on the floor, what will happen? It will move some distance without anything. Just if you pour, it will go some distance and it will be stable. After that, it will be stable. Take a oil. Just if you pour, suppose you take a coconut oil, just you pour. So it will also go some distance. When comparing to that water, that coconut oil will go less distance. So if you take some more, so take honey and just if pour, it won't go much distance when comparing to those things because of that viscosity. So viscosity is nothing but stickiness properties. Because viscosity is nothing but stickiness property. In Tamil, we'll tell pisipithanmai, like that way. In castor oil or crude oil, it will have more viscosity. So that viscosity itself barrier for flow. So that is the main thing will be that. So that is the viscous. So in viscous means there is no viscosity. The fluid, the viscosity of fluid is very, very less. So now we are coming to the definition of the real fluid. What is meant by, so fluid already I told that a matter or which a capable of flow. So like that way, a compressible means if the pressure change, bringing density changes. So gas we will tell is compressible fluid. The liquid means nothing but the incompressible fluid. So viscous means a flow is said to be viscous if both the normal and the shearing stress exists. Viscosity means both the normal and shearing stress will be exists. Inviscid flow means a flow is said to be inviscid when it does not accept the shearing stress. I will explain what is meant by shearing, what is meant by in the next slide. Okay. So now you can come for the definition of the real fluid. So real fluid means you can see it is a compressible fluid with it have that viscosity. Then it will say it is a real fluid. So you can see the definition. Yeah, fluid which is compressible has a viscosity and surface tension is known as real fluid. Suppose it is a fluid, it is a incompressible and it has a inviscid. There is no viscosity means then we will say it is a ideal fluid. So these are the like this way we are classified that liquids depend upon the properties. How we are telling the man and the humans are differentiate with but the inbuilt characters. Like that way in fluid also some due to that inbuilt characters we are classified some into some classifications will be there. So now if you come to the stress. So what is meant by stress means? The stress is a restoring force per unit area inside a body is called stress. So stress means inside a body. For example, I am here. My friend is always disturbing me. So what will happen? Inside my body, the stress will come. If the stress is high means, what will happen? Suppose the heart attack, so many things. So that's why we want to reduce our stress. Then only we can live long. We can avoid heart attack like that ways. So which are the restoring force which is inside our body? We are telling the stress. No, same ways in the fluid also, the stress is a restoring force per setup in the inside your body is called stress. So stress is nothing but the deforming force by area, that is F by A. So strain, the strain is not like that. Strain is a deforming per unit area of the original length. For example, you are standing here, your friend is coming, you're running and coming, and you're pushing in your backside. After just you pushing, what you will do? You will go front and you will come back. It will come to the original position. So that is called strain. Okay. Okay, you can see here the normal stress means like this way. The force is applied parallel to, you can see the here. So stress means, you can see stress means just you got the force is going in the way which is parallel to our not parallel. So you can see the stretching force is a force per unit area according parallel to a infinite surface element. The shearing stress is caused by the friction between the fluid particle due to the fluid viscosity. So strain is defining here the ratio of the distance deforming to the height. So that is called stress and strain. Shearing stress or shearing strain. So I already told that the viscosity is the more important properties which will affect the fluid flow. So low viscosity of fluid will flow more when you comparing to the high viscous fluid. So second important property, in that viscosity is classified into two things. The first one is called dynamic viscosity, another one is called kinematic viscosity is that. So what is meant by dynamic viscosity means when the viscosity of the fluid is studied with respect to force. The force means it will call as a dynamic viscosity. It is denoted by mu. But kinematic viscosity is not like that wise. The kinematic viscosity is studied with respect to the motion of the fluid. It's not depend on the force. It will represent the motion of the fluid is called kinematic viscosity. So that is dependent. That is denoted by mu. Nu. This is mu. This is nu. So these are the some properties. After that, we are classified that generally we are classified that fluid into Newtonian fluid and non-Newtonian fluid. So what is meant by Newtonian fluid? What is meant non-Newtonian fluid? Generally, if I tell to generally without any definition, if I tell me just you take a drop of water in your hand, what will happen? It will drop quickly. Just if you show me it quickly, it will drop into the floor or ground because it is obeying the Newton's law of gravity. So that we will say it is a Newton's fluid. Non-Newtonian fluid, suppose you take the honey or paste, you take a drop, means it won't fall down quickly. It will take some time. Otherwise, suppose if you take the paste, that is also a fluid, but it won't be fall down to the ground. There will be no. So that it does not obey the Newton's law of gravity. So that we will tell it is a non-Newtonian fluid in generally. So now if you come to the definition, must be a real fluid in which the shearing stress is directly proportional to the rate of shearing strain is called Newtonian fluid. So this is a definition of Newtonian fluid. The shearing stress is directly proportional to shearing strain. But here it is not. It is not proportional to the rate of shearing strain. So that is called non-Newtonian fluid. Example, you can see that water, air, ethyl glycol, water, oil, and etc. are the Newtonian fluid. But non-Newtonian fluid means blood, gel, fluid in a food industry, polymers, and etc. are the examples of non-Newtonian fluid. fluid in the food industry means that we can tell that sauce like that is a tomato sauce that are not only fluid. So these are the fluids used before that. Nowadays, the fluids are to the fluids. In that fluid, we want to increase the thermal conductivity of the fluid. If the thermal conductivity of the fluid is increased, means what will happen? The heat transfer rate will be enhanced. For that purpose only, I'm not going to give full idea about the nanofluids and all. Just I'm going to give some basics ideas of the fluids, then nanofluids and hybrid. Then I will go to my how we can do the research by using the computational fluid dynamics like that, guys. Okay, you can see that nanofluid. So already the base fluid is there. In that base fluid, to enhance the thermal conductivity of that base fluid, just we are adding some nanoparticles. It is not a natural fluid. It was first coined by the Choi in 1995. So what will happen? It will enhance some energy more than the base fluid. For example, if you are thirsty, means for example if you are going for running, suppose you are thirsty. If you drink water, you will get some energy. Suppose if you drink some glucose water, so take water and mix some glucose, and if you drink, you will get instant energy. So that glucose water is nothing but our nanofluid. This is the best example. To get the instant energy, so you are using some glucose in our ordinary water. So ordinary water, we will tell it is a base fluid. So we are adding some glucose particles, so that we will get a nanoparticle. So if you make stir and if you prepare that is called nanofluids. So it is not a natural fluid. I already told that. What will happen here means the solid plus liquid. All of you know about that in the solid, the conduction will be taking part. In the liquid, the convection only taking part to transfer the energy. So it will give the nanofluid, that is advanced heat transfer. So that's all. So examples, if you say means in mechanical engineering, they are using car, we are using in engine oils, we are using the nowadays the nano engine oils are there. So what will happen? It will enhance the fuel savings up to 21%. So this is the examples of nanofluids. So for nowadays, in recent decades, now the hybrid nanofluids also there. What is my hybrid nanofluid? In the base fluid, just we are adding one molecule, one particle, so that we will tell nanofluids. If you add more than one or two particles, so that we will say it is a hybrid nanofluid. It will give more effective than compared to the nanofluids. So that's why the research, now the research are going like that way. For example, suppose if you had spicy items, for example, if you had biryani for lunch, so you want to digest quickly. If you take water, hot water, it will help to digest your food. Suppose if you are taking some lemon juice with salt, suppose you are taking lemon juice with sweet, some person will take the lemon soda or lemon with sweet and salt. So it will give more effect than comparing to either by the salt or sweet. So that is nothing but our hybrid nanofluid. So I'm telling that we are using in day-to-day life example I'm telling. So hybrid nanofluid nothing but our salt and sweet lime juice, like that way we can tell. For that, and that if you are doing the research in that, the properties will, now I am coming to the thing, the properties of the liquid will be changed because the density can be compared. You can see that rho NF. Here rho NF means nanofluids. Here you can see that rho f is there. The rho f is nothing but okay, sorry. So rho f is the density of the fluid plus solid, so it will become nanofluid. But here you can see here 5 1, 5 2s are there. The 5 1 represents the properties of nanoparticle, the first one. The 5 2 is nothing but the properties second one. So here you can see S1 and S2. That is the particle S1 and S2. So it will combine become hybrid nanofluid. So nowadays the research are going like that. In those days in 90s, we are doing the research in only the fluids. So that is ordinary fluid like that way. But in the 20s and now recently, if you take the 10 decades, we are doing that nanofluid. Now at recently, the research are going in hybrid nanofluids. It will have more efficient than the ordinary or nano or like that way. For example, if you see the advertisement for paint, ICN paint like that way. Nowadays, they are using some nanoparticles. So that's why they are telling that in the paints we are giving that germ skill products are there. How it is developed means because of our research we are doing in nanofluids and the hybrid nanofluids. Using that idea only, the engineers are taking that idea and they are doing their products. Because the mathematical research will give some basics ideas, not only the fluid dynamics, each and every research, fuzzy also, each and everything, not only I'm not about each and every ideas give the abstract idea about that real world problem. Using that idea, the engineers will take that things and they can implement it into our day-to-day life. So that's why we are doing the research. So now you can come into the fluid dynamics. If you want to do the fluid dynamics research means, in that fluid dynamics research, we are mainly categorized into three things: experimental fluid dynamics, mathematical fluid dynamics, and computational fluid dynamics. So what is the experimental fluid dynamics mix? Suppose we are doing the research in experimentally. So we'll tell that, for example, if you want to do the research in cavity problems, we are make the cavity. After that, we will pour some nanofluids or like that way. So yeah, experimental means it is a realistics only. It will take more time. It will the expense will be more. When suppose if you what are the default means, that the demerits means, suppose if you are doing some particular experiment in particular parameter means, suppose you want to change that parameter. For example, you are taking square cavity. Suppose if you want to do in rectangle cavity, we want to model another things. So it will be time also more, the expense also more. So that's why if you are coming to mathematical fluid dynamics. So mathematical fluid dynamics is nothing but analytical fluid dynamics. Analytically, if you solve, because the fluid dynamics, each and every problem, each and every equations are in partial differential equations only. So the governing equations I'm telling about. So, suppose you want to solve exact analytical solution means. So sir, there will be some restriction will be there. Suppose it is non-linear things we can't solve directly by analytically. Suppose we want to approach some approximation or numerical techniques to solve them. So that is called mathematical fluid dynamics. Another one is called the computational fluid dynamics. In that computational fluid dynamics, it is a low cost and high speed using that computation, using computer we are doing. That computer means we are not doing in computer. In that some softwares are there. Using that software, we can design our own problem. We can solve. We already there each and everything that is a scheme, codes, all are inbuilt in that software itself. Using that software, we can solve our problems. So that is the benefit. That is the things in computational fluid dynamics. For example, fluid software is there. If you want to draw some diagrams, then you can generate the, you can split the geometry into some meshes. That meshes may be in either triangle or any shape you can able to meshes. After that, you can go for fluid. Then already the inbuilt every method is in the fluid, finite volume method, finite element method, each and everything is, if you click that means you will get answer. So in that fluid, in the computation fluid dynamics means we can do for any irregular geometry also, any complex geometry also. But in experimental we can't do, and mathematically we can't solve that. So some restriction will be there. So these are the advantages of the computational fluid dynamics. Suppose if you want to do anything, means within a fraction of a second, you can change the geometry, you can change parameters, and you will get the answers within using our mathematical softwares. MATLAB also you can use. So that is the computational, doing the research in computational fluid dynamics. So methodology used to solve the problem means, all of you know about the governing equations of the fluid dynamics. Normally we will use that continuity equation, momentum equation, and energy equation. So that is Navier-Stokes equation. I will show that things very briefly. So these are the problem. Governing equation problems are continuity equation, that is the momentum equation, and energy equation. The governing equations are nonlinear partial differential equation with some suitable boundary conditions. Because it is a nonlinear things, we can't get answer. So we were using some scalar transformation, because the units are not will be not unique here, not same. So using the, if you use the scalar transformation, that will be converted into a non-dimensional. So non-dimensional means the unit of the all the parameters will be same. So that's why. So non-linear, non-dimensional equations, so that can be solved either by the analytical or by numerically. So analytical means that is mathematical fluid dynamics. So analytically, if you want to solve the problem means you can use Human's function, hypergeometric function, then HAM, homotropic analysis method, spectral collocation method. So many methods are there. In numerically means RK method, finite difference method, finite volume, finite element. Suppose we want to familiar in that method for numerically means, when we are doing a PhD, suppose I did my PhD in cavity, on that time I wrote my code using Fortran for solving one problem. If the code, the length of that code will be 10 to 12 pages. We can run that program means it will take 8 to 10 hours to get one output. One day we want to, if I run that problem for single parameter, it will take 10 hours. But nowadays it is not like that way. Nowadays the workstations are there. So you want to know the finite element or finite volume or finite difference method. So many methods are there. But if you go to the computational fluid dynamics using some software, so everything is inbuilt. So no need bother about that codings and all. You want to focus only on the geometry. Either it may be a complex or any irregular geometry. After getting the geometry, you want to fix that into the some meshes. Then you can choose your own solution like that, a finite element or finite volume, like that. So this is the general methodology used to our fluid dynamics problem. So I already told that the three very the time is running, so I just skip the things. Okay. Continuity equation, this Navier-Stokes equations, Navier-Stokes equation, that is a momentum equation we will tell. Using this equation, what is our aim means, we are going to find the, you can see that dou u by dou t, that is change in velocity. Velocity can be find. What is the velocity of that fluid? Is find using that momentum equation. So I'm not explaining this. Okay, the present embodied. So energy equation means continuity equation, momentum equation. Energy equation means how the energies are transformed. So that can be studied using this energy equation. What is the velocity of the fluid? How the energy is transformed. These two are studied using that momentum and energy equation. The continuity equation is used to verify our velocity. That means the momentum, in that momentum equation we are finding velocity. If you substitute that velocity into in that continuity, if it's satisfied, means our velocity of the fluid is correct, like that is for verification purpose we are using. Now you can see that first model, that convection in a cavity. So all of you know about the conduction, convection, radiation. Just I'm going to briefly. So conduction means the heat energy is transformed by the, not the motion of the particle, by the energy is transformed by the particle to particle is called conduction. The convection means the energy transformed by the motion of the particle. Now I'm going to explain one simplest problem in cavity. Okay, so natural convection in a square cavity in the presence of heated plates. So just the things. So you can think that this is our physical geometry of our problem. So this is a first, for example, in a, this is our cavity problem. Two problems are there, left hand side, right hand side. So what is our problem? Main agenda of our problem is, this is a heated plate which is keeping horizontal and vertical position. Here the horizontal position is there. Oh, sorry. Vertically it is keeping here. Which is the best position? For example, in the computer CPU, suppose if you are keeping some chips either by the vertical position or horizontal position, so which will cool quickly, because if you cool quickly only, the strength of the equipment will be high. Suppose if you are using laptop or thing, suppose it is heated, so it want to gradually, we want to reduce that heat. The sudden, if you want to suddenly, if you reduce that heat, means it will damage something. For example, suppose if you are pouring the things, what will happen? The computer will be failed. It will be some if you suppose pour some water, what will happen? It will be burst. That's all. So it won't be gradually. That we will tell naturally. It want to be cool. For that, you inside that computer or inside that CPU, which position? Either we want to keep that the chips in the horizontal or vertical. So that is the main motive of this study. We did mathematically using the computational fluid dynamics. So here our things, here the four walls are there. The top wall and the bottom wall adiabatic, and the right wall and the left wall will be the cold walls. So here only the heating is the plate which is keeping the center of the cavity. This in the first thing it is a vertical position. In the second figure you can see it is kept in the horizontal position. The height of the length of the rod is half of the cavity we are taking. It is a square cavity only. So this is the first equation represents the momentum equation, and the second one is the energy equation. The stream functions are taking here, velocity function. So here u and v are the two velocity function. to reduce the velocity, because reduce the two unknowns, we are using that psi, that is the stream function. What is the purpose of stream function is to reduce the unknown. So these are the non-dimensional governing equation. So that governing equations are non-dimensional using some the parameters which are given in x is equal to like that, right? After non-dimensional, this is the boundary conditions. So methodology we used here, we use the methodology using ADI, that means a finite difference method with alternate direct implicit method with SOR technique for convergent criteria. So whenever we do the research, we want to compare our result with the previous one, so that we will tell it is a benchmark solution. If you want to publish a good paper in the good journal, means they will ask whether you did the benchmark solution or not. So that is nothing but validation. Validation, we will tell it is a benchmark solution. So now you can see here, the plate is kept horizontal. In the left hand side, it is the isotherms. In the right hand side, it is a stream function. What is the purpose of isotherms? Means isotherms itself, how the velocity is moving on the cavity. The stream function is the position. How the hello, it is hearable? Hello, sir?
Yes, sir, you're audible. Please continue.
Okay, thank you, ma'am. I think some. So just I'm taking the thin plate located horizontally in the horizontal position only. We are did result with just we are that already I told that the plate is keeping half of the cavity. Suppose if we are increasing, so increasing the grasshopper number. So what will happen means if you increase the grasshopper number, the convection is very high. That heat transfer is increasing. So after that, we are kept that the length of that plate into the 1/4 of the cavity length. That is half of that previous one. So we kept that in the 3/4 half of the cavity and 1/4 the 3 region. So what will have the heat transfer rate? Finally, you can see, just I'm going to explain that things. You can see here, suppose I am here, normally if I ask anybody means what we will think means horizontal, if you keep that plate in the horizontal position, like this way, that means horizontal position only, the heat transfer will be high, all will tell like that way. But it is not true. Because if you did that experiment means what will happen means that if you keep that, this is the heat transfer rate using that Nusselt number, we find that. So if the horizontal plate means the heat transfer is very low, if you keep the vertical only, the position will be vertical only, the heat transfer rate will be high. So we find that result. So what is the reason means? Suppose if you are keeping that the plate in the horizontal position, you can see here, the plate itself varies the flow in that cavity. Suppose if you are keeping that the heat chips in a horizontal position in your CPU means, because due to the hot air will be go up, then the cold air will be the come down. So that is the buoyancy force. So the plate itself acts as a barrier to flow the hot air into the up to go to the top of the top of that cavity. It will act as a barrier. So that's why if you keep the horizontal position means the heat transfer rate will be low. If you keep that in the vertical portion, vertical like this way means because the anterior cavity will be in the active region. We will tell it is an active region. But if you pick the horizontal means only the half of the top of the cavity. So that's why you can see that in the top of the cavity only the active cells are here. When here it is not like that because the conduction is formed here. But if you comparing this with in the vertical position with the whole cavity will be in active position. So we gave conclusion that the vertical position is better to keep the chips. It will be very, if you want to cool means quickly means, so it is the position. So same thing we did in placed in the heater buffers in 2 plates. Same the continuity equation, momentum equation, energy equations, that and all the dimensional. So they're using the non-dimensional form. We are getting the non-dimensional equations. The heat transfers are analyzed using the Nusselt number. ITBC means isothermal boundary condition, isoflux boundary condition. Isothermal boundary condition means in the region the temperature will be constant. But isoflux means in the same region the temperature is not constant. So we will tell it is isoflux boundary condition like that way. So we are using the two-step method. Here we use it to solve this. So finite difference. Otherwise, you can use the finite element method also, finite volume method also to solve all this problem. I used finite difference method. So time is running. So these are same problem we did for then. So now I'm coming for CFD. Because so what is so that we did program. After that program also we went for some software to plot the graph. We run that program using Fortran or C++ also you can use. So that is the computational only. Using that computational, we solve the analytically, and our final equations are converted into mathematical. Using that mathematical program, we will get some data. After getting that data, we are go to the another software. We are running that program in C++ or Fortran. After getting the data, we are going for to plot the graph. We are going for Anthem or Origin, like that word software. On that software, we can plot that contour graph like that way. We will get some. That is the result. But if you come to the computational fluid dynamics, each and everything is inbuilt computational. So this is research problem in my CFD software. So this is as the same study. You can see. So here also you can see that cylindrical shape is there. Suppose if you want to in computational fluid, I already told that you can do the research for irregular shape also, complex geometry also. So that's why in the cavity, see in that cylindrical, the curve like that which we are taking. So this is the governing equation. Okay, in that you can see that using that software you can get like this way results. So this is used by computation software using by Fluent. Using the Fluent, we are getting the result. Same problem only. So just you can see, I will explain this problem. Okay, schematic general in our blood flow problem only. Just we are taking the complex boundary. So that first I told that complex boundary can be converted into meshing. So these are the meshing. In the boundary we can use in that center of the center of the cavity. They are using some meshes. Here they are using the triangle mesh. Here they are using a square mesh, rectangle mesh. That is depend on the us only. So 70% of the tensor RI of the triangle face are the tetrahedron mesh also. That is after meshing. This is our problem. This is our flow geometry that can be measured in using measured here. After that, using our Fluent software, we will get some results. Suppose we are considering that flow in that geometry, it will ask whether you are taking that fluid is a non-Newtonian or Newtonian like that way. So you can click means it will the governing equation will be occur. After that governing equation, it will ask how to solve using which method, the finite element or finite volume like that way. So if you click that means the finite volume, whichever that is user defined only, whichever the things you need, you can take. So after that, if you click means you want to give all the parameters values. So you will get the results like this way. So you can see that if the length here is increasing, what will happen within the single program, we can able to adjust the parameters like that way. if you are doing in the computational fluid dynamics. But in there means you want to change the program like that way, because we can, if you reduce the length of this by the geometry, by the giving that the radius here means, if you reduce the length means you will get the idea very quickly. So you can see 50% of the blockage, 75% of the blockage, 90%. In the what is this main problem is, in our blood vessels, suppose the blockage is there means what will happen? Suppose the blockage is 50% means, suppose the blockage is 70% means, suppose the blockage is 90% means, what will happen means, suppose it is a 90% means, here the velocity of the fluid, that pressure will be very high when comparing to the, sorry, when comparing to the 70% of a blockage in our blood flow. Suppose it is a 50% blockage means more or less equal only. The velocity and the pressure will be more or less equal only here. So that can be using our our things, our results. The doctors are used to tell what they will make. Suppose the blockage rate is very slow, only we can cure this blockage using some medicines like that way. Suppose the blockage is more high means, what they will tell, so you want to do for some open heart surgery like that way. So how they are doing is using our mathematical models only. The main doctors and medicals are getting some ideas, and they are, after that they are proceeding. So like that wise we can do. These are the some problem, because I want to finish 12:45. I think the time is right of 12, it will be over. Okay, like this way we can do. These are the some applications, some problems using our computation fluid dynamics. Suppose those who want to do the research in fluid dynamics, okay, so you can choose either, we can't choose the experimental method, it is very difficult. You can choose either the mathematical fluid dynamics method or computational fluid dynamics method. Suppose if you want to computational fluid dynamics method means, you want to spend some, you can use some softwares which are in the market. So for example, MATLAB. Nowadays the simulations also can be done using MATLAB also for fluid software, I already told. So like that ways you can able to do the research. Once again, I will thank the organizers who gave me this opportunity to share my ideas on doing the research in the computational fluid dynamics. I think it will be very helpful for those who want to start their research in the fluid dynamics. Thank you, one and all.
Thank you for joining us, sir. It was a really engaging session on computational fluid dynamics, convection in cavities, and the dynamics of blood flow. Participants, if any of you have any questions, you can unmute yourselves here on Zoom, and you can ask your questions. And those who are streaming this from YouTube, please feel free to post your questions on the chat box or the comment section, and one of us will take it up.
In chat box, there is one question. Can you tell some software for finite difference method? Like that was they're asked. Okay. In finite difference method means you can go for that MATLAB is very it is enough for doing the for finite difference method, I think so. Finite difference method, you can use that MATLAB software. Nowadays the cavity problems can also be solved using MATLAB. That is one question is there in our my chat box. So I suggest the things is MATLAB is enough. Any questions? I think so. One question. They are asking for Fortran. Say Fortran 7.0 is there, ma'am. That is the latest version. It will be like C++ only. Thank you.
Dr. Abdul Hakim, sir.
Thank you, sir.
Sir, very nice presentation, sir.
Okay, sir. Thank you, sir.
So I have one small question, sir.
Okay, tell me, ask me, sir.
Sir, give any example for non-Newtonian fluid, sir?
So non-Newtonian fluid means blood is example for non-Newtonian fluid, sir.
Okay, sir.
Our blood is non-Newtonian fluid. Suppose you want to do the research in medical field, means you want to use the non-Newtonian fluid. Blood is the best example.
Okay, sir. Okay, sir.
Okay, thank you.
Now current best fluid paper or what is the now current or best paper, sir?
Best journal you are asking?
Right, sir. Which is best journal for publishing fluid dynamics paper, sir?
In Journal of JF, Journal of Fluid Mechanics is the best journal for fluid dynamics. If you do the research in either both analytical, numerical, experimental only, you can publish in JFM, Journal of Fluid Mechanics. Otherwise, the best because it is engineering oriented problem. The Journal of Heat and Mass Transfer, Computational Fluids is there. Journal of Molecular Liquids in Science Directory. So this heat and fluid flow in Science Directory. So these are the best journals in fluid dynamics. JAFM also now it is more than for 2 or 3 impact pack will be there. Heat and mass transfer also there. International Journal of Heat and Mass Transfer. So these are the some best Q1 journals in our fluid dynamics.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you.
So one participant in YouTube has asked, what are the difficulties that we face in horizontal?
Horizontal position.
Yes.
If you keep that baffles in horizontal position means what will happen means, wait, I will show, because the cavity, what to tell means it will act as a barrier for fluid flow, but because the half of the cavity only active, then the air or the liquid below that baffle will be inactive when compared to the above the cavity. Suppose if you are taking vertically means the whole cavity will be active, so the heat can be absorbed by the side walls very quickly when comparing to the horizontal. If you keep the horizontal means only the half of the horizontal wall only absorbing the heat, so that's why the vertical position is very it will give more enhanced when comparing to the horizontal one. Ma'am?
Okay, thank you, sir.
Okay, thank you.
I think with this we can conclude the question answer session for this particular talk. Thank you, Dr. Abdul Hakim, for joining us today.
Okay. So somebody is asking, can I get the Fortran the software? Okay, you can get the Fortran software. Suppose if the mail means I will send you. My mail ID is I'm typing.
Okay.
Okay, Dr. Abdul. I will send the latest version. Otherwise, you can get in Bardar University also, in Max department, they are having that latest version of Fortran softwares. This is my mail. You can mail me. I will send the Fortran software. Those were okay. Okay, thank you.
Thank you, sir.
Thank you, ma'am. So there is
we shall now have a lunch break till 1:30. We request you, the participants, to please join us at 1:30. The next lecture by Dr. R. Prakash will start at 1:30 sharp.
Okay, thank you, ma'am.
Thank you.
Once again, I thank you all the organizers who gave me this opportunity to share my things. Okay, thank you, madam.
Thank you, sir. Thank you for joining us.
Shall I leave the?
Yes, please do.
Okay. Thank you, ma'am. Thank
you. Okay, we'll all join by 1:30 again.
Sir Subir Kumar sir, please contact Dr. Jai Kumar sir. Now paper presentation is going. So this is only for eminent speakers paper presentation. So you contact to Dr. Jai Kumar sir.
Sir Matthew.
Yes, sir.
I think the Sir Prakash sir is there. Prakash sir, you are there? Prakash sir.
Sir, Pranesh sir, good afternoon.
Good afternoon.
Sir, he is from RVS College, Bangalore.
Yeah, RVC College. Prakash,
Yes.
I know. That's what I'm asking, whether he's there, he's joined or not. I just want to check.
Yes, sir. Within few minutes, I will also call you, sir.
Yeah.
Yes.
Richa, you'll be handling this session, right?
Yeah.
Sir, you have to unmute the Prakash. Prakash.
Hello, sir. Hello, sir. Pranesh, sir. Hello, sir.
Yeah, good afternoon, Prakash.
Good afternoon, sir. Good afternoon. Am I audible, sir?
Yeah, you are audible.
Okay.
Sir, you are ready, sir? Shall we start?
No issues, sir. I think some other presentation is going on the background. I don't know. Maybe.
That is a paper presentation is going on.
Okay. Then you can start, sir. No problem.
We'll start with that.
Yeah.
I joined it too. That is happening in the other group. That means
Okay.
with mobile.
Okay, sir. Okay. Thank you, sir. Thank you.
I'm there in both this side. I'm managing that.
Okay. Very great, sir. Great, sir. You. Okay, sir. Thank you.
And sir, we can start, answer.
Yes, sir. We can start, sir. No problem.
Answer, Matthew, we can start.
Yes, Richa, we can start.
Yes. Okay. Good afternoon, everyone. Our next speaker for today is Dr. R. Prakash. Dr. Prakash holds a PhD degree from Visvesvaraya University of Technology, Belagavi. Currently, he is working as an associate professor in the Department of Mathematics, RV College of Engineering, Bengaluru. He teaches courses on mathematics for machine learning, computational advanced numerical methods, and advanced statistical methods. He has 6 international publications to his credit. He won the second prize in the state level Sri Ramanujan Mathematics competition conducted by ISTE New Delhi. He has authored books on mathematics, a part of the GATE series, Pearson Education, and PGCET KSET Sapna publications. Without further ado, please join me in welcoming our next speaker, Dr. R. Prakash.
Yes, sir. Good afternoon, madam, and good afternoon, participants. Myself, Prakash, working. I'll share the screen first before going to that. Please let me know whether my screen is visible or not.
Okay, sir.
Madam, is my screen visible?
It's coming.
Just I'll open one file. Is it visible?
Yes, it's visible.
Okay. Shall I start, madam?
Yes, sir. Please go ahead.
Okay. Thank you. Good afternoon to everyone. Myself, Prakash, working as Associate Professor in the Department of Mathematics, RV College of Engineering, Bangalore. Firstly, I would like to thank the organizers for giving me this such an opportunity. I wish all the participants to a very happy Ugadi. Due to time limit, I converted my PPT to PDF because in shooting method, there is more of writing is required. It is easy for me to update few things on the PDF. So rather than on the PPT. Today I am going to give overview of a boundary value problem and also solution by shooting method. So outline of my presentation is first we shall discuss about boundary value problem and then shooting method, and examples I have mentioned here. So numerically it is very difficult to solve method problems on shooting method. One has to be go with the computation only using any of the softwares, either MATLAB, Scilab, or Mathematica or anything. but I'll try to give you some illustrations with examples so that how you can proceed with an method, that shooting method. So before going to that, I am going to explain about initial value and boundary value problem. So if my screen is not visible, please let me know, because I am not seeing anyone here once I share the screen. If anyone confirm me, I'll continue.
Okay, let you know, sir, if your screen is not visible. Right now, it's very clear. So you can
Okay,
go on.
thank you very much, madam. Thank you. See, as we know that initial value problem means all the conditions, the auxiliary conditions are given at initial point only. See, y of a equals y of a something, some value of y, and y dash of a equals y dash of a some value. Say both the cases x is given at a only. So initial point only. So it is initial value problem. Similarly, boundary value problem means just observe here y of a and y dash of b. So x is defined at two different points. X is equal to a here, x is equal to b here. So two different points, it is called boundary value problem. And solving initial value problem, there are plenty of methods available numerically. So the limitations is with the boundary value problem. There are no standard method to solve a boundary value problem. There is a method called finite difference method, finite element method, and also a method called shooting method. In shooting method, the idea is, in shooting method, the idea is converting boundary value problem into an initial value problem, and it is an iterative procedure and can be efficient in solving boundary value problem. So that is one advantage of shooting method. So actually, generally it works like this. The sufficient number of conditions are added. At one end. These conditions are adjusted until the required conditions are satisfied at the other end. This point I will illustrate with an example. So means whenever you are solving an initial value problem, all the conditions, if it is nth order differential equations, all n conditions are given at initial point only. So these n conditions are not given. We have to supply that conditions. We have to provide that number of conditions to achieve the solution of the boundary value problem. That is what the major part of shooting method. And here solve this, we will get a system of IVPs later on, you will came to know, and using MATLAB or Scilab or Mathematica, any softwares you can use and you can solve. Even for a simple cases, we can go for, I mean to say simple in the sense linear differential equation, and also simple second order differential equation. Manually also you can solve it. And this will be the overview of illustration of shooting method. This I'll address once again, but time being, you just remember this is our exact solution. And these are the boundaries. We are guessing the initial value S0, S1, S2, like that until we reach this solution. This is your exact target. That's why the name called shooting. So the target, we have to shoot it properly. So I'll repeat once again this. Next, there is some minimum, I mean, there are some certain steps to follow to find out the solution using shooting method. These are the steps. First step is converting ODE into a system of first order, ODE, that is boundary value problem, to a system of first order ODEs, that is initial value problem. And the second step, you have to guess the initial condition if they are not available. Generally, they are not available in case of a boundary value problem. And then solve the initial value problem obtained in the step 1 using any of the standard method like Euler method, Runge-Kutta method, even Taylor series method also you can use it. Then finally, then you have to check if the known boundary conditions are satisfied. I mean, your target is reached, the boundary reached or not. If not, you have to modify the guess. You have to modify your guess what you have taken. Finally, you can use any iterative methods or interpolation technique to update the guess. This guess modification is very, very important. The initial guess is nothing but your unknown. So the unknown can be modified with the help of these iterative method. That methods, I think you are all familiar with the bisection method, the Newton-Raphson method, secant method, and some interpolation technique also you can use. Okay. Anyhow, I'll discuss this later. Next, repeat 3 and step. See, 3 is solving the initial value problem and modify the guess. These 2 steps repeated until the desired solution is obtained. What is the meaning of desired solution? We have to reach the target. We have to reach the target. That is what the idea, I mean, steps which are involved in shooting method, solving any boundary value problem using shooting method. Now, there are 3 common boundary conditions we come across. One is boundary condition of first kind. This is also called as, 1 second. This is also called as Dirichlet's boundary condition. Dirichlet's boundary condition. And this is Neumann boundary condition. So where conditions are given on the derivatives, where conditions are given on the function. So function f of x. Here function f dash x, slope. Whereas it is a combination. So Robin boundary conditions, these are all the boundary conditions of third kind where both cases are available. Now, in the case of first kind, here see, observe here, y of a is given, y of b is given. Boundary conditions are given. This is a boundary value problem, right? Since it is a second order differential equation, we need y double dash, we need a condition y of 0 and y dash of 0 we need, because initial condition we want to solve this second order differential equation. This, but boundary condition is given, but initial condition on slope is not given. That you have to guess, that is your y dash of a is equal to alpha. So y of a is given. Y of a is given in the first case. So we don't have y dash of a because we need that y dash of a to proceed with the solution. So that you have to guess, that I have called as alpha. We are guessing that as an alpha. Then, as I mentioned, you have to repeat that step 3 and step 4. That is common in shooting method. Once you guess a initial condition. Similarly, in the second case, you observe the boundary conditions here. It is a second order differential equation. 2 conditions are given. Y dash of a equals a, y dash of b equals b. These are the 2 conditions given. But here, y dash of a is given. See, initially y dash of a is given. On slope, the condition is given, value is given. Whereas y of a is not given. Y of a is not given, that you have to guess, that is your alpha here. See, y of a is guessed here. So that alpha, again, you have to take this alpha and start solving the solution for the second order differential equation using any of the numerical method. That is step 2 and step 3, you have to continuously go. Similarly, in the case of boundary condition, where some complexity of the problem arises, where we have, you have to assume first y dash is of a equals alpha, then you have to rewrite from these 2 equations for y of a, and this y of a will be a1 alpha plus a divided by a naught. So this is what the case. So it come across rarely. So we'll consider boundary condition of first kind and boundary condition of second kind. A majority of the problem comes under these 2 categories. With this, I'll go with an illustration. Please, whatever I have said, I have mentioned in the previous slides. For that, I am going to give you supplement for those things. See, consider, for simplicity, consider second order ODE. So you consider second order differential equation in the general form. Y double dash is equal to f of x comma y dash. Here 2 conditions are y of a is equal to a, y of b is equal to b. So this is no doubt, it is a boundary value problem. Boundary value problem. I'll just take a smaller one. Boundary value problem. Now just observe the picture, the illustration I showed in the slide is same as this one only. Just observe here. So this is your A point and this is your B point. This is the boundary for this problem. Okay, AB is given. So for A, this is your point y of A. So y of A. Okay, I think it is visible now clearly. Then it is y of B now. So this is your actual target actually. Now you guess, you take one slope here, you take one slope here, and that is y dash of A is equal to alpha. This is y dash of A is equal to alpha. Y dash of A equals alpha. Then it will shoot here. See, it will shoot here. That is, you are shooting at, with this guess, you are going to this. It is overshoot. I mean, above B, above y of B. Similarly, you take another slope and it will shoot near here. Correct? No? So that is y of B is equal to beta, another guess, beta. So it is undershoot. Okay. Now what you have to do, you have to continuously guess these values and shoot until you reach this B. That is why it is called shooting method. So target is our y of B. That target we have to reach. That is the meaning called as shooting method. Now, once these two are not reaching our target, you have to chop off these two values and similarly go for the fresh guess and continue the process until you reach y of B. Correct? You remember here. So what could be the slope at x equals A? We can reach the target as close as possible. Very, very important, because in most of the cases, we are not going to get the exact solution. So generally in numerical method, we are going to get an approximate solution only that is more than sufficient for our analysis. It is nothing but, see, whatever you are saying here, this sentence states that it is nothing but you are going to find out a problem of finding a suitable slope. That's all. You are giving a guess for the slope here in the case of this problem. So you are nothing, it is nothing but finding a suitable slope for this problem. So you come across this type of case now, numerical in numerical method. See, we have x and this is y. I mean y of x. What are the values of A? X. X can take x0, x1, x2 up to xn with the step length h, equal length h. H is the step length. And now corresponding y will be y of A, y of x1, y of x2, y of b. See, this y of A is given. See, it is given here. Y of A is given. We don't have y dash of A. So that we are guessing and we are reaching, see, target to reach with alpha as the initial guess. This we are going to reach. You remember these two steps, very, very important. Target. Target is, this is our target. Y of B is equal to B. That is, I think it is given in the problem. Y of B is equal to B. Now, compare Y of B evaluated with this alpha, initial guess alpha, minus this B, this target. What is this actually? It is nothing but error. So you just take a modulus of this. If that less than some tolerance, you can fix tolerance on your end. It may be 10 to the power of minus 3 or 10 to the power of minus 2 or 10 to the power of minus 4. That depend upon your problem. Then the solution of this indicate that if it is less than this tolerance, that indicates that solution to the BVP is reached. Solution to the BVP is reached. So this is what the idea in shooting method. Okay. Now, looking for alpha. See, this, the statement modulus of y evaluated with the help of alpha, initial guess alpha, evaluated at B, evaluated at endpoint B minus B less than epsilon. This is the actual target. Okay. Numerical minus actual less than epsilon. Then the solution is reached is equivalently saying that looking for alpha, you just observe here, looking for alpha such that this difference is almost zero. This difference is almost zero. So now it is equivalently saying, see, this is again equivalently saying, finding the solution of phi of alpha. This you can treat it as phi of alpha. Means that y of B evaluated at B, y evaluated at B with the guess alpha. With the guess alpha minus B is equal to 0. So this is an algebraic equation. So that is what we have to guess. So new guess for alpha. The finding the solution is nothing but finding a new guess for alpha. So this is our equation that can be solved by any of the iterative method. Those iterative methods that as a like bisection method and secant method, Newton-Raphson method, regular-False method, etc. and so on. But the standard methods which are using to find out the initial approximation or the guess for the unknown or interpolation method, secant method, and Newton-Raphson method. See, remember, in interpolation method, we need 2 points. We are taking 2 points. I mean, 2 guesses we are taking, and we are going to join a line. So wherever the line crosses x-axis will be the new slope. That is what? Intersection with the x-axis is the new slope here. So with this new slope, you move on solving the IVPs. And the secant method is this. You're already familiar with that secant method. And in that, we need 2 initial approximation, because secant method starts with n equals 1, 2, 3. The suffix for n value will be 1, 2, 3 like that. So we need alpha naught and alpha 1, because if you put n equals 1 here, alpha 2 you get. In the right hand side, you are going to get alpha naught and alpha 1. So it is a function of alpha 1 and alpha naught. So we need 2 initial guesses to find out the new slope. Okay, I'll tell you what are the drawbacks on all these in all these methods. Then finally, we have Newton-Raphson method. Alpha n plus 1 is equal to alpha n, phi of alpha n divided by phi dash of alpha n. So it is the phi dash, wherever there is a dash, mean it is a need of derivatives required, and also suitable initial value of alpha naught. Because I have mentioned alpha, so that's why it is alpha naught, initial guess. It is for the unknown. So now, the one drawback of Newton-Raphson method means suitable choice of this, and also we are handling with the derivatives. So derivatives are very sensitive. We need to take care of the divergence criteria also. Convergence criteria also. In this, just you can have a look into it. So the choice of iteration method, this step plays very, very important role in shooting method actually. So there are 3 techniques: interpolation, bisection, secant method. So these are one category. I can call it as one category. See, in interpolation technique as well as secant method, we need 2 initial values, no derivatives involved. But guessing 2 conditions itself is a long process, and it is tedious some cases. So that's why these are not advisable. You can do it, but it is not advisable. And also bisection method, one can go through with a bisection method, but the convergence is of linear order. That's why we can avoid bisection method. So one of the best method to update your initial guess is the Newton-Raphson method. Here the advantage is, so remember, only one initial approximation. We need only one initial approximation, and also we know that Newton-Raphson method is of order 2, that is the quadratic convergence. So it converges very faster than other methods. And how the method will work out? See, phi of alpha will be this one, y of 1 minus y of 1 given. So this is nothing but y of b evaluated at alpha, and this is nothing but y of b. So that is your b. So this is given from the problem, and this you have to evaluate numerically. So we have to update this alpha using this method, that is Newton-Raphson method. Formula, I think you are all familiar with that. Alpha n minus f of alpha n by f dash of alpha n. So where n equals 0, 1, 2 like this. And remember, since it is f dash, derivatives are involved. So that derivatives will be y now becomes a function of alpha here. See, remember, function of alpha. So we need a partial derivative dou y by dou alpha. So we have to differentiate IVP1 with respect to alpha. That's why we need a derivative for derivative in the Newton-Raphson method, that is with respect to the unknowns alpha. It may be one unknown, it may be 2 unknown. Later on, you will came to know that. Now I'll go with few examples with an illustration, and I'll show you one result which I have computed using a Mathematica. Because the programming part, it is very difficult to explain in a stipulated time. Just I'll go with an illustration so that one can understand what is actually going to happen in shooting method and what actually programming is doing. So on backend, what is actually the program computation work is going on in any software, I mean any program is concerned. Either it may be Mathematica or it may be a Scilab or it may be a MATLAB. See, this is a very simple problem. Y double dash minus 4y plus 4x equals 0. Given that y of 0 equals 0, this is the example one. So, and then y of 1 equals 2. Now, if you illustrate geometrically, it is very good to analyze. So, always geometrical representation will help a lot to understand. Sometimes choosing the initial approximation also, it will help definitely. So that's why what is according to the condition, y of 0 equals 0. So this is the point actually. And what is another boundary condition, y of 1 equals 2. It is given here. So this is our actual target. This we have to reach. So to be determined. This curve we have to find out. Correct? No. So what is the step 1 here in shooting method? Means convert this star into, since it is a boundary value problem, it can be solved only through converting into system of first order ODEs or as finite difference method. So any of the standard methods you can follow, one can follow. So since we are following with the shooting method today, so I'll just tell you how to convert this into a first order ODEs. So for that, I need a notation called y equals y1, just for the convenience. If y equals y1, what is our y dash? Y dash is, this is y dash. So y dash is dy1 by dx. So when you differentiate y1 with respect to x, that becomes y2. And I need a condition for y1. So y1 of 0 is given because y1 of 0 is same as y of 0, that is equal to 0. And go to the second derivative. It's already given. Y double dash is equal to, rewrite the terms on the right hand side. It is nothing but dy2 by dx. So given from the data, it is minus 4y, right hand side becomes 4y, plus 4x becomes minus 4x, and y2 of 0 is not given. See, y1 of 0 is given, y2 of 0 is given, 0 is not given. I mean to say y of 0, the initial y dash of 0 is not given, y dash of 0 is not given. So that is your unknown here, but boundary is given. We have to reach this target at x equals 1, we have to reach 2. That is the target for this. So finally, what is that? If you write in a system matrix form, it will be y1 dash, y2 dash is equal to y2, the first one, this one, and the second row will be this. And with the condition y1 of 0, it's given y of 0, and this is your unknown. So that is how one can understand the shooting method to start the solution. So that is what I have mentioned. So the problem will be solved using any of the numerical methods. For solving IVPs, you can use Runge-Kutta method, Runge-Kutta-Fehlberg method, or Euler method, even Taylor series method, etc. For different values of y20, remember, until we reach this one, target y1 of y1 is equal to 2. This is one example where you can understand geometrically how this shooting method takes place. Now I'll look into the second problem. So just observe this. So I have taken around 3 to 4 problems. So they're all of different cases. So just observe here. Example 2. See, consider y double dash is equal to y square by 2 plus x. Y of 0 equals 0. Y of 2 equals 1. Again, at x equals 0 given, at x equals 2 is given. So these are two values of x. These are the boundary values. Again, this I think you no need of, I'll just briefly explain this. Again, you call let y equals y1. So in case of IVP1, I called as IB1. I'll let you know later. So you will see that. So y dash will be equal to dy1 by dx. It is nothing but y2 because dy1 by dx is nothing but y2. And y1 of 0 is as same as y of 0 because we need a condition y1 of 0. It is given. See, it is given. y1 of 2 is also given, but this is not required to start to write down the solution. I mean, to find out the solution, we need to reach this target. That is very, very important. Similarly, Go to the second derivative, y double dash, it's already given. It is nothing but dy2 by dx. On the right hand side, it's already available. y1 square by 2 plus x. Why it is y1 square? Because y is y1. y2 of 0 is alpha. This is not given. It is our unknown. y2 of 0 is nothing but y dash of 0. I mean y1 dash of 0. y2 is y1 dash. That is nothing but dy1 by dx. dy1 by dx is nothing but y1 dash. Now, as I mentioned, we are following Newton-Raphson method. Derivatives are involved. So now we have a function of alpha, unknown alpha. We need to differentiate partially with IVP1, partially with respect to alpha, and noting that dou y1 by dou alpha is capital Y1, dou y2 by dou alpha is capital Y2. So that we are going to do now. So just differentiate IVP1 now. Dou by dou alpha of, on the left hand side, say dou by dou alpha of dy1 by dx is equal to dou by dou alpha of y2. You are noting dou y1 by dou alpha as capital Y1, capital Y1. So this will be, you can interchange the derivatives. We can interchange the derivative d by dx of dou y1 by dou alpha. Here dou y2 by dou alpha. So what is dou y1 by dou alpha? You noted as y1, so it is dy1 by dx. So dou y2 by dou alpha is y2. So y1 of 0 is 0. Again, you differentiate this. It is dou y1 by dou alpha of 0 is equal to 0 with respect to alpha, because it is one differentiation. Dou by dou alpha of 1 equal to 0. So you are noting dou y1 by dou alpha as y1. So that is why y1 of 0. Similarly, the second equation. See, in the second equation, you remember left hand side same as that. You are just interchanging the partial derivatives, and you are noting that dou y1 by dou y2 by dou alpha as y2. So that is dy2 by dx. Go to the right hand side. It's very, very important. One, you should make a note of this thing here. Y1 square we have. Y1 square is 2y1, and the y1 differentiation is dou y1 by dou alpha. So the dou y1 by dou alpha is nothing but your y1. It is just like x square differentiation divided by 2 plus x. And y2 of 0 is 1. Why it is 1? See, we have y2 of 0. Y2 of 0, some small y2 of 0 is equal to alpha. You are differentiating with respect to alpha, means dou by dou alpha of alpha is 1. So that is what this. This is the second example where we have two IVPs, two set of IVPs. One thing you remember here, whenever there is number of unknowns is 1, number of unknowns indicate the number of IVPs, Here there are two sets set here. I mean, one IVP1 consisting of two equations. So there is one unknown here. So there is one more IVP, means another two equations here. So these are the two equations. This is one equation and this is another equation. With that, what is the algorithm involved here? How to proceed with the solution? See, one thing is you have to go with the initial values. Manually also, if you do, you have to take care of all this. X0, start with the initial value, y1 0, y2 0, y1 of 0, y2 of 0, because there are four conditions, four differential equations. So small y1, y2, then capital Y1, capital Y2. So there are four unknowns here. I mean, conditions we have to give at initially. So y1 of 0, y2 of 0, this is given, this is given. 0 is 1 actually. This is also given because now h you specify and you write down x value, and tolerance you have to mention. As I mentioned, 10 to the power of minus or 10 to the power of minus 4. And then in the step 2, solve IVP1, solve IVP2 using the initial values obtained in step 1. Then you check this. This is very important step. You check this using Newton-Raphson. This is the Newton-Raphson method. Alpha n plus 1 minus alpha n less than tolerance. Tolerance is here. Less than tolerance. Stop. Else go to step 2. Go to step 2 and repeat the process and with the new alpha. How to find out new alpha? We find out new alpha using Newton-Raphson method. See, because of this derivative, we need differentiation IVP, derivative of IVP 1, IVP 1, derivative of IVP 1 with respect to alpha. With respect to alpha. So this is very, very important. So in the first example, as I mentioned, in the first example, we don't have unknown, I mean, only initial condition is given that with an example of initial slope we have guessed and we followed. And in the second example, we have differentiated with respect to alpha, that we are going to check how the system of how to convert that given boundary value problem into a system of ordinary differential equation. And also 2 IVPs are coming because of this unknown parameter alpha. To update the alpha using Newton-Raphson method, we need to differentiate the IVPs, respective IVPs, with respect to the corresponding to the unknowns. Now, this example is the motivation for solving problems of fluid mechanics, especially the research problem, in order to address it. Like Rayleigh, suppose one on doing a problems on convection or anything. So the critical values, eigenvalues are very, very important. So normal ordinary method, analytical method always will not support the solution. Sometimes we need to go by a numerical method, and some advanced techniques we have to use. For that cases, we need to go for a shooting method or finite difference method or any other method. So here the problem is, you just observe here, d square y by dx square plus ky is equal to 0. Y of 0 is equal to y of 1 is equal to 0. Boundaries are given here. Boundary values are. Here we try to find the value of k, very, very important. See, so there are cases where find out the value of unknown k. I mean to say, for what values of k, this y satisfies that given differential equation. That is the aim of this problem. So for that, again, you go with the solution, this one, denoting the values. I mean, y equals y1, denoting the variable y as y1. And also you observe we need one more variable, that is y3. Y3 you call it as a k. So k is independent of x. No doubt if you differentiate with respect to x, that will be 0. Now you go with the writing IVP1. So this already I have mentioned. I'll not go in detail. And it will be minus y1, y3 because of what? See, you just bring this to right hand side. Bringing it to right hand side, but becomes minus k into y. K will be y3 and y will be y1. That's why it is minus y3, y1 and y3. And y2 of 0, the slope is not given here. So that's why I have taken a guess. It is unknown. And the third y3 also we need, because the value of y3 is nothing but your k value. So that condition is also required because of this differential equation. We don't know that. You can call it as beta. That beta you can take it as 0 or 0.5, 0.9, something like that, or 1, anything you can take, and you can start the iteration process. Similarly, since there is unknowns, 2 unknowns are there. Once you have to differentiate partially with respect to alpha, and noting dou y1 by dou alpha as capital Y1, dou y2 by dou alpha as capital Y2. Similarly, differentiate partially with respect to beta, noting dou y1 by dou beta as v1, dou y2 by dou beta as capital V2. See, just you can observe here. I'll just quickly explain that. See, this part you can observe. There is y1 and product rule. You have to see, this is nothing but dou by dou alpha of y1, y3. How to do that? Y1 as it is, dou y3 by dou alpha. So dou y3 by dou alpha is nothing but capital Y3 plus. Then y3 as it is, dou y1 by dou alpha. So dou y1 by dou alpha is nothing but capital Y. That we are going to write down whenever there is a product of variable is involved. Then with respect to alpha, this is 1. With respect to alpha, this is 1. Remaining, since again we have to differentiate with respect to beta, you can make a note of the changes, what is going to happen. See, in place of beta, you will have 1, all others are 0. You can observe here. Okay. Now, algorithm follows the same thing. First thing is initialization, solving IVPs, IVP1, IVP2, and IVP3, and check these conditions for the tolerance. Stop if it is less than tolerance. Otherwise, again repeat IVP1, IVP2 with the new values of alpha, beta, and one can display the values like y1, x, y1, y2, y3. X can take a range from 0 to 1, and this y3 is of interest. That y3 is nothing but k value. For what value of k, our differential equation y satisfies y double dash plus ky is equal to 0. That is our idea behind solving that differential. Whenever they say solve a differential equation, means computing the relation y of x. So with that, I'll with these 3 illustrative example, I'll just take a research problem where the Chandrasekhar problem. So that is the basic problem in convection analysis, and a very famous problem. And most of the articles, if you refer research articles, this problem is quoted everywhere. So I think I'm not going to discuss the detail of how this is arrived. This differential equation 1 and differential equation 2. This is by making use of normal mode analysis and converting that partial differential equation to an ordinary differential equation, so that for computation one can use any of the methods which are available for ordinary differential equations. Okay, so partial differential equations means that it is nothing but conservative of momentum equation and energy equation. Simply energy equation and momentum equation is nothing but these 2 equations. Now you can observe here, if you rewrite that, it will be a 4th order differential equation, and this is a 2nd order differential equation. This is a momentum equation after normal mode analysis. This is an energy equation after the normal mode analysis. And these are the boundary conditions one can observe. So I'll share this PDF. You can go through it in detail. It's very easy to, because one has to look into that conditions, how it is going to change, and one has to write on his own, so that you will feel the experience of how to write the boundary conditions, and I mean how to use the initial condition and how to arrive at the boundary condition, how to arrive at the solutions. And also that writing a set of ordinary equations, ordinary differential equation, that is set of IVPs, also plays a very, very important role. So W of 0 is 0 given, W of 1 is equal to 0 is given. And similarly, W dash of 0 is 0 given, W of 1 is equal to 0 is given. T of 0 is 0 given, T of 1 is equal to 0 is given. So there are 2 boundaries. So on T, boundary conditions as well as initial condition is given. On slope of W, so boundary condition and initial condition is also given. On W also, boundary and initial conditions are given. We'll see how many set of differential equations you are going to get. So since it is 4th order, so we need to move up to 4th, dy4 by dx. So for y1, y2, y3, y4. So then we'll have 2 2nd order differential equation. I mean d square t by dx square on t, dz square I can say with respect to z. Now, so you can call it as t5, t equals y5, and we have one more critical value. That is the motivation of the previous problem. That is just like a k. So eigenvalue, critical Rayleigh number is nothing but eigenvalue. So this we have to find out. For this, you call it as one unknown y7. So if you arrive at, so you are going to get these many equations. As I said, this is the first IVP. This is for the 4th order differential equation, d square w by dz square, dz power 4. Then we have unknowns. These are the boundary conditions used, referring to the previous problem. This is one unknown alpha, and this is also unknown beta. And for simplicity, you no need to take too many unknowns, because it is very difficult to compute matrix derivatives and also inverse of a matrix in Newton-Raphson method. So that's why I have scaled. Scaled means divide throughout by that unknown parameter beta. I have scaled, and the unknown is our delta, that is our r, actually r value. Now there are 3 unknowns. I converted as 3 unknowns: alpha, beta, and delta. So we need to have partial derivative with respect to alpha, with respect to beta, and with respect to delta. That is what I have done here. That is your IVP2. Please, you can go through it. I'll just go ahead. So similarly, IVP3, we are differentiating with respect to beta. This is what the, see here, whenever there is a small capital, small y's and capitals, it is nothing but partial derivatives. I mean, product rule. Similarly, IVP4 with respect to delta. Once this is done, follow the same algorithm. First is initialization. See, these W and T values can be taken with the help of a trial function, suitable trial function, and delta by singleton Galerkin methods. And solve, there are 4 IVPs, IVP1, IVP2, IVP3, IVP4. Check the tolerance. If the tolerance is less than tolerance, stop. Otherwise, go to step 2 and repeat the process with new values of alpha, beta, delta. And this new values you can compute using Newton-Raphson method. So this is what Newton-Raphson method. So why I have taken F1 and F2 and F5 only? This is because of this. Only those conditions have, those equations have boundary conditions. Just observe here. See, there is a boundary condition here. There is a boundary condition here, Y2, and there is a boundary condition here. So these are the things you remember. You just, Y1 means capital F1, function of F1 of alpha. So this is nothing but, I mean, F1 of alpha, beta, delta. This is your F2, and this is your F3. So wherever boundary is given, F5. Those boundaries we have to reach using the initial guesses of alpha, beta, and delta, in our case, using shooting method. I mean, target is reached. So this is the Newton-Raphson method. I hope you are all familiar with that. So that is Jacobian is involved because too many derivatives. So J inverse and C is this one, F1, F2, F3. This is nothing but your Newton-Raphson method for system of equations. That's all. So the system of equation means alpha, beta, and delta. One can refer that method. It's easy to follow. And only thing is finding the inverse here. So sometimes due to sparse matrix, I mean the values are almost zero, some cases. So you need to go for pseudo inverse for this. Pseudo inverse for this. To find out numerically, I mean any programming if you want to do, one can go with the pseudo inverse. So these are all some illustrations. Just I'll show you one more PDF. There I have done the same problem with Mathematica actually. So Mathematica, that's whatever logic I have followed, same thing is followed here also. So that's why so many Y3, Y4, Y5, everything. See Y7, everything is there. I have followed the same logic here, but syntax somewhat different compared to MATLAB or Scilab. Why I have taken this is because of it is user friendly. Mathematica is user friendly. No, too much programming is not required. Syntax is very simple and easy to follow. So this is nothing but initial guesses. You know, this is for alpha and this is for beta using suitable trial function. This is for delta. Since we are considered free boundary conditions, free boundary condition, initially I have guessed the R value as 670 and updated using this. And ND solve is the one method, I mean the one case where it will solve you to solve a differential equation. The ND solver is the thing in Mathematica, just like your ODE solvers. It is just like a ODE solver. So using that solver and Jacobian, this is Jacobian, and B is the right hand side matrix. And see, inverse you have to find out because F of F dash, if bring F dash to this means nothing but inverse, F dash inverse. That's why it is inverse. Then after finding some with initial guesses, I got the values like this. I plotted this with R versus A. These are the plotted. So this is what the plot. It is approximately matches with our result. So this is the plot. Okay, with this, I'll end my presentation. The reason is it's very difficult to show the programming, everything in this 45 minutes of time. Whenever there is a time required, definitely I'll help you in that. You can mail me. I'll just help you in solving any of the problems using shooting method, any of your research problem using shooting method. Hello, madam.
Thank you, sir, for the engaging session on shooting method. I'm sure most of us found it really useful. If you don't mind, can you please share your email address here in the chat box?
Yeah, I'll just share, madam.
Meanwhile, participants, if any of you have any questions, those of you who are on Zoom, you can unmute yourself and ask your question. And those who are watching the lecture from YouTube, you can post your question in the chat box or the comment section.
Prakash R at rvc.edu.in. I just posted, madam.
Okay.
If participants, if you have any problem in shooting method, I mean to say, if you are dealing with any convection problem or anything pertaining to fluid mechanics, you can approach me. Definitely, how best I can help you, I'll help you. I can guide you with the programming thing.
Ma'am.
Hello. Yes, present.
You can conclude that, Richa.
So I'll end the question answer session now.
Yeah. Nobody's asking anything. Some questions are there. See there in chat.
If any questions are there, I can address.
So somebody's asking, can we solve queuing problems with shooting method?
Queuing,
Queuing.
Maybe no, madam. Maybe for my knowledge is concerned, queuing is pertaining to something probability thing. No. Maybe I don't know. If it is a probability thing, it's not possible to solve. Any kind of differential equations can be solved using any model which is of differential equation type can be solved using shooting.
Sir, can you mention your email address here?
Yeah, I have mentioned, madam. I think I have mentioned.
It was mentioned here.
Yeah.
Prakash R at rvc.edu.in.
Okay, fine.
Meanwhile, I'll share my presentation thing also, madam. Next
okay, sure, sir. Thank you.
Thank you, madam. If no questions, I will thank organizers and also thank you, Pranesh sir, for giving an opportunity. One of the things, sir, I have some chart is there. Sir, I have third order PDE and I have, okay. So third order PDE can be solved actually. You can just mail me your detail, just I can help you in that. Third order, even fourth order PDE, whatever I have solved that Chandrasekhar problem is nothing but fourth order PDE. That you have to convert into ODE first. That is using the 7 ODS. Okay, fine. That depends upon your number of unknowns. Try to reduce the number of ODEs because you need to differentiate with respect to unknowns. It will get that Jacobian becomes more complicated. Try to avoid that because Newton-Raphson method is maybe 7 OD is correct, but you try to reduce one of the unknowns by scaling it out.
Sir,
please mail your yes.
I have one question, sir.
Yeah.
Sir, it is possible for solving hypergeometric equation at shooting method?
That we have to see the differential equation, madam. Sir, differential equation. What type of differential equations are there? That depend upon the boundary conditions. We can solve.
Conflict type.
Yeah, sir. Do one thing, sir. You can
Yes, sir.
mail me the details. Mail me that only the differential equation part. Only you can write in your handwritten and scan and send me through mail ID. I'll go through it and I'll update you in the mail only.
Thank you, sir.
Thank you. My mail ID is prakashar@rvc.edu.in. It is there in the chat box. You can note down. Hello, madam.
Yes, sir. I think with this we can end the session for Dr. Prakash.
Okay, madam. Okay. Thank you, madam. Can I leave now?
Yes, yes, you can.
Yeah, okay. Thank you, madam. Once again.
Yeah, the next speaker you can just see. No?
Okay, sir. Our next speaker for today is Dr. Tanuja. Dr. Tanuja is currently working as an assistant professor in the Department of Mathematics, Siddha Ganga Institute of Technology, Tumkur. She holds a PhD degree from Bangalore University, Bangalore. A prolific researcher, Dr. Tanuja has published more than 20 research articles in reputed national and international journals. She has also received the Best Paper Award in the conference Recent Trends in Mathematics and Its Applications in December 2019, held at Geetham University, Bangalore. Dr. Tanuja has around 12 years of teaching experience at the undergraduate, postgraduate, and engineering levels. Currently, she is also serving as a referee for several notable international journals, some of which are the British Journal of Mathematics and Computer Science and the Far East Journal of Mathematical Sciences. She is currently also a lifetime member of the Indian Mathematical Society and an international scientific committee member of Mathematical and Computational Sciences in the World Academy of Science, Engineering, and Technology. Let us now welcome our next guest speaker, Dr. A. Tanuja.
Thank you, Richa, for introducing me. Good afternoon, one and all. Today's session, my title of the talk is, it is a complex differential equation. Let me share the screen. Is it visible?
That's visible.
Yes, ma'am, it's visible.
Okay. Okay, so let's start the session. And the title of the topic is, it is the complex differential equation. So in this talk, I will be discussing about at first how this complex differential equation arises. And then I will discuss about, I will give the details of the textbooks available on the complex differential equation. And then I will explain the method to solve the complex differential equation, for which I will take an example on Riccati differential equation. Then I will give the details about my work on complex differential equations and also the ongoing work on complex differential equation. And also I will give the open problems which are on the complex differential equation, and also the journals one can publish papers on this topic. At last, references are also given. Now let us see how the complex differential equation arises. In the year 2013, Professor P.J. Siddeshwar and Titus in the paper Nonlinear Renewable Dot Convection with Variable Heat Source in the Journal of Heat Transfer, where they have considered the differential equation as in 1 and 2. So now, using the transformation f star is equal to f plus ij, here I is nothing but square root of -1, so that equation 1 and 2 can be converted into equation 3, which is a complex Ginberg-Lado equation. That means we are converting the coupled system of real ordinary differential equation as the complex differential equation. And this is the class of equation which belongs to quantum mechanics Schrodinger wave equation. Now coming to the books on the complex differential equation, one can refer Nevanlina theory and complex differential equation written by the Apollon in the year 1993, and the publisher is Walter D. Gruter. And this is an inspiring book where it covers both the basics of the Nevanlina theory, that is the technique we are going to apply in order to solve the complex differential equation. And along with that, there are numerous number of problems has been discussed on the complex differential equation, where they are going to find entire and also the meromorphic functions, meromorphic solution for a complex differential equation. Another book is Nevanlina theory, normal families, and algebraic differential equation, written by Stemmons, and the publisher is the Springer in the year 2017. Here they have considered, at first they have discussed about the basics of the Nevanlina theory and also for the normal families, and they have taken an example where in order to find a meromorphic or the entire solutions for the algebraic differential equations. And another textbook is one can refer is linear differential equation in the complex domain, written by Haroka in the year 2020. This is a recent book published in lecture notes in mathematics book. And here they have considered a linear differential equation, and they have found out the entire or the meromorphic solutions by using the Nevanlina theory. So this about details of the textbooks available on the complex differential equation. Now, before going to finding the solution for a complex differential equation, so let us recall some basic definitions. So let us see what is the analytic function. We denote U as an open set in the complex plane and Z0 to be a point in the open set. And we consider a mapping from open set to the complex plane, which is going to be a complex differentiable at a point Z0 in U. So if the limit as del Z approaching to 0, if this limit exists, then we say that F is a complex differentiable at Z0 in the open set U. So if F is a complex differentiable on U, then we say that it is a complex differentiable at every point in U. And also F is going to be the analytic at a point C in the complex plane if F is a complex differential on open disk which is centered at a point A. Suppose if F is an analytic function at every point on the complex plane, then we call such a function as an entire function. Here we can take an example as a sin z, z plus 1. Now, if the analytic function at every point of the complex plane, except at a points where it has got a poles, then such a function we call it as a meromorphic function. And here we can take an example is 1 divided by z plus 1 and also 1 divided by sin pi z. So these are the basic definitions which are required in order to understand the complex differential equation. So now let us move on to the technique we are going to apply in order to get a solution for a complex differential equation. So we apply the method that is the Nevanlina theory, which is also called as value distribution theory. And this is the branch of complex analysis. And this Nevanlina theory is developed by the mathematician Rolf Nevanlina in the year 1929. And because of this devising, mathematician Hermann Weyl called it as one of the few great mathematical events of the century. So in Nevanlina theory, we mainly study the distribution of roots of the equation f of z is equal to a. Here f can be the entire or a meromorphic function and a is some complex number. So using a Nevanlina theory, to find out a solution for a complex differential equation was first made by the mathematician H. Wittich in the year 1952. So now this Neven-Linear theory has got a wide number of applications. It can be used as a powerful tool in order to find a solution for differential equations, difference equations, and functional equations. It is also used in the study of holomorphic dynamics, minimal surfaces, complex hyperbolic geometry, and many more are there. To mention, I have given only the few. So this Neven-Linear theory is useful in the analysis of meromorphic functions, and these functions have a poles which blocks in the attempt of analysis, where a standard mathematical technique like maximum principle will fails. So to overcome this, Neven-Linear defined a series of a function which take account of these poles, and in turn can be analyzed to provide a property of virginal function. Now let us see the functions devised by the mathematician Rolf Neven-Linear. So first we'll discuss about the proximity function, and this is the function which is defined as in equation 4, and here this is the average of positive logarithm of mod f of z on the circle mod z is equal to r. So for this, we'll take an example is how to find out a proximity value for the given function. We can take an example is e to the power of z. So now this you will substitute in the equation 4, where here the cos value will take the value less than 0 in the interval pi by 2 to pi, and negative 3 pi by 2 to negative pi by 2. So that integral value, it's going to be 0. So now what I will do is I will take a interval as 0 to pi by 2. So on substituting and on integrating, we are going to get the proximity function for e to the power of z as r divided by pi. So before going to the counting function, let us denote the number of poles of f of z in the disk mod z less than or equal to r as a n of small n of r comma f. Here the poles are counted according to their multiplicity, and the small n of 0 comma f is the number of poles of f of z at the origin, and here the poles are counted according to their multiplicity. For example, we can take the function which is of the form z minus 1 whole square times z minus 2 whole to the power of 6 divided by z minus 3 whole to the power of 5. So this function as a pole at 3, so with a multiplicity of 5. So we can say that the small n of r comma f is nothing but a 5. And suppose if you want to find out the zeros for this function, so the counting function for the zeros of f of z, it's going to be the 8, because we can see that there are two zeros. One is z is equal to 1, another is z is equal to 2. So z is equal to 1 is a 0 with a multiplicity 2, and z is equal to 2 are the zeros with a multiplicity 6. So totally it's going to be the 8. So therefore we can say that the counting function for zeros of f is going to be the 8. So now let us see the counting function which is defined as in equation 5. So for this, here the small n of t comma f, which is defined as in the previous one. So that going to be the number of poles of f of z in the disk mod z less than or equal to r. So here we count the poles according to their multiplicity. So now in order to find out a counting function for the function e to the power of z, and this e to the power of z, since it has got a no poles, so we can say that the counting function for this function, it's going to be the 0. Next, before going to the reduced counting function, we can denote the number of poles of f of z in the disk mod z less than or equal to r, as it is nothing but small n bar of r comma f. But here multiplicity we are not going to count, and the small n bar of 0 comma f it denotes the number of poles of f of z at the origin, and here we don't count the multiplicity. So for this, we can take an example as considered in the previous problem. So f of z, as it is nothing but z minus 1 whole square times z minus 2 whole to the power of 6 divided by z minus 3 whole to the power of 5. So here, since this n bar of r comma f, it denotes the number of poles of f, but multiplicity is not counted. So therefore, n bar of r comma f, it's going to be just a 1, because in the pole is going to be, it is z is equal to 3, but multiplicity we have a 5, but in reduced counting function, we are not going to consider the multiplicity. Likewise, if you want to find out the number of zeros for this function with a reduced counting multiplicity, it's going to be the 2, because we have two zeros. One is z is equal to 1 and another is z is equal to 2, but z is equal to 1 is having the multiplicity 2 and z is equal to 2 having the multiplicity 6. Since we are not counting the multiplicity here, so therefore n bar of r comma 1 by f, it's going to be 2 for this function. Now coming to the reduced counting function, which is defined as in equation 6, and this is the one where we are not going to count the multiplicity. Next is the characteristic function, and this is the one which plays a cardinal role in the entire Nevanlina theory, and it is defined as a sum of the proximity function and the counting function, and this is going to be obviously the non-negative quantity. So now how to find out a characteristic function for a function of the form e to the power of z. I'm just taking a simple example here. So as already we have found out a proximity function for e to the power of z, which is going to be r divided by pi, and we got counting the function as a 0 since e to the power of z has no poles. So if you add the proximity function and the counting function for e to the power of z, we get a characteristic function as it's going to be pi r divided by pi. Next is the error function. If you take a small order of the characteristic function as r approaches to infinity, so that's going to be the error function. The Nevanlina theory is been crystallized into two main theorems. So first is the first fundamental theorem, where we consider f to be a meromorphic function and a is any constant in the complex plane. So that the characteristic function of 1 divided by f minus a, it will be the characteristic function of f with an error term as r tends to infinity. Here f is not equivalent to a. So from this, what we can understand is, if a value is assumed less frequently than the average, then the function will come close to that value more often than the average. Now let us see the Nevanlina's second main theorem. Here f is taken as a meromorphic function in the disk mod z less than r, and there are finite distinct complex numbers, so that if you take a proximity function of f plus proximity function of 1 divided by f minus a suffix j, which will be less than or equal to 2 times the characteristic function of f minus n1 of r plus error term. Here n1 of r is given as in equation 10, and the error term is given as in equation 11. So from this second main theorem, we can understand that there are relatively few values for which the function assumes less often than the average. So now coming to the books on this Nevanlina theory, one can read the meromorphic function textbook written by the Heyman in the year 1964, where the basics of the complex analysis along with the Nevanlina theory is been covered. And another textbook is the Nevanlina's theory of value distribution, the second main theorem and its error term, written by the Cherry, and the publisher is the Springer in the year 2001. The next textbook is Value Distribution Theory and Related Topics, written by the Bereskin, Eileen, and Xiang in the year 2004. And the inspiring research paper on the Nevanlina theory is written by the K.S. Charak. The title of the research paper is Value Distribution Theory of Meromorphic Function, published in the journal Mathematics Newsletter in the year 2009. So this is in this research paper, all the basics of the Nevanlina theory for a meromorphic function has been covered, and also the some of the open problems has been discussed. So now, before going to finding the solution for a complex differential equation, we need to understand the basic results which are required. One is the Malquist theorem, where they are going to consider complex differential equation as in equation 12. And here the right hand side r of z comma y, it's going to be the rational in the both the arguments, so that it will have a transcendental solution which will reduce us to Riccati differential equation as in 13. Here the coefficients a0, a1 and a2, they are going to be the rational in nature. Now this Malquist theorem has been extended by Yoshida. So the theorem is named as Malquist-Yoshida theorem, and in this theorem they have considered a differential equation as in 14. Here the right hand side is going to be a rational and irreducible in y with a meromorphic coefficient, and this differential equation will have a meromorphic solution, so that it will reduce this to the form as in 15, and this will have at least one of the coefficient of alpha suffix I of z will not vanish. Now, based on this fundamental results, we can move on to the finding the solution for a complex differential equation. Here I am going to take example is Riccati differential equation, which is considered as in equation 16. Now this Riccati differential equation we can reduce it to the form as in equation 17 by using the transformation W and A with C of Z should not be equivalent to 0. And this is going to be the special case of Riccati differential equation. So now we can say that this special case of Riccati differential equation will have a three distinct meromorphic solution U1, U2, U3, so that there exists a one parameter family which we denote it as U suffix C with U should not be equal to U1. And then this special case of Riccati differential equation will satisfy the condition that U should be the same as a parameter family. So let us verify this proposition. Now we'll choose a W1 as the difference of U1 and U2 with a negative power 1, and W2 as the difference of U1 and U3 with a negative power 1. So, and from this W1 and W2, we can clearly say that if you take a difference of these two, it will not be equal to 0. And this will denote it as, let it be a V0 as in equation 20. Now, from equation 18, we can see that the W1 and W2 will satisfy the linear differential equation as in 19. Since W will satisfy the linear differential equation as in 19, we can also say that V0 will also satisfy the linear differential equation as in 21. Now we'll choose a meromorphic function, that is W suffix C, as W1 plus C times a V0, where C is a complex constant. And now we are going to choose a U suffix C, that is a parameter family, as a difference of U1, and W suffix C with a negative power 1. So now from the equation 22, we can clearly see that this W will be the difference of U1 and U2 with a negative power 1. So now from the equation 21 and 22, so we can get that equation 24 and on integrating this equation 24, we arrive at the equation 25. Now, on simplifying this equation 25, we are going to get the equation 26. Now, if you observe carefully the equation 26, we can see that the right-hand side is going to be the W suffix C. That is from equation 22, we can say that W will be equal to W suffix C. So since W is the same as W suffix C, we can conclude that U is also going to be the same as U suffix C. Because of the previous equation, what we have defined in the equation 23 and the 22. So that means our proposition is true. So the special case of Riccati differential equation will have a three distinct meromorphic solution U1, U2, U3, provided this U should be the same as a parameter family, that is U suffix C. If this condition holds, then only that Riccati differential equation can have a meromorphic solution. So some of my works, we have already found out a meromorphic solution for differential equations like Stewart-Ladder equation by using the nonlinear theory. And also we have found out a meromorphic solution for cubic quintic Ginzburg-Ladder equation, which are arising in nonlinear dynamics. And also we have found out a meromorphic solution for a class of nonlinear differential equation. We are going to consider a condition that the meromorphic function and its derivative will share the value one counting multiplicity. And also we have imposed that condition that meromorphic function and its derivative with one ignoring multiplicity.
Yes, sir. So can you give me the exact number of participants, paper presenters?
And also the
no?
There are some more papers which we have published on finding the meromorphic solution for nonlinear ordinary differential equations, and also finding the solution for Q-shift difference equations, and existence of meromorphic solution for Riccati-Abel differential equations. So these are the previous works on the ordinary differential equation, that is finding the entire or the meromorphic solution. So now the ongoing work is we are finding the solution for system of partial differential difference equation and meromorphic solution for system of partial differential difference equation of a Fermat type. And next also to find out a solution for Q-shift differential difference equation. So in a complex differential difference equation, we are going to introduce the shift and to find out whether the solution exists or not. And also in order to find out a solution for Ginzburg-Ladder family of equations with a variable coefficients by using the nonlinear theory. So there are some open problems on this complex differential equations. So we can take an problem is differential equation as in 27. So we can pose a question that is it possible to characterize the transcendental entire function, that is the a of z, so that the equation 27 will possess two linearly independent solutions f and g, where the lambda of fg should be less than infinity. Here that lambda denotes that it is nothing but a exponent of convergence of zeros of f and g, and multiplicity are counted. Next is it possible to have the more explicit form of non-constant polynomial a of z, so that equation 27 will have a solution with an infinite number of real zeros and at most a finite number of non-real zeros. Likewise, we can take one more problem is the differential equation as in 28 with n is greater than or equal to 3. So this will have a solution with at most m meromorphic solution, where m is nothing but less than or equal to 1 plus n minus 1 times d square minus d plus 1. Now, is it possible this equation 29 can be improved for d greater than or equal to 2? Here d denotes that it is the number of zeros of the polynomial p suffix n of z. And likewise, there is a problem on a Fermat type equation. Here, f, g, h are the complex functions. So now this equation 30, we can pose a question that whether there exist a non-constant entire solutions f, g, and h for the Fermat type equation. And also we can check whether there exists a non-constant meromorphic solution f, g, and h for the equation 30. And is it possible to have the non-constant polynomial solution f, g, and h for the Fermat type equation as considered in 30? So these are the some of the open problems on complex differential equation. There are numerous number of problems are there. One can refer and start working on this problem, and you can publish good papers on this topic. So I will give the details about the journals where they are considering they are accepting the papers on the complex differential equations. So you can publish a paper in the Elsevier journal like Applied Mathematics and Computation, and also Computational Methods and Function Theory, which is publisher is the Springer, and next is Complex Variables and Elliptic Equations in the Taylor Francis group. And also one more Elsevier journal is Journal of Mathematical Analysis and Applications, Journal of Contemporary Mathematical Analysis, which is publisher is the Springer, and also the Mediterranean Journal of Mathematics. And also nowadays Proceedings of London Mathematical Society, they are also publishing the papers on the complex differential equations. So now coming to the references, you can refer the paper on Neven-Linear theory for Q-shift difference operator and meromorphic solution of a Q difference equation, where they have considered the Q-shift difference equation and found out a meromorphic solution with the Q difference operator. And this is published in Proceedings of Royal Mathematical Society in the year 2007. And also the second one, Gav have obtained the entire solution for the system of complex differential difference equation in the year 2016. And next is Shu have obtained the meromorphic solution of nonlinear partial differential equation of first order. And this has been published in a Journal of Mathematical Analysis and Application in the year 2011. And next is finding the meromorphic solution for a complex differential difference equation. So along with the complex differential equation, they have considered a difference term, so that they have obtained the meromorphic solution for this type of equation, and it has been published in Results in Mathematics in the year 2017. And also the author have obtained the entire solution of some differential difference equation, which is published in the Computational Methods Functional Theory in the year 2013. And next is finding the solution for a complex Fermat type partial difference equation, and also the Fermat type partial differential difference equation. And that has been published in Mediterranean Journal in the year 2018. And also finding the entire solution for several system of nonlinear difference equation and partial differential difference equation of the Fermat type. So likewise, there are already the works going on the finding the solution for a differential equation, differential difference equation for both ordinary and the partial. And also nowadays, people are finding the system of partial differential difference equation with a cube shift. So this is about my talk, where we can pose a question that for if you take a variable, complex variable as a purely real one, then we can say that there exists a real meromorphic function having a real poles. So from which we can conclude that there exists a real meromorphic solution for a complex differential equation. There are numerous methods developed by the mathematician in order to find a solution for a differential equation. But when it is a highly nonlinear, there is no unified technique that one can apply to handle a nonlinear differential equation. So from this, we can see that nonlinear theory is going to be the powerful mathematical tool for solving the differential equation which are appearing in the mathematical physics. So with this, I'll conclude my talk. If there is any question on this topic, it's welcome.
Thank you, ma'am, for delivering that talk on complex differential equations. Participants, if you have any questions, please feel free to unmute yourselves and ask ma'am. And those who are streaming this from YouTube, please post your questions in the chat box or the comment section.
Richa, I think there's no more clarification. You can just wind up. There's one from one question. They just see that.
Ma'am, Tanuja ma'am, can you see the question in the chat box? Dr. Twinkle Singh has asked, in the Fermat equation, are f, g, h functions of x or t?
Okay, in the Fermat type equations, f, g, and h, they are the functions of complex variable. So you can take that complex variable as a purely real, and that complex differential equation will reduce it to a real differential equation. So that is what in the beginning I have told. In order to find out a solution for a complex differential or the highly nonlinear differential equation, we are going to make you write the transformation in such a way that it will convert it into complex differential equation, and then we'll apply the nonlinear theory in order to get a solution for the real differential equation.
Thank you, ma'am, for answering that question. With this, we wrap up the session for Dr. Tanuja. Our next and final speaker for the day is Dr. R. Saurirajan. Pranesh, sir, is he here?
I think, madam, you are there, sir. I'm checking. 1 second.
Okay, sir.
Sauraji Rajan is there. You can just call him.
Okay. Okay. Tanuja ma'am, thank you so much for the presentation. We'll move on to the next session, which is the last invited session for today, which is, and our guest speaker is Dr. R. Saurirajan. Dr. R. Saurirajan holds MPhil and PhD degrees from Bharatiya University, Coimbatore. He is currently working as an assistant professor and the head of the Department of Mathematics at Dr. NGP Arts and Science College, Coimbatore. He has over 10 years of teaching experience and 3 years of research experience. Sir's areas of expertise are partial differential equations and mathematical finance. Under his supervision, 2 scholars have been awarded their MPhil degrees and 4 scholars are currently pursuing their doctoral studies. Dr. Saurirajan has several publications in reputed national and international journals to his credit. He has been invited to deliver lectures in numerous workshops, seminars, and conferences in established institutions all over the country. He has been serving as a member of the Board of Mathematics at Sri Ramakrishna Mission Vidyalaya College of Arts and Science since 2016. He has also authored a book on business mathematics and statistics, which was published in the year 2020. So without further ado, please please join me in welcoming our final speaker for the day, Dr. R. Saurirajan.
Dr. R. Saurirajan, can you share your PPT? Can you hear me, sir? I think he's not there.
He had joined, so I don't know where he went.
I think now he's
okay. Sir, we can see your screen now. Please go ahead with the presentation.
Maybe he's muted. Huh?
No, sir, he's not muted.
Sir, Dr. R. Saurirajan, can you hear me, sir?
Hello, sir. Technical issue for Dr. R. Saurirajan side, sir. Wait a minute, sir. It will be clear.
35.
Sir, any technical issues, sir?
Sir, now Sauri Rajan sir is added, sir. Just a minute, sir.
Okay.
Sir, your voice is not audible, sir.
மெசேஜ் பண்ணிருக்கீங்களா ஏதோ ஆக்கிரமிப்பு மிஸ்டீங்களா கலையாத செய்தி போட்டு
Is it audible now? Not audible, sir.
Am I audible?
Sir, yes, sir, but a little noise there, sir. Share, sir. It is shared.
Hello, sir. Sir, shall I start? Hello.
Yes, sir.
Hello, sir.
You can start, sir, now.
Okay, sir. Okay. Okay. Thank you. So, good evening to all. First time organizers for this opportunity to talk to you in the international conference of differential equations and mathematics. So today I have the topic on option pricing models and its in financial markets. So mathematics, I have chosen this topic. So I want to make this concept of option pricing, especially its application in financial markets. So option pricing is always used in financial market, and this field is very all over the world since
Able to hear me? Are you able to hear me, sir? Shall I continue? Hello? Hello?
Sir, your voice is not audible, sir.
Sir? Sir, no, sir. Sir.
Sir, am I audible, sir?
Yes, sir. Yes, sir. We can hear.
Okay, thank you, sir. Thank you. So sorry for the disturbance. So now I start the plan of my talk. So next slide, please. So next slide. So next slide, sir. Okay. So I have organized my talks in the form. First, I have to start with introduction, then the basic technologies in the financial markets, then the option pricing, common option pricing models, and then its effects on financial markets and recent developments. These are the 5 topics on which I have give some points today. So as we know, the financial markets forms very important role in the economy of any country, as you know very well. So in that financial market, we have to understand the logic behind the buying and selling of objects. Actually, the markets are of various types. So share markets, as you know very well, then commodity markets, and then currency markets, bond markets, etc. The markets are of many types. So first I have to give some introduction about option pricing, and then we move on to the next things, the types of markets, etc. So what is meant by option pricing model? Why are you using that model? As you know very well, modeling means mathematical modeling, because each and every problem in the real world can be modeled in some or another way using mathematics. So if that is the case, so previous slide, sir. Second slide, sir. Sir, second slide, not this, sir. Back, sir, back. Yeah, yes. No, sir. So third slide from introduction. Come to introduction slide, introduction. Yes, sir. Yes, that's it. Yes. Right. So why are you using the mathematical modeling? As you know very well, every real problem can be converted in some form of mathematics in order to get some solutions. What is the need for modeling? To get solution of problems, complex problems. So that's why. So here, this option pricing model refers to the pricing the option that I will explain you later, what it means by option, etc. So this option pricing model is nothing but a mathematical model which is used for calculating the theoretical value of an option. So what is the theoretical value? It gives an estimation. Theoretical. Why are you using the word theoretical? That's very important. Here we are not using the accurate value. Here just a theoretical. Theoretical means it may change. It may change. So it will give just a fair price. Just fair price. In other words, you can say it's just approximation. Here everything is approximation, not accuracy. Here everything is approximation. So in one or another sense, you can say that this is just a prediction method. This modeling, this equation is nothing but a prediction. You have to predict the value. You have to predict the value for future on future date. What will be the value of this thing X on after 1 month, after 1 year, like that. And in another sense, it can be used as directional strategy or hedging. That I will explain you later. Directional strategy. It will give you some direction. So these are the common meanings of option pricing models. So generally, the aim of the option pricing model will fix into some of these meanings. So next basic terminologies. So underlying asset. So before going to the terminology, just I will give you an example of how to understand the terminology of option. So let us assume that we are visiting a shop for buying some product. That product may be A, B, C, or some other thing. Some product. Let the person tells that the price of that particular product is 100 rupees, but you feel that this is very much higher because you want to buy the product regularly. From that day onwards, you want to buy it regularly. Let us assume that for 1 year you want to buy that product regularly. In that sense, if the shopkeeper gives you an option, if you buy this product after 1 month, then the amount of the product will be just 80 rupees. I will give you this product for 80 rupees after a month. After a month, because you are feeling that this price is very high now. 100 is very high now. So after 1 month, I give you the same product at 80 rupees per kg. It's per kg. But the condition is you have to give an amount of 5 rupees per kg now itself as an token, as an advance. In the financial terminology, it is a premium. So you have to give 5 rupees. After 1 month, if I want to get 10 kilos, then if you give at the rate of 80 rupees, you will buy it at 800 rupees. 800 rupees, excluding the 5 rupees what you get. So for 10 kgs, 50 rupees. So totally you have spent 850 rupees if you accept the option given by the trader, right? So in case after 1 month, if the price of that product comes down to 75 rupees, so what will you do? That will be the question. What will you do? You have already gave him 10 into 5, 50 rupees as the premium or some other thing. You are given 50 rupees. But now the price is for 10 kg, 750 rupees only. 750 rupees only. So if you come to the trader, what will say? The price is 80 rupees because you already gone into an agreement. That is 80 rupees. You have to pay 800 rupees for 10 kgs. If you say that we won't buy, you will lose that 50 rupees. You will lose that 50 rupees. What will be your decision on this particular situation? So 750, 50, 800. If I buy those 10 kgs, I will give 800 rupees. Already I gave 50 rupees, so 850 rupees. If I buy in some other trader, I will get those products at 750 rupees. If I buy this with this particular trader, I will get pay nearly 800 rupees. Will this be a loss or a profit? That the question will arise. Okay, so listen. Here, the amount that you will pay, 5 rupees, that I called as premium, that thing is called as an option. That is called as an option. Option pricing theory is nothing but you want to find the option of any agreement. In financial term, option refers to the agreement between the buyer and seller. So this agreement is just a right. It is a right, not an obligation. That means it is not necessary to exercise this option. It is not necessary to exercise this particular option. So what it depends on? That is the question. Underlying asset. Underlying asset is nothing but the product under which you are constructing the agreement. That is the underlying asset. The product under which you are constructing the agreement. You are framing the agreement, or which you have to sell or which you have to buy. That is the underlying asset. Derivative. So derivatives, so as usual the name refers to, it is nothing but the asset which will depends on some other quantities. For example, if I take some food product, it depends upon the date. It depends upon the time. It depends upon the time because it's not possible to use that after some particular time. Everything has its expiry date or best before date, like that, you know very well. So that is the derivative. These things asset depends on some factor. That is derivative. Then options. Option is nothing but the obligation. Electronic markets. So I'm not coming in order because these three things depends upon that product. Now electronic markets. Why I'm giving the name electronic market? There are more markets there. Starting from 1700s in US and UK, they formed these type of markets. So as you know very well, action, that's called as action in India. So they started with that and they slowly entered into the electronic markets through telephone, through the invention of telephones, and then moved on to the over-the-counter markets that we are seeing today, using both phone as well as computer internet facilities. So this slowly from the auction in the general place, it come into the building, inside the building. That's called a share trading center or share exchange, like what you can say, or stock exchange like that. So even though these two depends upon electronic, we are saying that electronic markets refers to the markets of the mid 19th century, which took place after the invention of telephone. Right? In order to avoid some problems in the electronic markets through the marketing through telephone, this over the counter markets was initiated, and now it's moving on with other facilities. Anyway, forward contracts. The contract is nothing but contract between two persons that I will buy this product after 1 month. That is the contract. Payoffs. Payoffs refers to the profit. So now, where will the problem come? That is the question. Where will the problem come? What are these? We are looking these base terminologies, and there are some other terminologies that I will explain later. Where the problem will rise. As I told you in the example, if it is 75 rupees, I will get those products from the other person, other trader, it will be 750 rupees. From this fellow, if from whom we have I've gone into an agreement, I have to pay 800 rupees. If the price of the product in the other market is lesser than 70 rupees, for example, let it be 50 rupees. What will happen? For 10 kgs, it is 500 rupees. If he exercise his right, what happened? He will pay 800 rupees. So premium is 50 rupees plus 850 rupees. So this buyer will incur a loss, whereas the seller will get the profit of 300. So these type of things will happen in the markets. When will this kind of things will happen? If the buyer or seller does not know the actual happenings or the actual product, the behavior of the product. Behavior of the product means price of the product. Price of the product, whether it will come down or go up. If the seller or buyer does not know these things, what will happen? This type of problem will take place. Either one of them will incur a huge loss. So there are many other external factors. We don't bother about this. So these errors will happen due to the inability of those persons to study the behavior of the product. So during up to 1950s, these things have happened. Even though we invented computer at that time, and the telephone exchange plays a major role in the stock exchange, these problems arise. So huge losses or huge profit take place. In addition to that, they will record everything. They record, if I speak some to stock exchange to fix the price, they will record it, because due to the fact that sometimes someone will negate the things. Negate the things means they won't accept. We have accepted for these rupees. They won't say. We won't say like that. So due to that, everything will be recorded in those days, in the 90s, 50s. So after that only, the researchers and especially the economists started to think of some particular models. We need some model which may give some values. If I want to find the option price, I need some accurate or approximate value, so that I can fix. So how can I find approximate value? Some modeling, because during that stage only the mathematical modeling came into existence. Therefore, they tried for that. See, in this figure, options are generally of two types: European option and American option. So what is the European option? For example, in the exam, I told that after 1 month, I will pay this amount and get the stock. So these can be exercised only after a month, only after 1 month. There are 30 days in between. You can't do that. If the price is very less, or if the price is very huge, it's not possible to exercise that option. This option can be exercised only after a month, only after the fixed time. That is called as time of expiration. Time of expiration. Only after the expiring of that particular time. Whereas American option is different. You can exercise this option at any time. That option at any time you can exercise. For if it is 30th day, you can exercise that on the second day itself. For example, if a product is selling at the price of 50 rupees per kg in the market, if I am the buyer of the product, if I comes into agreement with the seller of the product that after a month I will get the same product at the price of 60, and I will pay him a premium of option 2 rupees or 3 rupees, etc. Let I buy 1000 kgs, right? So after a month, if the actual price of that particular product is 50 rupees, itself, I have agreed to buy at the rate of 60 rupees. But after 1 month, the price of the product is 50 rupees only. What will happen? So whether I exercise this option or not, because it is of 1000 kgs, rupees 10 per kg is higher. That means it's 50, but I agreed upon 60. So what will happen? 1000 into 10, 10,000 rupees. I will incur loss of 10,000 rupees if I follow that agreement. So what will happen? I just cancel that agreement. I do not honor that agreement or obligation. So the seller will keep it as it is. He don't worry, because for 1000 kgs, I already paid him 1000 rupees as the premium. Minimum 1 kg, 1 rupee means it's 1000 kg, 1000 rupees. So he already had a profit of 1000 kg, but I already incurred a loss of 1000 rupees. So I get that product from some other one at 50 rupees per kg, and what will happen? I have reduced my loss. That's all. I have reduced my loss. This is for European option. Let us assume that in the 15th day, if that price of the same product is 75 rupees, what will happen? What will I do? I try to exercise that option because I have agreed upon 60 rupees. If I buy that thing for 60 rupees, 1000 kgs for 60 rupees per kg, what will I do? I will immediately sell to some other one at the price of 75 rupees. So 15 rupees profit per kg. 15 rupees profit per kg. So this kind of situation is not possible in case of European option. But in case of American option, I can do, because American option can be exercised at any point of time within the time of expiration. I can exercise that right. So here I'm using the word exercising the right. Okay. So American option can be used. Okay. Look at the other version. If I am the seller of the product, so after 1 month, the buyer is agreed upon 60 rupees. He gave me 1 rupees per kg. So I'm now having 1000 rupees. Okay. In the 15th day, if the price is 75, if he wants to apply that right, what will I do? Because it is already selling 75 rupees. That fellow has agreed upon 60 rupees. So if I gave him, what will happen? I will incur the loss of 15 rupees per kg. Because if I sell it in the open market, I will get 15 rupees. So whether I will honor that agreement? No. If I am the seller, I won't honor the agreement. Clearly. So what will I do? I will look for some other option. What are the options available? I will give him some amount as a penalty and ask him to cancel the agreement in such a way that both of them will be benefited. That's all. Both of them will be benefited. That's why I tell that option is just an agreement. It is just a right, not the obligation. It is not the obligation. Okay. Here there are something: call option, put option, knockout option, interest rate option, etc. These are all types of options. European call, European put, American call, American put, European barrier, European knockout, like that. So European and American option are very base, and frequently all over the world they are using type of option. You may ask whether there are Indian options or Asian options. Yes, there are. Indian options are there, Asian options are there. Every country has its own option. But in generally, since this is globalization, everything depends upon European and American. As you know very well, from the example that I told, American option gives more profit than the European option. the returns. In other words, it is called as returns. Instead of profit, they will tell us returns. The returns, American returns, are very much higher than the European returns. So that's the proved one. So call option means I am buying something from some other, agreement on buying the product. Whereas put option is agreement on selling the product. Whereas barrier means based on some fixed value, like that interest and knockout. So generally used options are call options and put options alone. Barrier options, knockout options are very much rare. They are only a few persons are using those. It's not possible for them to use regularly, like this call and put. So next, sir. Sir, am I audible? Sir? Oh, yes, sir, that's it. Yes. So now in this talk, I will give some details on the two types of models. One is binomial model and another one is Black-Scholes model, because these are the model under which the latest developments are done. These are the basis. That's why I'm giving these two models. So binomial models. So as name represents, it depends on two, binomial. It depends on two values. In other words, if S naught, if you see the figure, you find it. So if S naught gives the price, stock price at today's price, in other words, today's price, what the condition is, either these may goes up or goes down. Goes up or goes down. That you know very well. It may goes up or goes down. So S suffix U represents to the upper price. For example, if the product is 100 rupees today, it may go up to 125 rupees or come down to 75 rupees. How do you fix these two things? By the experience on the behavior of the stock, of that particular stock. I can say that these may go up to 125 rupees or these may come down to 75 rupees. So these things are to be analyzed. How we can analyze? As you know very well, there are brokerages, etc. They will analyze these things in detail. But as a common person, if you go through the website of any particular company, any share limited companies, you can find these regions. So it may goes to 125 or it may come down to 75. Therefore, this binomial model depends on two values, up price as well as down price. Up price and down price only. It won't allow other price to come within it. Then the other assumption is market is frictionless. So what is the meaning of frictionless? So no effect no external force will affect the market. No external force will affect the market. Market means its price. No dividends is given to the investors. Investors are risk neutral. Here it is not riskless, risk neutral. So risk neutral, what it means, I am said to be a risk neutral investor if I fix the highest profit as well as the least loss. In other words, loss. I can manage this profit as well as this loss. If I fix those things and invest in shares of some company or some firm, I can say that I am the risk neutral investor. There are two types. Riskless investor. Riskless investor means, for example, if you are able to deposit an amount in a fixed deposit or in certificate, in national savings certificate, etc., they are called as riskless deposit, because that is also a market, bond market. That is also bond market. So I will deposit some amount, after 1 year or 2 years, they will give you interest and I will get it back. They are riskless deposit. Riskless deposit. Risk neutral means I will find the amount which is manageable by me. Which is manageable by me. So if I'm able to find that amount, and based on that, if I invest in some shares, then I can be say that I'm the risk neutral person. Risk neutral person. So usually these risk neutral persons will invest in shares or stocks in which they know the upper value and lower value of the stock based on the performance. Where it reached its upper value. If the stock is 100 rupees, you will see the face value of each share. Each share has its face value. Based on the face value, they'll find the higher value and least value they reach. For example, a motor company in India introduced it during the COVID time, their price is 70 rupees per share. 70 rupees per share. Today, the price of that same share is 300 rupees. So if the investor bought that shares, 1000 shares or 1 lakh shares during that period, now you see the profit of that, out of that shares. So 70 rupees per share, now it is 300 per share, nearly 200 plus rupees are increased. Value is increased by 230. If I bought 10 shares, I will get 2300 as profit. If I bought 100 shares or 1000 shares, the profit will increase exponentially. So likewise, if I know the performance of that company, if I closely monitor the performance for at least for a year, then I am able to guess what will be its highest value, what will be its least value, if it is manageable by me or not. So this can be done individually or based on the advice given by the brokerages. You know how the brokers will give the advice. There are many share companies out there. How they give the advice? Based on the models. These type of models. Everyone is based on the models. Even they are analyzed using the manually. They will generally use the models. So if you visit some share companies, they will tell you how. So next. So there are two types of two-step of binomial trees. Two-step binomial trees. So this is application of a graph theory. As you know, this is the application of graph theory. So starting from the S0, that is the basic price. It can be fixed. There are levels can be fixed. Time 1, t equal to 2, t equal to 3, etc. So the levels can be fixed, or in other words, it is called a step. Steps can be fixed. So each step has its own value. So under what condition these steps are fixed? That would be the question. Under what condition these steps are fixed? That is based on the probability. That is based on the probability. So here the probability comes into play. How will you fix the probability? That will be the next question. How will you fix the probability? So based on the behavior. So for example, if a share costs some amount, X amount today, and if the highest amount is Z and the least amount is Y. So based on the data available, it is possible to find the probability of reaching the highest amount and probability of reaching the least amount. If I find the probability of finding the highest amount, then from that 1 minus that probability will give the probability for getting the least amount. So this is through the analyzing the data for some period of time. So larger data time means you get more accurate data, more accurate, not accurate, just somewhat more accurate data. Otherwise, you get least. So based on that, it is possible to find the probability. Based on that probability, here the steps are defined. Here the steps are defined based on the probability. So if you are able to find these things, then you can invest. But the right hand diagram, comparison of real world and risk neutral world. So real world data and risk neutral world data. So nearly more both of them are same. So if you know the probability, but here there's some simple star is included. So star is included means there may be some point of error in that. Some point of error. That won't be large. Some point of error exists. So if you see this model, you can say that okay, this will be the right model. It may give accurate result, but not so. This not give accurate result because so probability may be fixed, but it may change time to time. It may change time to time due to the external problems. So during the last year, as you know, all the company shares came down heavily. That's what I told you. One company share came 70 rupees. Now it is 300 rupees. But the face value of that share is 200 rupees. It came down to 70. So the reason is due to the lockdown, no sales, etc. That is not, it is not possible for you to control that. It happened. Right? So you can't fix that probability. It may have nearly 0.9 before that particular situation. But during that situation, it came back to nearly 0. And again, it start rising. So that's chart. This is uncertain world. We can't fix, we can't control the external factors. That's main thing. External factors. You may ask that is there no internal factors? Yes, there are internal factors. There are internal factors that we'll see later. So due to the external factors, this will happen. So next. So next, please. Next slide, sir. Okay. So there are some limitations that I will tell you then. So here the computing speed is slow. What in the computing speed? T equal to 1, you can calculate. T equal to 2, you can calculate. So there are 2 power 3 nodes. Finally, there will be 2 power 3 nodes. So in case if it is T equal to 10 or 20, that will be a huge tedious process. Therefore, its speed is very, very slow. In case of multi-period binomial, this is for single period. In case of multi-period, the process will be very much tedious. That's why due to these limitations, binomial tree model is not of preferred, not a preferred one. Next, Black-Scholes model. So this is the most important model which is used even nowadays. You may say that this most important means it is more accurate. Just as per the record, it is up to the accuracy level of 3%. So 3% is very less, but without, we don't have anything to measure up to that mark until now. That's why this is a Black-Scholes model is derived in the year 1973. It is derived, and for this particular equation or model, Fisher Black and Myron Scholes received the Nobel Prize, not in maths, in economics. They are economists, but they derived the model in partial differential equation. Okay, anyway, so coming to this price depends upon these 6 factors: volatility, its type means call or put, underlying stock price, strike price, time, and risk-free rate. Everything is considered as a constant here. Constant, they are not variable. What is volatility? That is the uncertain thing, uncertain happening. In other words, in the mathematical sense, I can equate this with variance, as you know, variance. Then type call or put, underlying stock price, that is the current price. Strike price means the price that I will fix, which will be exercised after some period of time. If I say that I will buy it 60 rupees per kg, that is called a strike price. Next, time, short time or long time, 1 month or 1 year or 2 years, like that. Risk-free rate. Risk-free rate. What is risk-free rate? I will get the profit. I will get the profit. I can simply say that I will get the profit. Risk-free. That's why it's called as risk-free rate, based on some percentage. So if I invest 1 lakh rupees now, definitely after some period of time, I will get at least 5% profit. So next assumptions. So these are the assumptions. That's why I explained you. This follows log normal distribution. Normal distribution. This is the main, again, the application of normal distribution. Short selling. What is meant by short selling? So very simply, I can say, in case I am analyzing some set of stocks, and I find that a stock of a company D will increase by this year end, will increase within 2 months. That means assume that now the price is 50. Based on the analysis done by me, if I say that it will reach 150 rupees, what I will say, I will come into agreement with some person. I will come into agreement with some person that I will sell the stock by 100 rupees after 2 months. But now at present, I am not having any share. At present, I am not having. So what I will do, that I am not having, but I will give you this amount of shares without having anything. So what I will do, again, after that particular period of time, he will give me some premium. As you know very well, he will give me some premium. During that particular period, if the stock price increases, what he will do? Either he will reject that option. He will reject, because In case if the price is very less, he will buy it directly. He will reject. So I will get the profit. I will get the profit. In case if the price reduces, then the exercise price. Right? For example, if the actual price is 150, and if he came into agreement with me with 200 rupees, he will incur a loss. So he will cancel that right. So the premium is with me. Without having any share, I'm getting the profit. In case if the reverse process, if he wants that share, if he want me to give that, what will I do? I will borrow those shares from someone and hand it over to him. Borrowing, it is allowed. Borrowing of shares is allowed. That is short selling. It is allowed. So there is no transaction cost. There won't be any dividends. Dividends means once the company will come into profit, they will divide their profit in shares and give it to the shareholders. That is usual thing. No riskless arbitrage. Then rate of interest and volatility is always constant. Process is always continuous. So these are the assumptions implied on the Black-Scholes model. Only based on these assumptions only the Black-Scholes is derived. Otherwise it's not possible to derive. Everything is constant, everything is risk-free, and you will get the exact value. That is the idea behind this Black-Scholes. So before this there is no model, except binomial there is no model. Since it is continuous, why this is given continuous? Continuous means it is, if you have the least limit as well as a maximum limit, that's enough. It is possible. You not worry about the amount of limit. It may be 0 to 100 or 0 to 1000, like that. It may be any number. Whereas in case of discrete or binomial model, as I already told you, if the level is 3, 4, 5, etc., and if it goes on 10, it will be tedious process to calculate. Whereas in case of continuous, that's not so. Therefore, continuous is accepted, and therefore that's possible. Then only this PD is derived. Anyway, arbitrage, that's another thing. As I already told you, there may be some internal thing. Arbitrage, short selling, more or less related, interrelated. It represents the same thing. If I come into arbitrage, I won't lose any money, anything. That is the meaning. Next, sir. So this is the Black-Scholes model. So dou v by dou t plus of sigma square s square dou square e by dou s square plus this. So here v represents the option price. That is the premium that is to be calculated. Sigma, volatility term, in other words variance. Yes, the stock price, current stock price, or risk-free interest rate. This is the Black-Scholes model. This is the partial differential equations of second order. Hence, it can be solved. It can be solved. I am considering only the call option, not the put option. It can be solved. The following equations gives the solution. Following equations gives the solution. So here it involved logarithmic term and d2 equal to x. These things are possible since we are assuming that it follows log normal distribution. Log normal distribution. That's why it is possible. Okay, you are having the solution. You can substitute and find the result. Right. Everything is right. Now I kind of find the option price. As I already told you, the accuracy is 3%. Based on the, since sigma s everything is constant, if you change the value, you will get different result. If you can change time, you will get different result. So for each data, there are some softwares available for finding the Black-Scholes model, Black-Scholes value, option price value. You can try in MATLAB or some other thing. So you find that you can get different predictions or option price for a single data. For a single data, you can get different type of predictions. So if it is so, how can this be accurate? How can this be accurate? No, it's not an accurate one, but somewhat it manages. It is possible to manage. It is possible for me to get some information, because as you know that something is better than nothing. Therefore, some information I can get, I can predict. Based on that, I will invest. Right. So next. So what are the limitations? So due to some time constraint, I'm just giving you the points. So this is restricted to European markets only. In case of American, it is not possible. It's restricted to European markets. At the risk-free interest rate, it is not at all possible. Risk-free interest rate is not possible. So there will be risk. Without risk, there is no market. So definitely there will be risk. So risk-free interest rate is not possible. Next, frictionless market. That is also not possible. There will be friction. There will be some problems in the market. Up and downs, everything will happen. There are external factors. These are no way we go to practical markets. Next, no returns. Again, the same thing. So these are the sum of the major limitations. Next. Okay, so these are the models. These are the basic models and mostly used common models available on the markets. In what way these affects the financial markets? As an investor, if I know that if I use this model, I will get some value based on that I can invest. What will I do? In case if I am a starting level investor, what will I do? Just simply I will invest. I will start invest. So by just seeing that model, I will start invest, or based on some suggestions given by some brokers, etc., I will invest. I don't know the actual thing. What it happened? So if you see the last 10 or 20 years, due to the globalization, this has increased. The trading has been increased. Trading means exercising the options. So buying and selling of shares have increased. And another one important thing, due to the development in information technology, this is also one important factor for increase in trading. Everyone with your system in home or even with your mobile, it is possible to calculate the option price, predict the option price, and you can invest. But it's not possible to check the accuracy, right? Only after the particular time of expiration you can find. Next, increase in arbitrages and hedgers. Hedgers, that's the most important concept, hedging. So just I'll give some outline about that as I crossed time. Anyway, hedging is nothing but, I already told you, short selling and arbitrage. So for buying some kind of shares, I will create a portfolio. What is a portfolio? Portfolio is the combination of shares, stocks, bonds, certificates. In common, in one word, I can say that it is the investment done by a person. So if I am that person, my investment is my portfolio. So just considering only shares and stocks, how many shares that I am having, how many stocks that I am having. What do you mean by shares? The shares, now I am having stocks. I can buy shares or sell the shares. I can buy the stocks or sell the stocks. So here stocks refers to anything, even commodity or like that also. It may include anything. So that forms a portfolio. So to avoid the loss, what will some person do? He will sell the shares, or he will buy some particular shares. At the same time, he will give the put option that he will sell the same shares at some price to avoid the loss. That is one of the process, hedging. It is a very, very big theory. So this particular process is used to reduce the risk in the financial markets. So most of the investors will do this. If he is very much thorough with the markets or the behavior of the markets, he will definitely do this hedging. Delta hedging is the most important tool in reducing the risk. In risk management also, you will study these things. This forms a very huge part of the financial market. Hedgers, arbitrators, the hedgers, the person who arbitrage or who performs hedging is called as arbitrators and hedgers. So it is increased. So now the researchers, there are 3% only, accuracy is up to 3%. So what they are doing, they are analyzing and again constructing the model based on black scores. So already based on black scores, there are many models are there. That's why I'm giving only black scores only. There are many models. For every day, their model is created by including some terms or by changing the constitutive variable, etc. Every day, a model is created using black scores. So performance of a firm can be analyzed. So that is increased. Instead of going to brokers, if I want to invest on my own, I can validate the performance of the firm by seeing the details on that website of the company. That is mandatory, as you know very well. So based on that, I will see the details. If I'm able to grasp those things within some short period of time, I will be a good investor. Good investor means I will reduce the loss or I can get some profit. Another thing, investments are increased. Investments in shares. Nowadays, government agencies are also investing in shares, as you know very well. So due to these things, due to some predictions, they are investing the money in shares. Even they are some public sector things, some public sector companies, undertakings, or the investment value, they are validated and they are selling them in shares. So whole company of the whole value of the company is split into shares and are given in markets, as you know very well. So next. So what are the developments? So in order to avoid those things, those shortcomings, what happened? Again, they are restarting their work on modeling. So as you know very well, as I told you, volatility is the most important factor, very important factor. This volatile situation, as you know very well, this is an uncertain situation. So what they are doing, they are giving more preference to the volatility. There are some kinds of volatility, implied volatility. So treating in reverse process. So that's got implied volatility involving stochastic forms of parameter. I have not given the proof of black scores while deriving the black scores. So while deriving the black scores, the most important thing is it involves probability. You can ask how it is a probability statistics, how the determinant, but the equation deterministic equation, but the portfolio etc. means that is purely uncertain. How will you link that? That is true Ito's lemma. So only by that stochastic equation it is possible to derive the deterministic form. That will take more time. Next, modeling through jump process. Jump process means involving the uncertain quantities, uncertain things inside the Black-Scholes equation. And using the theory of artificial intelligence like vector machine etc. That's upcoming area in the field of financial mathematics. That's very big area, and now machine learning is also used to get the somewhat good result in the field of option pricing. Parameter identification, that's also a new area. Parameter identification means based on the option price, it is possible to find the volatility or some other term. So keeping the data or collecting the data of option price and for which option you get different volatility, based on that it is possible to predict. That is also very new area, and this is very emerging area. At least the last two things, artificial intelligence and parameter identification, there are a lot of opportunities available for entering into the research in these areas, as the research analysts in these fields are most wanted all over the world, especially research analysts in these financial markets. So if you are very much interested in these things, you may study this on your own. You see there are many lots of articles are available even from the net itself. So these are my references. So as the time is very short, I'm unable to complete. I'll give you the details. Next. Thank you very much. Thank you for your patient hearing. So due to the net connectivity issues, I am unable to present all the things to you. Just I have given you a glimpse of those things that I have prepared. So thank you. Sir, any questions? Any queries?
Thank you for the insightful lecture, sir. Participants, those who have queries, please feel free to unmute yourselves and ask your questions. And those who are watching the lecture on YouTube, you can post your questions in the chat box or the comment section.
Hello. Hello, sir.
Hello.
Sir, which time we will start from validity function?
We'll start, sir. It's already late now.
Yes, sir.
Within
1 or 2 minutes?
Yeah, 1 or 2 minutes we'll start. In 2 minutes we'll start, sir.
Yes, I will invite our secretary and the principal.
Once if they come, you just inform me, I'll start.
Yes, sir. Thank you.
Sir, any queries, sir?
Sir, sir, once again.
Somebody is asking that interdisciplinary work can do with this concept.
Yes, sir. This is a interdisciplinary only. Actually, it's a combination of mathematics, statistics, and economics.
Or Singh is asking.
Yes. So this is the interdisciplinary only, sir. As I already told you, this is our work is mainly done by the economists. But actually, in the Western countries, they will treat the maths and economics as a same part. They will study the dual course like that only. So that's why I'm able to do these things. But this is the interdisciplinary only, sir. But more than one problem: maths, economics, statistics, and nowadays artificial intelligence will come into this.
Thank you, sir.
Any other, sir?
Yeah, I think only that much questions they asked, sir. Only one question. Thank you very much, sir.
Thank you, sir. Thank you very much.
Thank you for your nice, wonderful lecture.
So thank you very much, sir. Thank you all for your patient hearing, and I'm sorry for the frequent interruptions. Thank you very much, sir. Thank you. Thank you.
So can we start the function, sir?
Start So we can start the program, sir.
You can start, sir. Okay. Answer. Answer, Matthew. Yeah.
Yes, sir. Am I audible?
Yeah.
To improve the golden moment of opportunity and catch the good that is in our reach is the great art of life. A very pleasant evening to one and all present here. I, Ansa Matthew, research scholar, Department of Mathematics, Christ, deemed to be University, feel privileged to welcome you all to the valedictory function of the two-day international conference on new trends in differential equations and applied mathematics, ICNTDEAM 2021. Organized by the Department of Mathematics, Sri Vidya Mandir Arts and Science College, Tamil Nadu, in collaboration with Department of Mathematics, Jyoti Engineering College, Thrissur, Kerala, and Department of Mathematics, Christ, deemed to be University, Bengaluru. I extend my heartfelt welcome to our chief guest, Dr. Mayama Joseph, Head Department of Mathematics, Christ, deemed to be University, Dr. T. Balasubramaniam, Principal, Sri Vidya Mandir Arts and Science College, Tamil Nadu, and Dr. N. Gunashekharan, Vice Principal, Department of Mathematics, Sri Vidya Mandir Arts and Science College, Tamil Nadu. Also, other dignitaries, Dr. S. Pranesh, Department of Mathematics, Christ, deemed to be University, and Dr. Smita S. Nagoda, Department of Mathematics, Christ, deemed to be University. Prayers work in miraculous ways and is considered as the harbinger of blessed beginnings. Thus, I request all of us to start a minute of silent prayer. The fragrance of flower spreads only in the direction of wind, but the goodness of a person spreads in all direction. Dr. S. Pranesh is one such inspiring personality who is highly passionate about delivering the best to students that could infuse hope among learners. I take pride in calling Dr. S. Pranesh, PT Coordinator, Department of Mathematics, Christ deemed to be University, to welcome the gathering.
Good evening, one and all. I deem it's a great honor and privilege to welcome one and all to this valedictory function. Any conference is an occasion for concerned scientists to get together and enlighten one another. The constant updation and upgradation of knowledge in any subject is extremely important, and conferences are the best way for carrying out the same. I'm sure that this conference has provided a forum for scholarly presentations of new research, stimulating discussions and exchange of ideas between the participants. It is our privilege and honor to have with us the distinguished chief guest, Dr. T. Balasubramaniam, Principal, Sri Vidya Mandir Arts and Science College, Dr. N. Gunashekaran, Vice President, Sri Vidya Mandir Arts and Science College, Dr. Mayama Joseph, Head, Department of Mathematics, Christ deemed to be University, Bangalore. On the behalf of the organizing committee of the conference and everyone present, I welcome all the distinguished chief guests. On the behalf of everyone present here, I extend a hearty welcome to all the resource persons from India and abroad. I now take pride to welcome Dr. C. Raghavan, Head, Department of Mathematics, Sri Vidya Mandir Arts and Science College. Welcome, sir. I extend a hearty welcome to conveners of the conference, Dr. S. Jaikumar and Dr. S. Palani, organizing secretaries, Dr. J. Satish Kumar, Dr. S. Muniratnan, and Dr. Joseph Varghese. A very hearty welcome to all the delegates with whose presence this conference could not have taken place. I also take this opportunity to welcome all the faculty members from Sri Vidya Mandir Arts and Science College, Jyoti Engineering College, and Christ deemed to be University. Last but not least, I welcome my dear students, volunteers whose dedication, efforts, and time has brought us to this day. I once again welcome each one of you present here. I remind thank you.
Thank you, sir, for such a warm welcome. A leader takes people where they want to go, but a great leader takes people where they necessarily do not want to go, but ought to be. Amongst us, we have one such enthusiastic leader, Dr. Mayama Joseph, who guides young minds to strive for excellence. I take immense pleasure in requesting our chief guest, Dr. Mayama Joseph, Head, Department of Mathematics, Christ deemed to be University, to address the gathering.
Thank you, Ansa. Am I audible, Ansa?
Yes.
Yes, ma'am.
Thank you, everyone. Respected Dr. T. Balasubramanian, the Principal, Sri Vidya Mandir Arts and Science College, Dr. N. Gunashekaran, Vice Principal, Sri Vidya Mandir Arts and Science College, and the team behind ICNTDEAM 2021, Dr. Muniratnam, Organizing Secretary, Dr. Pranesh and Dr. Palani, the conveners, Dr. Raghavan and his team of faculty members and students from Vidya Mandir, and respected resource people and esteemed participants. A very good evening to one and all. I'm certain that all those who had been actively involved in this two-day conference might be having a sense of delight in expanding the horizon of their knowledge, ideas, and networking. I was recently going through the latest All India Higher Education Survey of HRD, Government of India. According to the survey, the latest one, only 2.5% of the colleges in India run the PhD program. And if we look at the enrollments, the PhD students contribute only less than 0.5% of the total student enrollment. So it is important that a platform such as this should enable us to think and see what can we do to increase enrollment for the PhD program and hence improve the quality of research. So it is important that we come together. As we have already seen, research happens in collaboration. We have heard, starting from the fractional calculus to the economics application of differential equation, how collaboratively people are coming out with new results. In this context, I want to emphasize that the collaboration between Christ deemed to be University and Sri Vidya Mandir College also has to further have strategic plan that will yield good research output. And this time we had Jyoti Engineering College also. So let us look forward for more collaborative programs. As everybody would agree with me, the forceful confinement to our homes during this COVID pandemic phase of our human existence, we were also empowered to use different ways and means to get connected through technological tools. So I'm sure it is possible for us to effectively work together. Let this conference result in newer ideas, newer platforms, newer ways, and specifically, let us see more PhD enrollments and better quality outputs. Once again, congratulating and thanking all the professors who worked tirelessly behind this conference. I remain. Thank you. Thank you once again.
Thank you, ma'am, for your influential message. Nothing great will be achieved without great men, and men are only great if they are determined to do so. And amidst us, we have Dr. T. Balasubramaniam, Principal, Sri Vidya Mandir Arts and Science College, Tamil Nadu, who has been a source of constant motivation for conducting this event. Sir, I request you to say a few words.
Sir, you are muted, sir.
Yeah, sorry. Honorable founder, respected secretaries and joint secretary, distinguished eminent personalities, and invited speakers of this international webinar, Honorable Vice Chancellor of Christ University, Honorable Registrar, and faculty members of Christ University, respected Principal, Jyoti Engineering College, and faculty members of Jyoti Engineering College, our beloved HOD of Mathematics and convener of this international webinar, staff members of Department of Mathematics, Sri Vidya Mandir Arts and Science College, and participant of this international webinar. Good evening, one and all person here. It is my immense pleasure to have a felicitation over this international webinar on new trends in differential equations and applied mathematics. First of all, I thank our management and Jyoti Engineering College and Christ University to making collaborative to conduct this international webinar. Definitely, I hope in future we will have a good partnership for all activities of our development. I heard about that more than 10 personalities, eminent personalities have given lecture to this webinar. It gives the deep insight to the all participant and research scholars. I congratulate all the organizing team members of this international webinar. I convey my heartfelt wishes to all the participants. Thank you for the opportunity given. Thank you.
Pranesh?
Yes, sir.
Sir, we next invite our additional secretary, Mr. P. Venkadasalam, sir.
Okay, okay, sir. Okay, okay. Answer, did you note down? Okay, I now invite the Additional Secretary of Sri Vidya Mandir Arts and Science College, P. Venkateshwara, to talk few words about this conference. I welcome you, sir.
அனைவருக்கும் வணக்கம். ஸ்ரீ வித்யா மந்திர் கல்வி நிறுவனங்கள் மூலமாக 3 நிறுவனங்கள், கிரைஸ்ட் யூனிவர்சிட்டி இன் கர்நாடகா, in Jodi Engineering College in Kerala, in Vidya Mandir in Tamil Nadu, 3 நிறுவனங்களும் சேர்ந்து ஒரு உலகளாவிய இன்டர்நேஷனல் வெபினார் என்ற முறையிலே கணிதத்துறையில் மிக சிறப்பாக செய்ய வாய்ப்பளித்த இந்த நிறுவனத்திற்கு வாய்ப்பளித்த அனைவருக்கும் நன்றியை தெரிவித்துக் கொள்வதோடு, இன்றைய காலகட்டத்தில் கல்வியினுடைய வளர்ச்சி, அதைவிட அதில் ஆராய்ச்சி எந்த அளவிற்கு முக்கியத்துவம் என்பது மிக சிறப்பானது ஒன்றாகும். அந்த அளவிலே ஒரு நாட்டினுடைய உயர்கல்வி வளர்ச்சி பெற வேண்டுமானால் அந்த நாட்டினுடைய ஆராய்ச்சி மேம்பட வேண்டும். எந்த அளவிற்கு அந்த GDA என்று சொல்லக்கூடிய ஆராய்ச்சி பங்கு மாணவர்களிடம் ஆராய்ச்சி திறன் மேம்படுகிறதோ அந்த அளவிற்கு நாட்டினுடைய கல்வி வளர்ச்சி மேம்பட வாய்ப்பாக இருக்கிறது. டெவலப்மெண்ட் ஆஃப் இன் கண்ட்ரி, ஒரு நாட்டோட வளர்ச்சி கல்வியின் மூலமாகத்தான் முதலில் உருவாக வேண்டும். அதுவும் உயர்கல்வி இன்றைய காலகட்டத்தில் மாணவர்களுக்கு மிக ஒரு வாய்ப்புகளனாக அமைய வேண்டும். இது போன்ற வெபினார் புரோகிராம்கள், இது போன்ற நிகழ்வுகள் எல்லாம் இளம் ஆராய்ச்சியாளர்களை ஊக்குவிக்கும் ஒரு நிகழ்வாக அமைகின்றது. இதன் மூலமாக நிறைய மாணவர்கள் பங்கு பெற்று தனது திறமையை மேம்படுத்திக் கொள்வதற்கு இது வாய்ப்புகளனாக அமைந்திருக்கின்றது. உலக நாடுகளில் மிகச்சிறந்த பேராசிரியர் பெருமக்கள் மூலமாக இந்த நிகழ்வில் பங்கு பெற்று அரியதொரு கருத்துக்களை வழங்கியவர்களுக்கு அத்துணை பேருக்கும் எங்களது நிறுவனத்தின் சார்பாகவும் எங்கள் நிர்வாகத்தின் சார்பாக அனைவருக்கும் நன்றியை தெரிவித்துக் கொண்டு, மேலும் மேலும் கல்வியில் ஒரு மாற்றத்தை உருவாக்க இது போன்ற நிகழ்வுகள் செய்து காட்ட வாய்ப்பளித்தமைக்கு நன்றி கூறி விடுகின்றேன். நன்றி, வணக்கம்.
Thank you very much, sir.
Thank you, sir. I now call upon Dr. N. Gunashekharan, Vice Principal, Sri Vidya Mandir Arts and Science College, Tamil Nadu, whose guidance has helped at the various stages of the event, to say few words.
He is absent. You to move to the next guys.
Okay, sir. Okay. Answer next you.
Yes, sir. I now request our young and vibrant Dr. Smita S. Nagoda, Associate Professor, Department of Mathematics, Christ deemed to be University, to present the conference report.
Sir, can you mute Smita Saklesh Nagoda to? Can you unmute her, sir? Hello, sir.
Yes, sir. I think I'm audible.
Yeah.
Okay. Thank you, Ansa. Thank you, sir. A very good evening to one and all present here. This is a brief report of the International Conference on New Trends in Differential Equations and Applied Mathematics, organized by Department of Mathematics, Sri Vidya Mandir Arts and Science College, Krishnagiri, Tamil Nadu, in collaboration with the Department of Mathematics, Jyoti Engineering College, Thrissur, Kerala, and Department of Mathematics, Christ deemed to be University, Bengaluru, held during 12th and 13th April 2021. The inaugural ceremony was held at 9 a.m. on 12th March, followed by the welcome address by Dr. J. Satish Kumar, Organizing Secretary, Department of Mathematics, Sri Vidya Mandir Arts and Science College. The theme of the conference was presented by Dr. S. Jaikumar, the convener from Sri Vidya Mandir Arts and Science College, followed by felicitations to Mr. V. Chandrasekharan, founder, Sri Vidya Mandir Educational Institutions, R.P. Raje, Secretary, Sri Vidya Mandir Arts and Science College, Dr. T. Balasubramaniam, Principal, Sri Vidya Mandir Arts and Science College, Dr. N. Gunashekaran, Vice Principal, Sri Vidya Mandir Arts and Science College, Dr. Mayama Joseph, Head, Department of Mathematics, Christ deemed to be University, Bengaluru, Dr. C. Raghavan, Head, Sri Vidya Mandir Arts and Science College, and followed by vote of thanks by Dr. P. Palni, Convener, again, Vidya Mandir Arts and Science College. The conference provided a platform for researchers in emerging areas in the field of differential equations and applications of the same in multidisciplinary fields in mathematics. In these 2 days, researchers had opportunity to listen to eminent speakers from premier institutions from India and abroad. The keynote speakers were Professor Odi Makinde, Faculty of Military Science at Stellenbosch University, South Africa. He spoke on modeling thermal boundary layer of magneto-nanofluid with inherent irreversibility. Dr. P.G. Siddeshwar, Senior Professor of Mathematics, Christ deemed to be University, Bengaluru, spoke on making sense out of differential equations without solving them. Dr. Mahesha Narayana, Department of Mathematics, the University of West Indies, spoke on exact solution of boundary value problems arising from heat transfer in nano-liquid flow due to quadratically stretching sheet. Dr. Ishwari Prem, Assistant Professor, PG and Research, Department of Mathematics, Government Arts College for Men, Krishnagiri, spoke on the topic, a brief introduction to differential equations and application in mathematical modeling. Dr. Kanchana C., Research Expert, Instituto de Alta Investigation, University of Topeka, Chile, spoke on the topic, breakdown of regular convective motion to chaotic one at a threshold eigenvalue in hydrodynamics. Dr. Sunny Joseph, Principal, Professor and Dean of Research, Jyoti Engineering College, Thrissur, spoke on fuzzy modeling and decision-making applications in the real world. Dr. A.K. Abdul Hakim, Assistant Professor of Mathematics, SRMV College of Arts and Science, Coimbatore, spoke on Introduction to Computational Fluid Dynamics. Dr. A. George Maria Selvam, Associate Professor and Head, Department of Mathematics, Sacred Hearts College, Vellore, spoke on the topic Fractional Derivatives and its Applications. Dr. S.R. Sudhindra, Professor and Head, Department of Mathematics, School of Engineering, Residency University, Bengaluru, spoke on the topic Mathematical Modeling of Atmospheric Pollutions. Dr. S. Karthikeyan, Assistant Professor, Department of Mathematics, Periyar University, Salem, spoke on controllability of semi-linear stochastic models and dynamical systems. Dr. S. Karthikeyan, Assistant Professor, Department of Mathematics, RMK Engineering College, Kavarapetti, Chennai, spoke on functional equations and its application. Dr. A. Tanuja, Assistant Professor, Department of Mathematics, Siddhganga Institute of Technology, Tumkur, spoke on complex differential equations. Dr. Prakash R., Associate Professor, Department of Mathematics, RV College of Engineering, Mysuru, Bengaluru. He spoke on shooting method is a technique of solving boundary value problems by using the methods for solving initial value problems. And Dr. R. Soviranjan, Assistant Professor and Head Department of Mathematics, Dr. NGP Arts and Science College, Kalapatti, Coimbatore, spoke on option pricing models and its impact in financial markets. The conference brought together 1,328 participants from across India and abroad, and there were 70 paper presentations. The platform for all these were either Zoom meeting or WebEx. Overall, the conference provided an opportunity to bring together the experts, research scholars, researchers, and students to explore new developments in the field of differential equations and its applications in interdisciplinary fields. Thank you, sir. Thank you, everyone.
Thank you, ma'am. Before we move further, I would like to draw your attention to the two links given in the chat box by Gayatri M, certificate link for the participants and also the certificate link for the presenters. We would be more than happy to hear from our dear participants about their experience about these 2 days of the international conference. Your valuable feedback will help us to improve further. I request Kirti Reddy to share her feedback with us. Kirti Reddy.
Sir, can you unmute her, sir?
Good evening to one and all present here. Myself, Kirti Reddy, research scholar from Department of Mathematics, Presidency University, Bangalore. Firstly, I would like to thank the organizers for hosting such a wonderful conference. All the sessions were very informative and extremely helpful for the upcoming researchers. The presenting style and the knowledge shared by all the eminent resource persons were totally amazing. Their zeal and enthusiasm towards research motivate the young minds. Looking forward for many more effective conferences, which includes the lecture from such learned professors. Totally, it was a wonderful and a well-organized virtual conference. Once again, a special thanks to Sri Vidya Mandir Arts and Science College, Christ deemed to be University, and Jyoti Engineering College for this valuable platform. Thank you.
Thank you, Kirti. I now request Nirmala to give her feedback. Nirmala.
Is it, are you asking me, participant, or from your?
Yes, the participant.
Participant.
Okay. So this is, I am Nirmala, Assistant Professor, Department of Mathematics, University College of Engineering, Dindivanam. See, I really appreciate a team of the organizers for having such a wonderful conference that you organized in a very well manner. And you took much effort in each and every part. So actually to speaking, I found very difficult in the presentation, but Jayakumar sir, I think, he called me and he asked what is the difficulty and he made me to present. So this concern is very appreciable. So and you people made well and you collaborated with that other two universities or colleges and you really wonderful. I heartfelt congratulations as well as I appreciate you. Thank you.
Thank you, ma'am. I now request Mohadarshini to give her feedback. Mohadarshini.
Good evening to all. I am Mohadarshini on behalf of Sri Vidya Mandir Arts and Science College, Department of Mathematics. First of all, I extend my most sincere thanks to the Lord God. I extend a very hearty thanks to the resource person who spared time from their busy schedule to grace the occasion. From their topics with their style and their own ideas of explanation of everything from their topics, I mention my hearty thanks to all the resource person because of whom we made this conference possible. I also extend thanks to our head of the department and also to all the assistant professors in our department for their cooperation in the institution of this conference. As the wheel starts rolling weeks ago and requires planning and bird's eye for detail, here we are fortunate enough to be backed by a team of a very dedicated and motivated team of our institution and also in collaboration with Christ, deemed to be university, and Jyoti Engineering College, who know their task and are very much result oriented. So I specifically thank the people who have been the backbone of the event. Finally, I thank all the research scholars who have greatly helped us in organizing their conference. Thank you very much. Thank you for this opportunity and thank you to all.
Thank you, Mohadarshini. Up next, we have Kaushik.
Yeah, are you calling me?
Yes, sir.
Yeah. Thank you very much for this offer. And I'm just delighted to just share my views and experience here at the valedictory session. In the last 2 days, it was really a wonderful experience to me. And I can really appreciate and congratulate all the organizers, the entire team, for very nicely and very lucidly organizing this particular conference for this last 2 days. And of course, I think I just can see in the Telegram web link that there are so many participants who at the last moment are trying to submit their abstracts, and you have accepted them delightfully and organized them and accommodate them very, very nicely. So it's a very wonderful effort. Only 2 things I just want to say here. First of all the lectures, all the invited speakers were really good and really brilliant. The point is, sometimes I have seen that there are certain overlaps, like who are the contributed presenters like me and the invited talks, they are going simultaneously. So in this opportunity, what happens, who are presenting at a certain session, they miss the different lectures, and perhaps all the lectures were very beautiful. So some of the portions were missed by everybody. So that's what I want to say, that in the next future arrangements, please take care of this particular thing, that they should be, the time accommodation should be different one, and that should be split in different ways, so that the plenary lectures can be arranged in a particular platform where there should not be any other contributed paper presentations. And second thing is that in my presentation session, what happened that I don't know, might be this is a technical problem. You are actually using the free Zoom link. That's why after 40 minutes, each time it is getting augmented, and next time you have to freshly start this particular session. So 1 or 2 speakers, they have actually had a problem in the rhythm, because they have already started and they are having 5 or 6 minutes lecture. After that, this was completely, the network failure was done. And after that, he or she has to start again. So please take care of that particular situation. Either I think better to use a Google Meet link, perhaps it is freely working for a certain number of days, and other certain things. That's my share. But otherwise, I want to say that it's a very wonderful experience. I really enjoyed these 2 days session and all the lectures. Thank you very much.
Thank you, sir. We shall definitely be looking into the matters that you've just, issues that you've raised. Up next, we have Arnab Mandal.
Yes, I am audible.
Yes, sir.
Respected all the dignitaries, thank you organizing committee for organizing such a conference in this pandemic situation through online mode. And it will be very helpful for us in the upcoming year if you organize such a conference in the offline mode, so that we can present there in the institute, and it will be good for our collaborative work, and we can gain more knowledge from the respected dignitaries through all the world. Again, thank you to organizing committee. Thank you, everybody.
Thank you, sir. Thank you all for your valuable feedbacks. We shall be looking into the issues that have been addressed here. Talent and skills are the crops that are nurtured, groomed, and given all possible opportunities to grow and bloom. I know all the paper presenters are waiting for this moment. With further ado, I request Dr. S. Pranish to announce the best paper presentation.
In order to encourage the youngsters and more participation in the coming conferences, organizing committee members have decided or selected through the chairpersons of the corresponding sessions. We have selected around 9 best paper presenters. So I'm just read out the names of that. The Vijay Kumar R, Periyar Government Arts and Science College, Tamil Nadu. The title of his paper are Computational Model for the Generalized Dispersion of Viscoelastic Fluid with the Influence of Electric and Magnetic Field. The second one is Anupam Kauta, Indian Institute of Engineering Science and Technology, West Bengal, on the paper Effect of Population Dispersal on the Transmission Dynamics of Infectious Diseases, a Mathematical Approach. The third one is N. Kirti Reddy, Presidency University, Bangalore, on the type paper Natural Convection of Different Hybrid Nanofluids in a Non-Uniformly Heated Annular Geometry. Dr. Kaushik Ghosh, University of Institute of Technology, West Bengal. Fractal Behavior and Spontaneous Criticality in the Daily Data of New Confirmed Cases of COVID-19 in India. Amlan Kanti Halder, Pondicherry University, Puducherry. Solutions of a Financial Model using the Symmetries. Rupa S. Sri D. Devarajaras Government First Grade College, Karnataka. So Laplacian model of sludge energy of some standard graphs. Andrab Mondala, IIT Dhanbad, the effects of diffusion on leech heart neuron model. Zerwin Zin Lobo, St. Xavier's College, Goa. Group methods in solving ordinary differential equation. And last is Priyadarshini, Government Arts College, Tamil Nadu, on oscillation theorem for second order natural differential equation with maximum. All these awardees will be presented with a certificate of appreciation, and congratulations to all of you.
Congratulations to all the winners. Gratitude is the fairest blossom which springs from the soul. The events like this one are the milestone on the journey of life. As we come to the close of valedictory ceremony, I invite Dr. P. Palani, convener, ICNTDEAM 2021, Department of Mathematics, Sri Vidya Mandir Arts and Science College, Tamil Nadu, to give the vote of thanks.
Good evening to one and all present here. I am fully grateful to stand before you all to convey my sincere gratitude to all who should begin the success of this great event. First and foremost, I record our sincere thanks for our founder, Mr. V. Chandrasekharan, who is always with us in all our endeavors. Thank you, sir. Then I thank our secretary, Mr. R.P. Raji, and the additional secretary, Mr. P. Gavadachalam, who has been the greatest support for us in this gathering. Thank you, sir. Then I thank our principal, Dr. T. Balasubramanian, and the vice principal, Dr. L. Gunasekaran, who had given consent for the arrangement of this conference. Thank you, sir. Also, I sincerely thank to Dr. C. Raghavan, head of the department, Sri Vidya Mandir Arts and Science College, Autonomous, Uttarakhand, and Dr. Mayama Joseph, head of the department, Christ Dean University, Bangalore, and Dr. Sunny Joseph, principal, professor, and dean of research, Jyoti Engineering College, Thrissur, Kerala. Thank you, sir. Then I thank Dr. S. Pranesh, Christ Deemed to be University, Bangalore, and S. Jaykumar, and Dr. P. College, and Dr. Conveners, and Dr. Joseph Varghese, Christ Dr. J. Sadish Kumar, Dr. J. Sadish Kumar, Dr. S. Anthem, organizing activities. Thank you, sir. Then I thank all the delegates who had from all the corners of the states in no particular order. I thank Professor Modi Matande from South Africa, Senior Professor Dr. P.G. Siteshwar from Bangalore, Dr. Mugesha Narayana from West Indies, Dr. C. Kanchana from Sri, Dr. Sunny Joseph from Kerala, Dr. A. Abuja from Kuku, Dr. R. Prakash from Bangalore, Dr. S. R. Sudhendra from Bangalore, Dr. A. Abdul Hakim from Kuwait, Dr. A. George Maria Selvam from Tirupati, Dr. S. Hartley from Periyar University, Salem, Dr. Vishwari Prem from Krishnagiri, Dr. S. Hartley from Chennai, and Dr. S. Sauri Rajan from Kuwait for shaping and molding our knowledge. I thank you all so much. Then I thank to all my faculties of Sri Vidyamandir Arts and Science College, Autonomous Othangarai, and Christ deemed to be University, Bangalore, Jyoti Engineering College, Tiruchur, Kerala, paper presenters, media and audio persons, research of various universities, colleges, professor of other colleges, and each and everyone. Thank you, sir.
One small request from everybody. Please, can you switch on your audio or video, so that we can take one photo. This is for the reference. All of them who are there on that, if we can, we'll take a screenshot of.
Requesting all the participants to kindly enable your videos so that we can take a memory.
Please, Alar, open your video. Participant, please open your video. Sumita ma'am, Mohan Priyadashini. Nirmala. Shagu Ghosh. Uma. Please open your video. Falani, open your video. Nirmala.
We'll take one overall there. One will take 17.
Shivaraman.
Thank you, sir. Thank you very much, sir.
Thank you all. Thank you.
Yeah, yes, sir. Continue.
The end of a story is the new beginning for many others. On this note, let's conclude a remarkable, memorable, and knowledgeable session. On behalf of the institution, we sincerely thank the dignitaries for being with us this evening and enlightening us with their enthusiastic remarks. I shower my heartfelt gratitude for each and every person present here. Thank you very much. Have a wonderful and fun-filled evening.
I also take this opportunity to thank Ansa Matthew for from the whole day she is managing with that, and all the other supporters for her, Gayatri, Meghna, Richa, and special thanks to Smita Madam, because the whole day they managed the entire program. On my behalf, thank you very much for all of your cooperation. And thank you, Raghavan sir. Thank you, Muniratan sir.
Yes, one second, sir. National anthem is there, sir.
Yeah, we'll do it, sir. Yeah. And so Matthew, you can just announce for a national anthem.
Yes.
I request all of you to kindly stand for the national anthem.
चंचल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगल दायक जय हे पालक भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you, Pranesh sir.
Thank you, sir.
Thank you for your whole team, sir.
Yeah, thank you, sir. Thank you very much.
Yes, sir. Thank you, Smita ma'am.
I think she is not there.
Thank you, Raghavan sir.
Yes, Mayama Joffers ma'am. Thank you for your.
So your enthusiasm is really great.
Yes, ma'am.
So continue being young and enthusiastic and energetic.
Yes, madam. For your kind support, madam.
Thank you.
Sir, Raghavan sir, we have shared the Google form for certificate.
Yes, sir.
So if they fill up and submit, they'll get a certificate for this.
Yes, sir.
And this, now what is this? This appreciation certificate, we'll be sending you little later because we are not prepared for that. But tomorrow or after, we'll be preparing and sending to that.
Yes.
Prize best paper presentation.
Yes, sir. In addition to that, we need 9 chairperson participate certificate also, sir.
I'll check. So otherwise, we can give them a letter of appreciation. The letter we can give.
Yes, sir. Yes, sir. Yes, sir.
I'll prepare and let you send it.
Yes, sir. Yes, sir.
I'll see that one.
Yes, sir. Thank you for your nice support, sir.
Yeah. Thank you, sir.
Thank you, sir. Thank you, sir.
Can we leave, sir?
Yes, sir.
Yes. Thank you.
Thank you.
Thank you, madam. Thank you, Answer. We can leave.
Thank you, sir.